optical and microwave circuits. And today he will talk about novel aspects of microwave technology. So thanks to Professor Berselli. I don't know if you can share the screen.
Okay. Do you hear me?
Yes. Unfortunately, we still cannot see the screen. We see you, but not the screen.
Do you hear me?
Yeah, we hear you.
And do you see me?
Yes.
It's a big problem because now I use my wife's laptop, which is very unusual for me. But I hope that I will go further. Now,
Excuse me, Professor, you can move your mouse to the bottom of your screen to that you appear share screen, green button with share screen.
But I don't see.
Move your mouse. Okay, that's good.
Okay.
Now, what I can do.
You may just open the slides you have, and we can see meanwhile your screen, so it is perfect.
Where can I find? Do you hear me?
Yes.
Yeah, yes, we can hear you.
Give me just 10 minutes and
Do you see that I am looking for the
Yeah.
talk? Oh.
Bear with me. Huh?
Okay.
هذه العشرة سهلة
Do you see?
توصل لما تقول لي دابا شوي شاطر.
Yes, we can hear you. Yes. Yeah, we can see the presentation. It's fine.
Do you see my slide?
Yes.
Yes?
We see them.
It's is it my voice strong enough?
Yes, it is.
Yes. So can I start?
Yes, please.
Okay. So I would like to mention a very brief historical background of microwave technology, because microwave technology has a long history and tradition. In the middle of the last century, its main activity was in the development of radars for civil and military applications. That was followed by long-distance point-to-point interconnections carrying television programs and multi-channel telephone traffic. After some decades, this service was taken over by long-distance fiber optic links. At the turn of the century, new application areas appeared in mobile networks. Microwave links provided connections between the central stations and radio base stations, as well as between the radio base stations and the subscribers. Step by step, the connection between the central stations and radio base stations are taken over by fiber optic links. Presently, the picocellular mobile networks and the autonomous vehicles offer new application possibilities. As I mentioned, the title of this presentation is Novel Aspects of Microwave Technology. In that context, we consider microwave technology as a very wide field. The main trend is to extend the applied frequency bands to higher frequencies, that is to millimeter wave bands and also to terahertz frequencies. This trend involves significant research and development activity, which results in new devices, new technological procedures, new circuit and system concepts. The first task is signal generation at millimeter waves and terahertz frequencies with high stability and low noise. That is a crucial problem. The traditional construction of a free-running oscillator can be used at millimeter waves. However, to construct a millimeter wave oscillator, the necessary devices had to be developed. The main achievements were obtained by integrating a complete circuit block based on nanotechnology. However, due to the very small dimensions which are obtained this way, the available power is also very small, in the range of microwatts. Now I would like to show you, sorry, what happened? Sorry.
You can just close the window. Your presentation is behind, Professor Tibor. Just close these windows.
Maybe you see that I am looking for the lost.
Yeah, okay.
Okay, that is a contact problem. Right. Maybe. Oh, that is terrible. So may I continue?
Yes, please.
I am very sorry for this problem with the laptop. That is some contact problem, as I see. So coming back to the presentation, signal generation at millimeter waves. I show here a chip which has a size of 2 × 2 millimeter and works at 94 gigahertz. You can see a complex chip which has a VCO voltage controlled oscillator and also a mixer. But now we are interested in the oscillation procedure. On the right side, you can see a diagram, a measured diagram showing the tuning possibility from 90 to 97 gigahertz. During this tuning procedure, the output power is almost constant. Frequency stabilization at millimeter waves. The frequency stability of a free-running oscillator is not sufficient in many applications. For example, this one which I showed also. For automatic frequency control, a phase lock loop is applied. It needs a reference signal with high frequency stability. That is well known. I only repeat it to mention other problems. Usually, a quartz oscillator provides a stable reference signal, and its frequency is multiplied to the millimeter wave band. That is the problem, because with frequency multiplication, the phase noise is increased as well. That relationship limits the applicability of AFC frequency stabilization at millimeter waves. The former problem can be reduced by the injection locking approach. When an external loaner signal with a frequency equal to the free-running oscillation frequency is injected into the oscillator, then the oscillation frequency is locked to the injected signal frequency. At the same time, the variation of phase, that is phase noise, is also reduced. For the procedure, the injected signal has to be more stable and less noisy compared to the oscillator stability and noise. There is a relationship for the locking band which depends on the Q factor, frequency, and the ratio of the injected power and output power. So here I show you developed circuitry utilizing both injection and phase locking. As you see in the diagram, block diagram, the reference signal is divided into two parts. One part is injected directly into the oscillator, and the other part is used for automatic frequency control to increase this way the locking band, as I mentioned. And here you can see the effect. Without PLL, the locking range is very small. And when the PLL is closed, we have a locking range much wider compared to conventional injection locking. That means when we have no AFC simultaneously, then we have 50 times wider locking range, as you see in this figure. And as I mentioned, also the noise behavior is improved significantly. So you can see here in this figure, the free running output signal, which is, and its noise, phase noise in dBc over Hertz on the vertical scale. And on the horizontal scale, you can see the offset frequency. Then we have an injected signal which has a phase noise much better. In that case, this reference was the force multiplied frequency, so the original was 23.4 gigahertz. So we got the force harmonic in the 90 gigahertz band. And using this locking procedure, we could get the figure in between, for example, minus 83 dBc over Hertz at 100 kilohertz offset frequency. Now another example, a millimeter wave oscillator using CMOS technology. This oscillator has a pair of transistors, as you can see here, and we get an output power minus 20 dBm and a phase noise of minus 93 dBc at 10 megahertz offset frequency. That is not so good if we compare it to the previous case. And you can see the circuit layout and the spectrum of this W-band oscillator. Another example, 520 gigahertz oscillator on a 130 nanometer silicon germanium HBT technology. It uses a traveling wave distributed topology. In this example, 4 transistors are cascaded and produces minus 54 dBm output power, which is 25 nanowatt. Very small, but we are at a very high frequency. which is the third harmonic frequency of the oscillator, and it is at 520 gigahertz. You can see also the oscillation spectrum. Now, a third example, what I want to show you, integrated 200 gigahertz graphene-based FET receiver, which contains not only an oscillator, but also amplifier. It is the amplifier port. So the oscillation frequency and the input frequency is 200 gigahertz. And the IF, let's say, intermediate frequency at 1 gigahertz. At the diagram on the right side, you can see measured data, the conversion loss in decibel versus local oscillator power in dBm. The conversion loss is extremely high, in the range of 30 to 60 decibel, which is very unusual in the microwave band. Usually we have less than 10 decibel conversion loss, but we are at very high frequency in this case. So the conversion loss is presented here again versus the frequency, radio frequency in the range of 200 gigahertz. That is with high local oscillator power, and the result is in the range of 30 decibel. You can see also the band of the IF frequency around 1 gigahertz. A further example in the terahertz frequency band, and indium phosphide heterojunction bipolar transistor is used as a terahertz detector. So the frequency range is presented here, 0.25 to 3.1 terahertz. And the modulation bandwidth is up to 10 gigahertz. You can see a very complex device structure. That is the cross-section of the principle of the cross-section of the device, a heterojunction bipolar transistor. Then the next figure shows the micrograph of HBT and configuration of the contact pads. And the third picture on the right shows the package of the test chip where the transistor is in the pot of this picture. So we have also multipliers in the millimeter wave band. That is an example from 40 to 80 gigahertz, high power. That means we want to use the output of the multiplier as an output of the block. Here you can see the picture of this construction. The input signal is coupled to the diodes in a reduced input waveguide. You can see the height is 1.1 millimeter. So, and the filter structure can be seen as well. So that is a very small device. The planar Schottky diode is flip chip mounted on a filter and located in the split waveguide block. The diagram shows the output power versus input power. As the input power is, for example, at 300 milliwatt, we'll get about 100 milliwatt output power at 80 gigahertz. And this doubler is cascaded to a 80 to 160 gigahertz high power multiplier, frequency multiplier. You can see the efficiency on this diagram on the left side. So around 160 gigahertz, the maximum is 23% efficiency. Not bad compared to the very high frequency. But you can see that when we increase the injected power, we are approaching some saturation step by step. And so for example, this 200 milliwatt output power, we get 35 milliwatt output. And in the former diagram, we could get 100 milliwatt. So if it is injected into this multiplier, then we will get 25 milliwatt. Then there is an interesting device, tunnel diode. And using tunnel diode, a resonant tunneling oscillator can be constructed. I would like to mention you the story of tunnel diodes, because I was using tunnel diodes before the turn of the century, around the 80s. So the tunnel diode was that time the first device which could provide microwave frequency oscillation in the range from 2 to 10 gigahertz. Then step by step, transistors, the operation frequency of transistors was increased into the microwave band. And the tunnel diode oscillator was not important in this band. But that time, tunnel diodes could be used to higher microwave frequencies. Later, even in the millimeter wave band. And now, this construction, naturally, after significant improvement, can deliver power at 1.9 terahertz frequency. And the advantage of this device is that it can operate without cooling at room temperature. Now I would like to change and switch to opto-electronic oscillator, because the opto-electronic oscillator utilizes both microwave and optical technology. So that is a much more complex construction, but it has significant advantages. If we compared this principle to the traditional microwave oscillator principle, we could get significant improvement, mainly in the noise. For example, dielectric oscillators, which are widely used in the microwave band, can have a high Q factor between 5,000 and 10,000 and a really very low temperature dependence. However, in many applications, these properties are not sufficient, mainly at millimeter wave frequencies. So the opto-electronic oscillator, which has a block diagram as a basic block diagram, is presented here. We have a continuous wave laser source and a Mach-Zehnder modulator. And here is the closed loop, feedback loop. So from the Mach-Zehnder modulator, which has a modulation in the microwave, millimeter wave band, we have an optical beam carrying the, let's say, millimeter wave modulation. Then we have an output coupler, and one part of this signal is detected in a photoreceiver. So we regain the microwave signal, which is amplified, filtered, and coupled back. So that is a complete closed loop. This way, we will get the advantage of using the optical method. That is the reason that we can have a relatively long, let's say, Fabry-Perot resonator utilizing the fiber. That means we can have a more multi-wavelength resonator in the optical domain. And the fiber has a very low noise. Therefore, the Q factor can be very high, even very close to 1 million, but that is a very special case. But around 100,000, sometimes of 100,000 Q factor can be realized. However, we have a problem. What is presented here in this formula, that the neighboring resonances, delta, are very close. And it depends on the length of the fiber. It is the L means the length of the fiber. If we, for example, use a 100 meter wave, if we use a 100 meter long glass fiber, then the frequency difference between the neighboring resonances is only about 1 megahertz. That is a problem. For that problem, we use the bandpass filter. Now we are facing a problem. When we want to use very low noise, that means high Q factor, then the length of the fiber should be long enough. But then the neighboring resonances are too close, and it is very difficult to develop a bandpass filter for a very narrow relative bandwidth. So this we have to make some compromise. But there is another possibility. This difficulty can be overcome by a dual feedback loop. So if we use not only one loop, but two loops, that the method is that we use two fibers, a longer one and a shorter one. And then we can get a significant improvement in that means the neighboring resonances will be shifted significantly. And this way, these resonances which are far enough in the frequency band can be suppressed by the microwave filter. Here you can see the amplitude and phase behavior of this dual feedback loop using two parallel fibers. And also the noise can be improved significantly. That is an example when you can see the single sideband phase noise, dBc over Hertz, as a versus offset frequency from the carrier frequency in megahertz. So the solid line gives the simulated results and the dots are the measured results. The black one is for a single loop, one loop, and the white line and dots are for a three-loop case. So significant improvements. Signal generation is possible also by optical mixing. That means we have two lasers, as there is a mastered laser and a slave laser here. Their beams are mixed in a photodetector, and we have here a feedback loop to get some stabilization. In the loop, we have a loop filter. Also, some thermal tuning possibility can be used. So in this way, new results demonstrate microwave generation at 120 gigahertz and 300 gigahertz, respectively. The main problem is the high-speed photodetector. There is another possibility for optical generation of microwave or millimeter wave. That is the mode-locked laser. That means the laser operates in two or maybe some more modes. And these modes are separated in frequency, which is in the microwave or millimeter wave. By mixing these two modes, these two beams coming from the mode-locked laser, we can generate microwave or millimeter wave signal. However, the stability of the signal is relatively poor. Therefore, the oscillation modes have to be locked in some way. That is the title not locked laser. For that stabilization, several methods are applied. That is a passive stabilization when we use a microwave cavity in the feedback loop. Active stabilization means that the generated signal is fed back. That was shown in the diagram in the cross-section or block diagram, which I presented. No, sorry. Here I presented here. That is an active mode blocking, even for two lasers. And finally, that is the self-mode blocking. So now I would like to mention briefly that mobile communication networks is a wide application field for high frequency, that means millimeter wave frequency radio connections. Many difficulties are in the millimeter wave because presently the central station is connected to the radio base station by an optical fiber, and a millimeter wave is used for connecting the radio base station to the users. However, the optical connection should be good enough. And here I only briefly show you two diagrams. When we have polarization controllers, then we can improve the signal transmission over the fiber. So without polarization control, you can see the eye diagram. Then at the transmitter, we use polarization control. It offers a good improvement, and when we use this polarization control in the receiver as well, then we get very fine transmission. And we can increase the capacity of optical connection by double two polarizations on the same fiber, vertical and horizontal polarization. So usually in the millimeter wave band, 60 gigahertz frequency is used, and picocell construction, picocell networking construction. Finally, as time is flying, finally I only want to mention novel fields of applications. Autonomous vehicle, picocellular mobile network, proximity sensors to avoid COVID in problems, robotics, telecontrol of drones, children, noise, security tests at airports and every other, so other locations, tests in manufacturing. So finally, I am very sorry with the technical problem of my computer, what could be solved finally using another laptop. So thank you for your attention.
So thanks a lot to Professor Berselli for this interesting presentation. And it was particularly nice to see a mixture of topics bringing together optical aspects and the integrated circuit aspects. But before leaving the floor to the questions of the audience, I would like to ask a question from my side. In particular, I would like to know from Professor Berselli, how does he imagine the impact of microwave photonics, in particular silicon photonics, in the beamforming technology for phased arrays?
So, I would like to, maybe you can see more my voice. I would like to mention that that was a survey of the field. So some parts were produced by my group at the Technical University of Budapest, and some other parts of the presentation were used from the publication of my colleagues. So I always presented, I cited the publication. What I would like to mention, that at our university there is no possibility to develop nanotechnological devices. So we can work on the circuitry problems, first of all. And also what we could do, the combination of optical and microwave technology. So what I showed you, the opto-electronic oscillator, that has been done together with my group. And also the 94 gigahertz oscillator has been developed with cooperation with Fraunhofer Institute in Germany. So we use the possibility, first of all, in the framework of cost projects, and also we were participating in European consortiums. And therefore, we have good relations with University of Duisburg in the optical field, then CNAM in Paris, France, and many others. Valencia, University in Valencia with Professor Capmani. Also Bucharest in Romania, we have a colleague there. And so on. Sorry for this ringing of phone. So
Okay.
we could use, first of all, a cooperation with Drexel University in Philadelphia, Peter Hertzfeld, for many decades. In the last 3 decades, we had very close connection with Drexel University, and first of all with Peter Hertzfeld and his group, Afshin, Darius, Harry Rosen, and so on. Many students at Drexel University were also involved into this cooperation. That is what I could tell to your question. Maybe it is not sufficient, I don't know.
Many thanks. I don't know if we have other questions from the audience. If not, maybe I have another one concerning LiDAR applications. As you mentioned before, automotive application
Yes.
could be a huge domain for this type of systems. So, what do you think is going to happen in terms of application from for this specific area?
You mean LiDAR?
Yes.
Yes, the main advantage of this technology is that the very high frequency of what is used in the optical domain. I would like to mention that actually these devices work not in the visible optical range, but close to the visible optical band, but in the infrared band, around the 1.5 nanometer wavelength. So the main advantage, the very high frequency, therefore it can be used for short distances, which is very important in the case of autonomous vehicle, because the main purpose is to get information about the neighborhood of the vehicle, of the car or truck or any device, any type of vehicle. Otherwise, the principle is very similar to the microwave radar. Naturally, it is important to get data processing. That is very important because we get sensors like LiDAR or LiDAR. We get sensors around the vehicle in many directions, and the processing of the obtained data is very important to get proper actors in the self-driving. That is what I can tell you about this.
Thanks again. I don't know if there is any other question for Professor Berselli.
Thank you.
So if not, I think we are quite in time with the schedule, so we may thank Professor Berselli for this nice presentation. And I leave now the floor to Otman.
Thank you, Professor Luigi, for sharing this session. And thanks, Professor Berselli, for a wonderful presentation. And now we have a break of 30 minutes, and then we will start another talk, another exciting talk given by Professor Miguel Berruti from the Public University of Navarre. So we have a 30-minute break, and then we can start. So stay with us.
Enjoy.
Hogy ezt így meg tudtad tartani. Hát ez valami hír.
És ez nem működik. Hogy itt nincs, csak 3 csatlakozás.
Hát dehogy nem, hát oda kell bedugni.
De hiába dugod be, mert akkor nem tudtam bedugni a pendrive. Hát ezen a laptopon nincs több hely. Tehát a pendrive el volt dobva, akkor csak ennek a mikrofonja, és ennek a hangszórója szól.
És hallottad azért?
Tessék?
És hallottad azért?
Hallottam, de hát ugye a végén megyek is.
Ja.
For the let's say provisional agenda, the partners, and knowing also the you know, highest ranked to other partners, there are some. Mhm.
Hello. Hi, Otman. Hi,
Hi,
everyone.
Miguel.
How
Good
are
morning.
you? Good
Fine.
morning.
And
Good
you?
morning. Very well. So sorry for not having connected before. I was busy. So
Okay, no problem. Take your time.
all right, all right. So yeah, just to check. Let me just share my screen.
Okay.
Just a minute. Okay.
Now it's okay. Now it's fine.
Okay. Can you
Yeah.
see it's full
Yeah,
screen?
yeah.
Oh, great, great.
Okay.
Okay. Very good, very good. So how are you doing?
We are fine. And what about you with this
Well,
particular situation?
yeah, you can imagine. You can imagine.
Yeah.
I guess everybody's in similar situation.
Yeah,
I'm at home right now, so
yeah. Okay. So what about classes? So giving them remotely or?
no. Here in Pamplona, in spite of the fact that we've had a lot of, cases of coronavirus, we didn't stop the cars, and we've been presential teaching all the
Okay.
time.
So
So
it's fine. It's good.
yeah, sometimes it's a bit dangerous.
Yeah, but okay.
I mean, for the students, probably yes, that's the best, and also for us teachers, it's
Yeah.
also It's also good. But the situation is quite strange. Now it's quite cold here, Pamplona, and we've been teaching with windows open, and people are freezing in the classes.
Yeah.
You can imagine.
Yeah.
I see my students with the coats on.
Yeah.
And myself, I try to be normal, but it's difficult.
Yeah.
Anyway, that's what we have.
Yeah, but it's better than teaching
Yes.
remotely. Okay, so we have
Yeah.
in touch with students. It's fine. You can do your labs. Okay.
Yes, definitely.
Yeah, that's the
How are you
important.
doing? Are you remotely or are you presential?
No, remotely. Okay, everything
Oh.
is remotely. Okay, so now we are thinking maybe if the situation is getting better in the next month in January, maybe we can have some presential session, for example, for labs. Okay, so to catch up what we have lost in the past months. Okay, so this is the situation now.
Good
So
luck.
we have to deal with it.
Yeah, this is what we have to do, everyone. You're right. Okay. Anyway, I'm glad to see you, even though remotely.
Okay.
Okay.
It has been a long time we didn't keep in touch. Okay.
Yeah, maybe no more than 1 year for sure.
Yeah.
Okay.
So maybe after this we can set up a meeting. Okay. So we can discuss.
Yeah, there were several proposals, I remember, but all this COVID situation has changed everything. So
Yeah.
we need to rethink everything now. Anyway, as you say, we can talk in the future.
Yeah.
Sure. That would be great. Okay. So let's wait. Okay, switch off my.
We have here Professor Luigi and Professor Gragnani, and also we have Professor Saidi, and now I think I see Professor Belotti join us.
Yeah,
okay, so.
he's here. Yeah, great. Okay, I'm going to switch my microphone off. Okay.
Ils ont plusieurs réunions, j'essaie de faire mon mieux, comme tu sais.
Okay, good morning, everybody. Professor Gianluigi, you are with us?
Yes.
Okay, so I think we can start your session, please.
Yes, welcome everybody. Let me introduce the next speaker, Professor Miguel Berruti from the Public University of Navarra. I guess everybody know him, but anyway, is still very young, but is one of the most proficient and appreciated researchers in our field, and especially about metasurfaces, TRS technologies, opto-electronics. Furthermore, he was awarded many prizes and honors. And first of all, he is one of the past winners of the Yarman Carlin Prize. So this is also to witness the high quality of the MMS group and conference. I think his talk will be very interesting for all of us. And so, Miguel, please.
Okay, thank you very much, Professor Gragnani, for this very nice introduction, and mostly for saying I'm still young. Okay, so thank you very much, because I'm getting in that age where I'm, people, students just look at me like with some respect. So thank you very much for the introduction. It's my pleasure to be here with all of you in this remote conference. Of course, it would be much better to be in person, but this is COVID time, so we have to adapt. So maybe next time, I don't know. In any case, as Professor Gragnani said, I'm Miguel Berruti. I'm from the Public University of Navarra. And here I'm going to talk to you about some metasurfaces that we have developed for wave control at millimeter waves. So this is the outline of my talk. If you allow me, I'm going to switch off my video because probably I will have some problems with bandwidth at home, so I hope you don't matter with that. This is the outline. I'll first start with an introduction to millimeter waves and terahertz technology, just to give you some motivation of what I'm going to talk about. It will be mainly related with communications and communication technology. And then I will just mix with metamaterials and metasurfaces. And then I will show you some of our recent developments. They are really recent, so you will be the first ones in seeing them. So I hope you appreciate it. Is a super oscillatory meta lens, and something different, also a meta lens, but based on geometrical phase concepts. And finally, the conclusions. So let's go. This is, sorry, this doesn't move. Also problems, technical problems here, sorry. So now. So let's start with millimeter waves and terahertz technology. As I said here, we are trying to bridge the terahertz gap, and you will see why I see this in my slides. So first, to begin with, we are in a microwave symposium. So I guess most of you know very well about microwaves and the possibilities that we have in microwaves. Of course, almost any device, any gadget that you are using right now in wireless technology will be operating here at the microwave band. You can think of cellular mobile phones or Wi-Fi or Bluetooth or many other technologies. The fact is that probably it's a very good range to operate these wireless devices. The problem is that the microwave spectrum is getting saturated. This is one of the bad news that we are facing right now. Another reason is that we as users are getting very demanding in technology, and we mostly young people, our students, want to share more and more data. Now, voice is not so important anymore. What is important is to be able to transfer in very short time huge quantities of that data, like photographs or videos. So the question is that if we are going to operate below 6 gigahertz, then we have a problem because we don't have enough bandwidth, and we need to move to further frequencies, to larger frequencies like the millimeter wave spectrum, which is exactly the spectrum that we have here, the upper part of the microwave range. Roughly speaking, it starts at around 30 gigahertz and it goes up to 300 gigahertz. And here probably is where we have to look up more closely in the future if we want to develop wireless devices. So here are some of the millimeter wave bands which are being proposed right now for future communication systems. In fact, if we look at the current situation, if 2020 would have been a normal year, we should have now in several countries 5G operating. Of course, everything has been delayed a bit because of some pandemic situation that we all know. But in any case, the tendency is quite clear. When we were speaking of one or two, the first two generations, the main focus was on voice applications. But starting at 2.5 third generation, then mobile data becomes more and more relevant. And this is more clear in the fourth generation, and now with 5G, probably we will have to be more careful about that. You can compare here in this graphic how the data rate is evolving from 10 to 100 kilobits per second, and now we're speaking of 1 gigabit per second. So this means that we need higher data rates from megabits per second, for instance, to gigabit per second, and this implies at the same time that we need more bandwidth. So a clear strategy to get more bandwidth is to use higher frequencies, so then we should move to the millimeter wave band. And this is also happening at the same time that we are developing the Internet of Things, where virtually any device will have an IP address. So now we need very fast communications, but at the same time, we need to be able to manage many communications at the same time, because we will have wireless connections with any gadget, and even with between cars or in home systems that we will need to control remotely. So this is a clear motivation for us to explore the millimeter wave band. And probably in the future, we will be more involved on that. Now there are groups working on 6G, even in 7G. In the tendency is clear, as you can see it here. This arrow is always pointing upwards. So we will be speaking of probably terabit per second capability in the future networks. So we need to explore those frequencies in order to get this wider bandwidth and the higher data rates in general. So this will move us steadily from the microwave to the millimeter wave band, and probably we will be speaking in some years of terahertz band for realistic communications. Now the terahertz band is mostly a range for exploration, maybe mostly are related with basic science. Of course, there are technological developments, but at the present time, not so much technology involved, and not so much or not so many useful communication systems ongoing in this technology, in this band. But this will probably change, and we will be able to be speaking of some devices operating at this frequency for some particular applications. In fact, we will be, or we could be speaking in the future of terabit per second links with connection in, you know, virtually any place you can put a transceiver. For instance, in the street lamps or buildings, we could even have indoor communication systems. This is a bit science fiction. They are envisioning here that we could have, you know, the doctor at home in this hologram representation. So we would have the possibility to speak with the doctor without moving from home. Okay, this is probably some science fiction at the present. Maybe it will be reality in the future. Anyway, we'll have huge bandwidth for our systems if we use the terahertz band. The problem with these waves is that they are very short range because they decay very, very fast. First, because they have a very small wavelength, so the propagation loss is quite high. And second, they are easily attenuated due to gas attenuation, mainly water vapor absorption. So these communications, of course, will not be long range. They will be limited to some meters at most. But this is not a problem in this Internet of Things context, because by definition, the communication should be small, because we want to communicate many gadgets, many devices at the same time, and we would like to avoid interference. And of course, if we want to communicate in this indoor environment, we don't need to go beyond this room. So this shouldn't be such a problem if we think of future systems under this new perspective. Anyway, now going more closely to what I'm going to present here, for us, this terahertz band and millimeter wave band, I will speak of both of them like, you know, interchangeably. Of course, they are not exactly the same, but we are working in the limit between both. For us, it is very interesting to explore this band because it allows us to mix together metamaterials concepts and plasmonic concepts, because they simply fit very well in the terahertz band. So if we have to think of future technology, why not using these concepts which have revolutionized electromagnetic research? So this is probably our main motivation. Even beyond technology applications, we would like to see what we can do with metamaterials and plasmonic concepts at the terahertz band. So this is the motivation, and this is what we are going to do. So first, I will start with this description of a super oscillatory metal lens. Let me tell you, just as a forward, that we have had some experience at the Public University of Navarre in the design of metamaterial lenses. We have these designs here that have been done in the past. For instance, a plano-concave lens, Sorel metal lens, Woodson plate metal lens, a Fresnel lens, biconcave lens, and epsilon near zero metal lens. Of course, we like all of them, but we must acknowledge some of their defects. Probably the main one is that they are all limited by resolution. They are unable to get super resolution. So let me just first start defining what we understand, or what it is understood by super resolution. In principle, we say that we have super resolution when the resolution of this device, of this lens, optical device in general, is below what we call the classical diffraction limit, which is the minimum distance that we can put two different point sources and still be able to distinguish them. In order to compute this diffraction limit, we have some classical numerical criteria. I put here two of them, the Rayleigh criteria and the criterion, and the Abbe criterion. For this example here, with these numbers here, we have represented these two cases with two sources close together. And for the Rayleigh criterion, we have this situation. The distance in this with these numbers should be around 2.06 millimeters. You can see that is quite conservative because it's very clear that we have two different sources. With the Abbe criterion, the distance is a bit smaller, it's 1.69, and is more relaxed if you want, because it's assumed that we have resolution, even though it's quite difficult to distinguish the sources, but there is still a very small valley between them. So with this, we have still resolution. So in order to compare our devices, we will use this one because it's the smallest distance. And if we are able to beat this one, then we will be also beating this one. So we are going to compare always with the Abbe criterion in our devices. So how to overcome this diffraction limit? Well, from the beginning of metamaterials research, this was one of the main motivations. In fact, back in 2000, Pendry proposed this revolutionary work about the Pfeffer lens. He argued that you could have a perfect resolution of the stars at the focal position by simply using this slab with this refractive index n equal to -1. In this situation, you have focusing of the propagating waves, that's quite well known, and at the same time you have this amplification of evanescent waves. So all the information that you have in the stars is replicated here in the focus. Of course, this was a very revolutionary idea, an excellent physics behind. The problem with this is that when you come to implement this Pfeffer lens, then you will have loss because this is unavoidable, and then these losses kill somehow this amplification of evanescent waves. Anyway, this was just the beginning of a series of works where researchers tried to improve the resolution of the lenses. And here is another very influential work, the super lens, which uses a single silver slab in order to have better resolution than conventional lenses. This operates very similar to the Pfeffer lens, but only for T waves. Here they're exploiting the plasmon resonances, the plasmon waves that are supported at in the silver slab. Other ideas are, for instance, also stemming from the metamaterials research is the hyperlens. The idea here is to use this coating with these concentric multilayers and then transport the near field information of two sources here to the far field by guiding them. Okay, and this was also very popular at the time. And other strategies are, for instance, using spheres with conventional microscopy systems, so that you have here better resolution than with the microscope alone. This is similar to what we did with the photonic nanojets, where here we were using the dielectric cube, and when we illuminate this cube with this plane wave from the left, for instance, then we have this jet at the output, and this jet has some super resolution that can be exploited in this type of applications. And another different possibility is the use of super oscillatory lens, which is what I'm going to talk here about. The main idea is to use masks and then have some interference between all these points here in order to have a focus, so that this focus is sub-wavelength. So let me explain this a bit more in detail from a mathematical point of view, and with very simple terms. So what's this super oscillation about? Here is this simple example. We have, yes, this super oscillating function which is composed of 5 sinusoidal waves. You can see here we only have 5 harmonics. From n equal to 6 and more, the coefficients are 0, so we only have these harmonics here. So this is the red curve that we have represented here, and this is just a zoom-in view of some interesting zone. First of all, of course, the maximum frequency of the Fourier transform of this function is 5, because this is the highest harmonic. This is completely straightforward. But if we represent this highest harmonic function, we have this blue curve here, which oscillates much slower than the original function. So now, if we want to approximate this function, the red one, locally, we can have this function here, where now the frequency is 43.6. You see that this is a very good approximation in this local approximation, and then we can say that this reminds us of some function which is oscillating at a frequency much higher than the maximum frequency of this harmonic. So this is the main idea. We can have some super resolution, super oscillation at some local zones, even though we are in a band limiting function. So this is the main idea, and this is what is exploited in super oscillatory lenses, having this type of behavior in order to have super resolution. And this is the typical approach that has been used. Researchers used a mask where they are implementing these rings with opaque and transparent zones. The opaque zones usually are metals, nothing more than that, and the transparent zones are just air or some dielectric, okay? And the idea is to have this interference pattern so that it is possible to get this super oscillation here, where you have this very narrow focus, of course, with some small amplitude, because this is the price you pay if you want to have this huge super resolution. You will have not much energy here, and you will have a lot of energy in the side bands, in the side lobes. But in microscopy applications, this is not such a problem because there is usually a lot of energy to play with. So even though the efficiency is not very high, the resolution that it is possible to obtain compensates this loss of energy. And here is a table with some results extracted from the literature, and you can see I have highlighted 2 columns. Here is the average resolution limit for all these works here, and here is the full width half maximum of the focus, and you can see that in all cases we have super resolution. This full width half maximum is below the average resolution limit. Well, the problem with this, or well, let's say the limitation, it's not such a problem because this is something that the researchers were expecting. The efficiency is low in general, and this is typical of super oscillatory lenses. If you check these references, you will find that it's below 5%. And another point is that as the focus is made narrower, the concentration of the electric field in the focus decays exponentially, and also the level of the lateral lobes increases strongly. So our plan here, our aim here was to try to improve these numbers with our own design. And we found that the typical super oscillatory lens implementation is based on this opaque and transparent zoning. It doesn't matter if it is with revolution symmetry or with straight devices, with straight grooves, for instance. In our proposal, what we want to do is to have more efficiency by simply replacing these opaque zones and the transparent zones with metasurface designs with different particles for even and odd zones, for opaque, what was before opaque and transparent zones, in order to have increased transmission efficiency. The idea is that these metasurfaces, of course, will not have total transmission, but will have a transmission above 0.5, it will be the largest possible transmission in each case. I will show you later, but this is something important, that with preliminary tests and simulations, we have found that we should have at least a phase difference between the even and odd zones of 30 degrees. I will show later the results that support this assertion here. And finally, most of these lenses are designed using optimization algorithms, and we had to redefine or redesign the optimization algorithm in order to reduce the level of the side lobes. So our main aim is to have higher efficiency and reduction of the side lobes. So here is what I said before, the study that demonstrates that we need to have at least 30 degrees of phase difference between the even and odd zones. We start with 2 degrees difference. Here is the lens in the top position. You can see that if we have only 2 degrees of phase difference, there is a very tiny focus here, but not very clear. Now, if we increase the phase difference, the focus is a bit better, still not very relevant. With 16 is even better, 24 now it's a clear focus, but we still have a lot of power near the lens. And when we move to 30 degrees, now things are more clear. Of course, with higher phase difference, the focus is prominent in all these map here, and we have almost no energy near the lens. But as a compromise, because it's very difficult to get this phase difference between the zones and still have good transmission coefficient magnitude, then we will stick to 30 degrees in our designs. And how we implement it? Well, there are several possibilities. We started with this, and I put forward that this will not be the final design, but it's good to start with this in order to understand how it works. So we start with this annular ring slot, where it's just simply composed of metal, aluminum, and thin dielectric substrate for fabrication purposes. And what we do here is to vary the radius, the diameter, sorry, of this ring slot. And here you can see the transmission coefficient magnitude map as a function of this diameter and the frequency, and the same for the phase of the transmission coefficient. We fix the operation frequency at 100 gigahertz, so this is what we have highlighted here. And you can see that as we vary the diameter, we have this variation of the transmission coefficient, and the same for the phase. So we need to have 2 particles where we have at least a phase difference of 30 degrees, and with significant magnitude of the transmission coefficient. So we select these 2 particles with diameter 0.36 and 0.4, and you can see that they cross exactly at 100 gigas. This is a very good point to cross because both have the same magnitude and with very significant transmission around 0.95, around 0.90. So the phase difference you can see here is more than 30 degrees, is around 40 degrees. So these are very interesting candidates for our lens. And we also obtain the refractive index. Of course, this doesn't have much physical meaning because the refractive index of a single layer is difficult to see what it represents. In any case, it's good for us to have this number because it allows us to do simple calculations, always keeping in mind that probably this doesn't have a very much physical meaning in any case. So now what we do is to apply this optimization algorithm, the binary particle swarm optimization algorithm, with which we have modified a bit. Let me explain this in some detail. This is the mask that we are going to use. We want to have this focus at the focal length of 28 millimeters, all right? So you see that we impose a very, very narrow focus for the algorithm to converge. And we do our calculations by simply applying this this calculation. This is the field that we obtain by applying the transmission coefficient, magnitude, and phase, and we are going to use only the values that we obtained for the selected cells that I showed before. The transmission coefficient, magnitude, and phase only will be of those of the previous slide. And we calculate this by applying the Huygens-Fresnel method. So in principle, these are analytical calculations which are approximately correct. Of course, a simulation will be more accurate, but for this stage, it's enough to have this accuracy. So we first have an initial phase of the optimization algorithm where the main aim is to obtain a focus. Okay, and this is here below. You can see this representation, which means that with this, when we are seeing these squares in below, it means that we have particle type 1, and this is particle type 2, then 1 again, 2, and so on and so forth. You can see this is the distribution of particles, of the cell particles that we have. And with this, we obtain this clear focus. But now if we see this is the cut along this direction, we see that this is the focus, but with high side lobes. Now, next stage is let's try to reduce these side lobes. And then we apply an additional optimization iteration, and we obtain this new design where here we have particles of type 1, type 2, 1, 2, and so on. And now the focus is still there, but with very much reduced side lobes. In these initial calculations, our full width half maximum is of only 0.44 wavelengths, and this is a very satisfying result. So now it comes to implementation, and here you can see more clearly what I said before. Here we have particles type 1 and type 2, and you can see the central zone of the lens. These are particles of type 1 and then type 2, and then we'll have type 1 again, and so on. And this is the global solution with 1 and 2, which means the type of particle that we have. So with this, we launch a simulation, and we obtain this field distribution with this focus here. This lens is a cylindrical lens. This means that the focus is not a point, it's a line, okay? So what I mean is that this lens is infinitely replicated in the vertical direction. So the focus is not a point, it's a line that goes out of the paper, okay? In any case, in this simulation, we can also obtain the field distribution along this cut, and you can see that the full width half maximum now is a bit larger. It's around 0.52 wavelengths. This is quite normal. This usually happens because the Huygens-Fresnel method is not so much accurate, and then there are some points that are only covered by the simulation. This is probably a more realistic value compared with the previous one. Okay, and here are some more results now. We go from the cylindrical lens to the let's say spherical lens. When I say spherical, is that I mean that we have revolution symmetry, so that now we'll have a focus, point focus, as you can see here. We simulate this, and then this is what we obtain. Let me call your attention here. We have used a homogenized model, so we don't have the cells. We have some equivalent media that are doing the same trick. So here, because just for memory constraints, we couldn't simulate with the metamaterial particles. Anyway, here are some more clear results. This is the H-plane distribution, XZ axis, clear focus here. For the same for the E-plane, and the XY plane. This is the transversal plane at the focal position. With these results, we obtain this full width half maximum around 0.5, 0.6 wavelengths, and here is the distribution of the power along the focal axis of the lens. And it's clear that near the lens there is a low amplitude of the power, and when we go to the focus, where we are near the focus, we get this clear enhancement of the power. So these are very reassuring results. Now we wanted to implement this for experimental purposes. So the problem with this, the previous unit cell is that it was square. So it's very difficult to cover annular rings with this square unit cell. Sorry, I hear something in the background. Somebody has mute the microphone. Anyway, also thank you very much. So
can you?
yeah, it's okay, no problem. So what I said, it's very difficult to cover some circular shape with a square unit cell. So it's probably a better shape is to use hexagonal unit cells so that we can more closely follow the circular shape. And this is what we do here. We implement this hexagonal shape. Now, as we are approaching to fabrication, we want to put this to the limit. So we increase the operation frequency now to 327 gigahertz. So it's mainly the limit between millimeter waves and terahertz waves. Now we put the focal length at 10 wavelengths. And in order to obtain our two different particles, we just play with this parameter here, the distance between the hexagon edge and the slot, the hexagonal slot edge, which is here, what we call alpha, okay? And when we sweep this alpha, we obtain the transmission coefficient, magnitude and phase, function of alpha and frequency, and we have these maps, and we keep our criterion of having a phase difference of around 30 degrees and the highest possible transmission magnitude. So in this case, it's a bit more difficult because we have less degrees of freedom. We choose these values, alpha 1, 60 microns, alpha 2, 20 microns. Now the transmission coefficient magnitude is around 0.8 with a phase difference near 30 degrees, 28.8 degrees. So this is what we are going to implement. And here I show more clearly the algorithm. I'll go fast because I have explained right now in the previous slides. So this is, for instance, an initial solution that we have with a random distribution of the unit cells. Then we apply the first stage and we obtain the focus optimization with a clear focus, but also very high side lobes. Then we apply the next stage where we reduce the side lobes, and then at the same time we keep the focus. And this is what we consider the final solution, very satisfying. Here we compare the analytical and simulation results. This is H-plane, E-plane, and XY plane. You can see, of course, the analytical results are better, we can say, but this is more realistic. This is more accurate, more comparable with the experiment. And so you see that the focus is a bit wider in the simulation results. So now here we compare in this table what we have, and you can see that the full width half maximum is quite similar. The enhancement, which is the power that we have with the lens compared with the power that we have without the lens at the focus, is around 18 for the simulation, for the analytical results, sorry, and 16 for the simulation results. So it's a good enhancement. And ellipticity, which is how circular the focus is, in the case of the analytical results is perfectly circular. In the case of the simulation is a bit elliptical, and with this depth of focus. So in principle, it seems that things are working quite well because we have very high transmission efficiency with this enhancement, and at the same time we have this super resolution. So this is what moved us to do this experiment. This is the fabricated lens with all these zones that you can see here. We performed this experiment from 260 to 350 gigahertz with a frequency step of 1 gigahertz, and we scan the power at the axis of the lens from 6 to 14 millimeters with this step of 0.5 millimeters. And at each position, we raster scan the XY plane in an area of 5 times 5 square millimeters with a resolution of 0.2 millimeters. So this is a huge experiment. We need here, there are many points, but we want to confirm that the focus is there, and that we have super resolution. This is the reason that we need such a small step here and here in this for the Z and XY dimensions. Of course, we cover everything with absorbing material in order to avoid reflections, and we illuminate the lens with a horn antenna, and we collect the power with a probe that gives us the field at each point, magnitude and phase, so that we can then we can reconstruct and take some maps in order to find if we have a focus or not. So let me show you the results. Here we have the map where we represent the transmission coefficient magnitude as a function of the frequency and also the position in the lens axis. These are analytical results. These are the experimental results. So first thing that we observe is that the tendency is very similar in both cases, but there is a clear frequency shift between the analytical and experimental results. In the experiment, the focus, the maximum is at 295 gigahertz, and in the simulation is 327. So this is some significant frequency shift. But the good news is that the focal length, in terms of the wavelength, is very similar. It's around 8.9 and 9.2. So it seems that probably there are some fabrication deviations, or maybe the dielectric is not as thick as we thought, or has changed the permittivity. Something has happened that has caused this frequency shift. In any case, if we analyze now the experiments, we can first obtain the enhancement, the power enhancement. So what we are doing here is to obtain the maximum at each frequency position. And here, this is the curve that we obtain. The maximum happens at the experimental frequency, and it's around 18 dBs, very high power enhancement. It's even larger than 18 dBs. And now, in order to check if we have super resolution or not, we have to compare with the diffraction limit. So this is the analytical diffraction limit that we can calculate easily. And then we obtain the full width half maximum in our lens, but we have to be very careful because not always the focus is going to be circular. So we have to obtain the full width half maximum at different directions, more than the ones that you see here. There are more cuts in the up to around 30 degrees. So we have more cuts than those you can see here. And we obtain then an average of the full width half maximum. And this is what we have represented here. It's very clear that we are always below the diffraction limit. So in principle, we have a huge fractional bandwidth of 18%, where the resolution is below the diffraction limit. It goes from 275 to 330. So this is a very, very good result for our lens. Now, if we represent more results, this is the H-plane, E-plane, and XY planes, analytical, simulation, and experimental results. Here, of course, you can see there's a good agreement in general between all the results. And when we go to compare the full width half maximum, then I will show you a table, but it's clear that we have, in all cases, super resolution. Now, here on the right, it's a quite interesting result. What happens at the operation frequency as we move away from the lens? So let me explain this in a bit more detail. If we are at 6 millimeters, for instance, we have very good resolution. The full width half maximum is much below the diffraction limit. But at the same time, the enhancement is very low. It's even negative in decibel scale. So this means that we have a very narrow focus, but with very small power. As you can see here, the focus is very tiny. It's very small. It's around here. And it's surrounded by a high side lobes around. So this is very good resolution, very small power. Now, when we increase the distance, then the full width half maximum increases, and eventually we are above the resolution limit. So no good at all. But the interesting thing is that this frequency, there is a valley where we are below the resolution limit, and at the same time we have the maximum enhancement. And this is this point here, the focus that we have considered in our lens. This is an excellent point because we have super resolution with a very high enhancement, with a very good transmission efficiency. Now, of course, we could do better for the resolution. We could go to this point. So full width have maximum is minimum, but also the power enhancement is a minimum, and so on and so forth. So it's a matter of what you want. If you want very good resolution, you have low power enhancement. If you want high power enhancement, then you can work with less resolution, but still have be below the resolution limit. And here are some pictures of the experimental focus that we have obtained. Let me show the next slide because there is an animation where you can see more clearly how it evolves. This is the point that we have considered as the focus. And then as we move, of course, you have more resolution in some cases, but with smaller power. So I think this is very, very clear and very didactic in order to see how it evolves. So finally, to finish with this lens, here is a comparison between numerical, simulated, and measured results. You can see mostly, I'm mostly interested in the power enhancement, around 18 dBs, and at the same time also the resolution. Of course, the resolution, the worst case is for the experimental results, but in any case, we are always below the resolution limit, and this is probably the best result. And also, I don't want to forget about the side load level, which is minus 13 dBs in the experiment. So we have complied with our two main objectives here, which was increasing the enhancement, increasing the efficiency, and reducing the side lobes. So this is something that is right now under review, and I hope that we have news in the near future about this. So how is my time? Well, I still have time. Okay, so I'm going to move now to the other lens I want to present here. This is the bilayer millimeter wave metal lens based on Patcharan Berry and geometrical phase concepts. So let me explain this in short, in a few words. What's this Patcharan Berry or geometrical phase concept? Well, it's something, I'm going to simplify everything here. Let's suppose that we have a half-wave plate, which is an optical device where the retardation between axes is of around 100, exactly 180 degrees. So we have this situation with linear polarization and we put a half-wave plate in the middle, then we will have this rotation of the polarization. It becomes orthogonal to the previous one. The interesting thing is that if we use circular polarization instead of linear polarization, the half-wave plate rotates the handedness of the polarization. For instance, in this case, this is the input, and at the output we have the opposite handedness in the circular polarization. So this alone is something which is just a half-wave plate and nothing else. The interesting thing is that Patcharan and Manberry found independently that if you have a half-wave plate and you rotate it by an angle, like for instance this one, then and if you excite this with a circular polarization, then at the output, the cross-polar component, the one that you have at the output, acquires a phase which is equal to 2 times the rotation angle. Okay, this is just a geometrical phase. This is why sometimes the Patcharan and Berry phase is also called geometrical phase. And this is only due to this combination of polarization conversion and rotation of the half-wave plate. This is quite interesting because it allows us to synthesize devices where we can have point control of the phase by simply introducing this rotation. And this has been exploited in the past in excellent works mainly by the group of Professor Capasso. You can see here these elements are half-wave plates, and they introduce this rotation in order to have this, for instance, this focusing in this lens, or they can even combine 2 different elements in order to have independent control on the right-handed circular polarization and left-handed circular polarization. So they have 2 different foci depending on the polarization at the input, and they can discriminate the response of some elements like this Scarabat depending on the right-handed circular polarization or left-handed circular polarization, and also lenses operating in the visible, covering from red to blue with these devices that are also based on these rotations. Of course, there are also examples working at microwaves, mainly done by the group of Professor Su. Here are some examples of optical vortex. In their design, they use 3 layers. This is important because we are going to reduce the number of layers. They did also this in the terahertz range, again with 3 layers. And here is an example of some blends using this topology here. Our aim now is to reduce this to the limit because, of course, 3 layers is excellent. It's a very good, and the results are very good. The question is that for layers probably is a bit more difficult to align than having only 2 layers, where you can use a single dielectric slab and then print by photolithography, for instance, the metallic elements in both layers of this dielectric slab. So this is our proposal. We are going to use a bilayer metasurface made of H-shaped elements, and the operation frequency will be at 87 gigahertz, so we can cover the millimeter wave band. Now, if we excite this structure, this unit cell with circular polarization, then we have this situation here. The input, we have left-handed circular polarization, and you can see that at the output, we have right-handed circular polarization, mainly with this curve here. And the rest of parameters, reflection and transmission, are quite low. Now, if we compute what we call the cross-polar discrimination parameter, which is simply the relation between the right-handed circular polarization at the output and the left-handed circular polarization at the output, this gives us an idea of the purity of the polarization. We find this curve here, where there is a peak around the operation frequency, which is around 15 dB. This means that at the output we have 15 more dBs for the right-handed polarization than for the left-handed polarization. And at the same time, we have good matching. This means that the reflection is not very high. So if we want to understand a bit what's going on there, we can analyze this with the linear polarization. And we find that for the vertical polarization, we have resonance exactly at the operation frequency. This resonance is going to create first a unit magnitude or very high magnitude at the transmission coefficient, and at the same time a very fast phase change, which will be critical for us in order to have 180 degrees of phase difference, and you can see here in the black curve. For the X or horizontal transmission, well, there was a resonance here, and here we are at this second point where we have high transmission, but it's not due to the resonance, so the phase difference, the phase excursion is not going to be abrupt. So in principle, we have high transmission for both X and Y, and a phase difference of 180 degrees. Now, analyzing this in a bit more detail, for the vertical polarization, there are like 2 dipoles. For the horizontal polarization, a single dipole due to this part here. And this is the coupling. I'm not going to go into details. The coupling between layers is critical. We see that for the vertical polarization, there is magnetic coupling, and for horizontal polarization, there is electric coupling. And we have identified the modes that are responsible for this coupling. In any case, I'm not going to explain this in more detail because I guess I don't have a lot of time right now. So just trust my word, this is magnetic coupling and this is horizontal coupling, and it's important in order to have the half-wave plate performance that we are looking for. So now we apply this geometrical phase concept, and then you can see here that for this geometrical phase at the output and the rotational angle that we need. Of course, in the ideal situation, in the theoretical one, this is not correct, the legend here. The theoretical one should be the blue curve that we have here, and the simulation, the initial simulation, is this purple curve that we have here, and there is some deviation, of course, because of the coupling between particles in the same layer. Probably we have this deviation, so we have to correct, because we want to have a very good phase correspondence for our devices. So this is the corrected phase that we implement at the output by changing the rotation a bit of the elements. So if we do that, then what we want to do is to design a lens. So this is the classical approach. In order to have a focus able and then have a plane wave in the normal direction of the lens, this is what we have to apply. This is the path length difference. This is this part here that we have. And the lens, in order to correct this path length difference, must have a phase at each position of the lens. If we take this as a reference, then we should have this phase as a function of the position. So just doing the calculations, this phase can be easily calculated with this equation here. And then if we generalize this to 2 dimensions, we have this equation here, which depends obviously of the focal length and also of the operation frequency. So this is the profile that we obtain. This is the phase profile for the theoretical case. And we have overlapped here the obtained phase shift that we have with this phase correction. And you can see that there is a very good agreement. So in principle, things will work well. So this is the implementation with the rotations. And this is what we have analyzed in the simulator. And here are the results. For this case in the XZ plane, we have this focus, which is near the theoretical focal length. There is a bit of a shift, but not so important. And this is the same for the YZ plane. And this is the focus in the transversal plane. You can see it's quite circular, quite well defined. Now, the full we have maximum is 0.0 lambdas. In this case, we are not looking for super resolution, and we don't obtain super resolution. And the important thing is that the ellipticity is equal to 1, and we have very low lateral lobes. So now this is an ongoing work. In fact, we received the lens yesterday, and we are measuring it right now. This is some pictures of the prototype, which are being measured at this exact moment in the university. So this leads me directly to the conclusions. I'll be very brief here. I can say that we can obtain novel lenses operating at millimeter waves and terahertz waves using metasurfaces. And I have presented here a super oscillatory lens and a patch-around and very geometrical phase lens. In this case, our main aim was super resolution as well as good transmission enhancement. In this case, we wanted to prove that we can do this with only 2 layers. And the important, interesting thing here is that we can have a clear focus with very simple rotation of the elements and for the circular polarization, which is not so conventional. So this leads me directly to the end. Thank you very much for your attention, and I will be glad to answer any questions you might have.
Thank you very much, Professor Berruete, for your very interesting talk. I think there is a question, or so please.
Okay, I have, Professor Gianluigi, if you can check I think the Q&A section above, there is one question.
Well, I think that there is a question. I don't know very well.
I'm reading it. I'm reading it. Don't worry.
Okay.
So,
okay.
The discussion is open. Are there questions?
Yeah. So I'm going to read it. The question is made by Adel Kapoor Abraray, and he asked, what do you think about using this meta lens in wireless communications to focus the signal towards a particular user, specifically the lenses that have multiple focus or focal points? Oh, excellent question, and difficult to answer. In principle, probably the super oscillatory lens is not able to do that because usually the efficiency of the focus is small, and our main aim here has been just increasing this efficiency. Now, doing more complicated things like having multiple focus, that will be detrimental for the lens, because in principle it will decrease the amplitude of the focus, and the difficulties would be much higher. For the other design, the geometrical phase lens, this can be done indeed, and it's not so difficult. It's just a matter of defining which should the geometrical phase, the phase distribution on your lens, in order to have two different foci, and that can be done. Yeah. The question is if we want to have dynamic control on that, then we should have active materials, like, for instance, you can think of liquid crystals or varactors or other technologies. The problem in that case is technological: how to feed the varactors, how to polarize the liquid crystal, and how to avoid loss, which is always a concern in these frequencies. So in principle, theoretically, it can be done, but the technological challenge is high. So this is my answer.
Okay. Thank you for this presentation, Professor Miguel. I have one question.
Yeah.
In the unit cells that you have used in the last design, so you
Yeah.
have used, I think, circular, polygonal, and H side. And I know that you are famous with whole arrays. So is there any reason why you changed from whole array to these shapes?
Oh, well, you mean in the past? I was using whole arrays. Yeah. The question is that whole arrays are quite limited in their capabilities, in the potential. In principle, if you are going to work with metasurfaces, which usually have a single or by 2 layers or 3 at most, in principle, whole arrays don't give us as much freedom as we want, because of course, if you operate beyond extraordinary transmission, then you have a bit more freedom. But extraordinary transmission, which is what we employed in the previous lenses that we developed, has very stringent conditions on the periodicity. And you can change that. It's just the periodicity that you have to respect is around 1 wavelength. So if we want to put things together, close together, below 1 wavelength, then we have to think of other things. And these shapes gives us the freedom that we need. Now, here we think more of the dipolar resonance equivalence than of the, a collective effect, like the extraordinary transmission, which implies all holes working together. Here, what we do is to design each unit cell independently, and then we assume that when we put all of them together, the performance is similar. But the approach is completely different in this sense.
Okay. Another question is that we can use those meta surfaces for sensing applications. So do you have some ideas?
Yeah.
About
sensing.
About sensing.
Yeah. Well, in fact, we've done that, and I have other presentations. I had doubts about including it also here, but I found that the presentation was long enough, so I didn't include. But yes, indeed, in the past we have published some interesting works, in my opinion, regarding sensing terahertz. Indeed, I think that in the things that you shouldn't see, I think I have some ideas. This is what here it is. It was in the back slides. These are the structures that we have used for sensing purposes. I'm not going to explain because I don't have time, but yes, the short answer, yes, it can be used for sensing purposes.
Okay, thank you so much, Miguel.
Thank you very much.
Okay, are there other questions? I have one, is more a technological question. To what extent can you repeat the production of such lenses. I mean, the super oscillatory lens, for example. What is the accuracy, and how many experiments did you carry out to get your results?
Excellent question. Excellent question. So about the repeatability, we have more prototypes at our lab, but the question is that we didn't have the time to measure them. But in principle, just looking the lenses at the microscope, the fabrication seems quite repeatable. But of course, we should be cautious with this because the eye is not able to see what happens later when you experimentally analyze the lens. So in principle, for the super oscillatory lens, this is critical, and probably I expect more deviations if we analyze more prototypes. In fact, in this case, we had significant frequency shift compared to the simulation. So this gives us an idea about the problems in fabrication. Regarding this one, I don't expect so much deviation because the operation frequency is below that, and we are in a safe range for the photolithography that we are using. So for this prototype, we have 3 different samples, and all of them look well. Now, regarding the experiments, the number of experiments, I can tell you that this, in order to measure this lens, it took more than, I think it was 1 week and a half, around 10 days of measuring, because the step was very small and we had to get many points. And we had to repeat these measurements. And the good news is that the experiments were quite solid. When we repeated the experiments, mounting everything again and so on, the results were very similar. So in this sense, we are quite sure that it's working quite well. Regarding the other one, I don't know, because we are doing the experiment right now. At this exact moment, they are measuring this. In this case, probably the main problem will be the circular polarization, because we have to compose the circular polarization from linear polarizations. And that's always a problem, because there can be some small errors in the phase that when you add them together, imply a significant deviation. But we will see. I don't know yet.
Okay, thank you very much.
Thank you.
It seems there is another question. No, just a thank you from Abdelgafur Abrarai. So if there are no more questions, thank you again for your very interesting talk.
Okay, thank you very much. Thank you very much.
Miguel.
Thanks. Great.
Okay.
Now we will move to another session. Okay, I think titled by Professor Typhoon. Good morning,
Hello.
Typhoon. Hello, how are you?
Hi, I'm good. How's it
Okay,
going?
I think,
Everything okay?
Yeah.
Good. So the next presentation, let me take a look, will be given by Professor Bilotti. Is he here?
Yeah, it's there.
Yes, yes, here I am.
Oh, hi, how are you?
Hi, very good. How are you?
So,
Good to see you.
Professor Bilotti, nice to meet you. I mean, Professor Bilotti has a long biography, but very briefly, I would like to say a few words about him, then leave the floor to Professor Bilotti. He completed his undergraduate and PhD degrees at Roma TRE University in 2002. He completed his PhD, and he worked at the same university until 2012 as a faculty member. Then in 2014, he became a full professor, and in 2012, he became the director of Antennas and Metamaterials Research Laboratory. And he's still, I think he's still the director of this laboratory. His main research contributions are in the analysis and design of microwave antennas, arrays, analytical modeling of artificial electromagnetic materials, metamaterials, metasurfaces, and including their applications for both microwave and optical frequencies. So that's a brief introduction for Professor Bilotti. So I think you can start your presentation now, if you don't have anything to add on what I just said.
Okay, thank you very much for the very kind introduction. I'm sharing the screen right now. So can you see it, please?
Yes, yes, we can see it.
Okay, that's fantastic. I try to skip this. Okay, so everything should work now. Okay, so thank you very much for the kind invitation to give this talk today at the MMS'20. The talk is about intelligent metasurfaces and their application in future wireless systems. So basically, this is the outline of the presentation I'll give you. First, I will briefly review the concept of metamaterials and metasurfaces. Then I will talk more about the challenges we will have in future communication systems. And I will show you what are the key performance indicators there and how these challenges are actually relevant. Therefore, I will show you that there will be need for a paradigm change, and the role of electromagnetic people and people working in metamaterials will be very important. And in fact, I have focused my presentation on the concept of metasurfaces and their applications. And I will show you that by increasing complexity of such metasurfaces, we can actually broaden the functionalities, and we can also extend the range of applications, including the ones in future wireless system. And in fact, what I call the third generation of metasurfaces is a very promising key enabling technology for future wireless systems. And finally, I will draw the conclusions of my talk. So let's start with the concept of metamaterials and metasurfaces. So I would like to put it in a kind of historical perspective, showing the process of investigations which led eventually to metamaterials. Metamaterials can be considered the final stage of this process, but at the same time, it is the starting stage for many new relevant routes in nowadays worldwide research. So in the 19th century, basically, the investigation were mainly oriented to find the properties of natural materials, and mainly studying or exploring the interaction between the electromagnetic field at visible frequencies and such natural materials. Why this happened in the optical frequency range, simply because due to the dimensions of atoms and molecules and due to their separation, the relevant interaction with the electromagnetic field happens at those frequencies. There we have discovered so many interesting properties. Then we wanted then to apply also to other fields, like for instance radar systems, communication systems, and so on. If you think, for instance, of optical activity in quartz crystals, as well as the interesting properties of natural chiral materials, they can actually work on the polarization of the field, and so could be useful also at different frequencies. So how to get the same properties but at much lower frequencies, such as radio frequencies and microwaves? The idea was to mimic nature and to replicate the same structure we have in nature, but at a different scale. It was the era of artificial materials, starting from around the 40s of the last century. But what is really interesting in artificial materials is that actually we have here artificial atoms and artificial molecules, which are on the scale of the centimeter, for instance, and can interact with the RF and microwave frequencies. But what is more interesting is that the degrees of freedom we have in artificial materials are much more than the ones nature offers us. In fact, in nature we have the periodic table of elements, and which means that we have a fixed number of elements. And not only that, also the combination between such elements must follow certain well-defined rules, which depend mainly on what? On the physical and chemical nature and structure of the atoms. Now, when dealing with artificial materials instead, we have so many degrees of freedom. We are related to, for instance, the shape, the size, the geometry, the symmetry, the material of the individual particles, as well as the electromagnetic properties of the host material, and also the spatial arrangement parameters, the alignment of the particles, so on and so forth. So basically, in artificial materials, we can be much more flexible than what nature offers us. And therefore, around 2000, we were able to exploit all these degrees of freedom in order to get new properties in artificial materials that cannot be found in any natural material. This was the onset of metamaterials, and in particular, you remember the first investigation was about a negative index material, which is not present in nature. So metamaterials were born in electromagnetic community, working at RF and microwave frequencies. But let's talk more about the name. Metamaterials are artificial engineered materials whose properties actually go beyond what nature offers us. So this is the meaning of meta. And then what is important is also to consider their bidimensional counterpart, which are called metasurfaces, which are very useful because they are thin engineered structured surfaces, which allows for very easy implementation at any frequency. And also they are characterized by less losses than metamaterials, And so they are the most practical way to use metamaterial concepts in nowadays technology. But what is important to underline is also that metamaterials and metasurfaces, even if they were born in electromagnetics, then now represent a concept which has been extended to all the other fields of physics. So, for instance, acoustics, mechanics, thermodynamics, we have applications of metamaterials concept now ranging from quantum physics up to civil engineering, which means that we cover all the scales from the nanoscale up to the meter and kilometer scale. I would like also to say that there is a scientific international society about metamaterials, which is called Metamorphos Virtual Institute, which owns a congress series, which is called the Metamaterials Congress, which is a prime event where every year people from many different communities gather to show and discuss also the recent advancements in this field. And I was the organizer of the first edition of this Metamaterials Congress back in 2007 in Rome. And I remember there that the major part of the attendees were from microwave community. They were actually electromagnetic people and almost all engineers. But in the next years, I mean, starting from 2008 in Pamplona, then in 2009, in 2010, and so on, so forth, the program actually and the flavor of the scientific program changed because many people from physical community came, and also many people working at optical frequencies. And nowadays, if you see the scientific program of the Metamaterials Congress is actually reflects this broad range of physical communities working around the metamaterials concept. So we have many sessions in acoustical metamaterials, mechanical metamaterials, in thermodynamics, quantum physics, and so on and so forth. Another point I would like to underline is that in these 20 years of innovation in the field of metamaterials, the main research trends can be summarized to me as follows. At first, once we discovered that microwave frequencies such very interesting properties, the idea was to apply them to improve the performances of existing electromagnetic components and devices, such as antennas, absorbers, waveguides, filters, and so on. But later on, what was really interesting was that through these unique properties offered by metamaterials, we were actually inventing conceptually new electromagnetic components and devices, such as the lenses, as Miguel has shown in the previous talk, like the super lenses, the hyper lenses, but also the invisibility cloaks. They were completely new, conceptually new electromagnetic components and devices. But not only that, after a couple of years, actually, it started already the quest for getting metamaterials working in the visible. And this actually has been boosted also by the strong advancements in nanotechnologies, so that we are able to now scale down and nanostructure metamaterials to make them working in the visible. After that, the other, big trend in the research about metamaterials was, and currently is, to enable tunability and reconfigurability at both the whole material level and at the individual particle level, which could offer so not only reconfigurability and tunability, but also can make this structure ever more intelligent and can enable smartness and awareness. Now, I would like to share also this definition of metamaterials, which I call the operational definition of metamaterials. Basically, if you have a look at the technological pile, you can see that the bottom layer is made by the materials, which are rather the main support or the mere support where a device is built on. All the functionalities and all the processing on the electromagnetic signal, on the wireless signal, for instance, is left to the device. And then when we integrate more devices together, so many functionalities towards a common end, we have a system. But now, when talking about metamaterials, at first we suddenly realized that metamaterials actually is a new layer, completely new, which is across the original layer of material and device. Because on one hand, these metamaterials may represent the support where we can build some devices on, but at the same time, they already make the processing of the electromagnetic signal. So they enable already some functionalities. But not only that, with the ability we have nowadays to control the properties of the metamaterials, even at the individual particle level, then we can integrate many functionalities and many different processing of the incoming or radiated electromagnetic field in such a way that we have many functionalities integrated on the same material. So basically, the metamaterial today covers the whole layers of the technological pile, ranging from the support up to the system level, integrating many functionalities together. Another point I would like to highlight is the hierarchical organization of metamaterials and metasurfaces we can have today, where basically each individual metasurface, let's say, can be actually have a multi-scale architecture, ranging from nanometers up to centimeters. Therefore, in this way, we are able to have the same devices, the same device working for the whole electromagnetic spectrum. But not only that, we can also structure this artificial surface or material in such a way that it can interact with different wave phenomena in order to have multi-physical functionalities. Actually, this trend nowadays is posing lots of challenges, which ranges not only to the fabrication technologies, but also to the modeling and also to the numerical simulation. So multi-scale and multi-physics aspect of metamaterials. Now, having said that, let's have a look at what will be the future challenges in wireless systems and see how, if and how metamaterials and metasurfaces can help in this. So basically, as also Miguel has shown in his previous presentation, when switching from 5G to 6G communication systems, so we are talking about what is beyond 5G, actually we have striking numbers over here, like 1 terabit, up to 1 terabit per second as a peak data rate, as well as 100 microseconds in latency and 1 microsecond in jitter, which is the variation of latency. And then all these other numbers, like the density, the number of devices per square meter, the reliability, and so on, so forth. But these numbers actually are ever more striking if we compare them with the current 5G technology. So you see here, for the peak data rate, you go from 20 gigabit per second up to 1 terabit per second. You see the maximum bandwidth from 1 gigahertz to up to 100 gigahertz. And also latency is going from 1 millisecond up to 100 microseconds. Jitter is not a specification in 5G, but it will be in beyond 5G wireless system. And also reliability goes down to 10 to the minus 9. So we have several challenges to take here. And we will have massive capacity, almost zero communication latency and jitter, ultra high reliability and security, just to name a few of these challenges. Now, how to handle all these challenges? There is need for sure for a paradigm change, and I will tell you why metamaterials and metasurfaces can play a role here. So there will be need for seamless connectivity, which is not only for everybody, but also for everything. So it's the IoT. But on the other side, this would be a cloud of real-time, not only communications, but also sensing, remote actuation, tactile interaction, monitoring, and data processing. Now, how can we handle all of this by using a current 5G technology? Well, a possibility at the physical layer would be to use a huge number of access points and base stations. And at the higher level of the communication pile, we could use massive local computation to face these challenges. And this is especially true, actually, in complex indoor environments where we may think of thousands of machines, wearable devices, fixed terminals, and so on, which dynamically exchange information at a rate which is ultra high. Now, another challenge here is the use of millimeter waves, as also Miguel has mentioned in his talk. When talking about millimeter waves, they are, of course, needed. They are mandatory because of the bandwidth requirements we have. But if you just have a look at the line of sight link, then even this very simple link is very much affected by the use of the millimeter waves. Why? Because we have a very fast free space attenuation due to the millimeter scale of the wavelength, but also any object in the environment actually is a very important obstacle for the propagation of the millimeter waves. Now, by using current technologies, what kind of possibilities we have? We can rely at the physical layer on massive MIMO systems. Sure. At the higher levels, we can rely on SDN, software design networks, or MVF, network virtualized functions. But all of these technologies actually involve a dramatic increase of the computational time and on the computational resources. There is too much signaling behind. And this is a direct consequence of the virtualization of the hardware functions. In fact, basically in the previous generation of wireless systems, everything has been moved to the higher level, to the protocol level, to the algorithm level, to the higher levels of the communication pile, and is completely left from the hardware level. So now there will be a kind of revenge of the communities that usually work at the physical layer. But so let's have a clear look of this. When talking about massive MIMO, clearly massive MIMO cannot be the solution for future wireless system. And you can have a look here why. This is a very advanced front end for massive MIMO systems, is a commercial one. Is very innovative, is technologically advanced, and so on. Very, it has great electromagnetic performances. But now, let's have a look what happens when a signal is incoming over here. Then there will be need of loss of signaling behind. I have just cited here a few of the functionalities that must be needed behind, like for instance, beamforming, modulation and demodulation, data extraction, forwarding strategy, and this flow is actually going back and forth in the back end of the hardware system. Therefore, this is too much. It's simply too much time, too much resources for having 100 microseconds of latency and 1 microsecond for jitter. This is not the solution. So now, what are the critical points here? The critical points are two. One is the extreme virtualization of hardware functions, and the other one is the negative role or the bad role played by the environment due to the use of the millimeter waves. So now the challenges clearly are moving to the physical layer. So what can we do to relax these critical aspects? First, we can reduce and minimize hardware virtualization, bringing back again many functionalities from the higher levels of the pile towards the physical layer. And the other point is to play with the environment, making it contributing to the system. So the environment must not be only an obstacle, but should contribute to actively to the system. So clearly there will be room for electromagnetic people, not only for antenna designers, but also, and I would say ever more, for designers of smart electromagnetic surfaces, which are used to make the environment intelligent and actively contributing to the system. As I wrote here, assisting the wireless connectivity while being non-invasive, cognitive, low power, low complex, and secure. So clearly there is room for us there. And so let's see what kind of technology we can use in this frame. So that's why I will focus now more on metasurfaces. And in particular, with this slide over here, I summarize briefly, very briefly, I would say, 20 years of advanced research in the field. I have highlighted here the 3 generations of metasurfaces. The first one were starting again in around 2000, where we had just passive metasurfaces, which were completely periodic structures. Then the second generation of metasurfaces, where inhomogeneities actually come into play, and now the current generation of metasurfaces, the third generation, where we are able to control the properties of metasurfaces, not only in space, but also in time. And this is actually very important. I will show you why. So in the first generation of metasurfaces, we had just periodic structures, and the response to the electromagnetic field does not change in space and time. So basically, what happens here is that the individual particle size and the separation among the particles is electrically small, so that the electromagnetic field impinging on it doesn't see the granularity of the metasurface and interacts with the metasurface through the homogenized parameters, like, for instance, the surface impedance or the surface admittance. What kind of applications we have seen, for instance, in antenna systems? We have been working on cloaking devices. We have developed lenses and polarization transformers, waves and spatial filters. We have been working on high impedance surfaces and artificial magnetic conductors, just to cite a few of the applications we had of this first generation of metasurfaces. Then we can talk about the second generation of metasurfaces, which is characterized by inhomogeneous structure. And these could be, we have different families here, like quasi-periodic structures, gradient structures, holographic metasurfaces, and so on. Many groups in the work are now working in the world are now working on these inhomogeneous metasurfaces. And the surface impedance, or the homogenized properties, now are varying point by point on the surface. So the boundary condition actually changes point by point. And these kind of structures are actually very useful all the times we want to change or to get an anomalous direction of the beam, let's say of the reflected beam or the refracted beam. In reflection, for instance, if we would like to achieve a non-specular reflection direction, we can use this kind of inhomogeneous metasurfaces. And also, if we embed a source within an inhomogeneous metasurface by using so this variation of the surface impedance, for instance, we can get radiation from this kind of structure, and we can have the so-called metasurface antennas. Many groups in the world are working on this. But nowadays, we are working mainly with the third generation of metasurfaces, where we can control the properties in space and time, even at the individual particle level, even at the unit cell level. So these actually, so the control mechanisms can be different and are different at the different frequency ranges of the electromagnetic spectrum. So we can use, for instance, thermal properties of such materials, optical properties of some materials. We can use liquid crystals. We can use electronic circuit loading of these structures. So we have many ways to control the properties of the metasurfaces at the unit cell level, which of course can be used depending on the response time, or depending on the frequency range of interest, and depending on the application. Anyhow, in this way, we are able to get tunable, time-modulated, reconfigurable, and even programmable metasurfaces, as some groups in the world have proved. And I will show that this kind of metasurfaces actually can deal to a new generation of antenna systems, and at the same time can be the key enabling technology for future beyond 5G communication systems. So I would like to retrace this historical process of the 3 generations of metasurfaces just by showing some of very few examples of what we did at Roma 3 in my group about that. For instance, we have been using this first generation of metasurfaces, like just passive metasurfaces, to get cloaking devices, to hide structural elements which are in front or close to antennas or radiating elements. This is just an example of a CubeSat satellite. We have UHF antennas. This is a cross dipole mounted on, and you have some structural elements which are just sustaining sensors, which are at the very tip of this structural element that should be apart from the chassis of the CubeSat satellite. And these structural elements are changing the radiation pattern of the UHF antenna. Such it goes from this one on the left, this radiation pattern on the left, to the other one we have on the right. And you see clearly that we have some nulls appearing in the radiation pattern, which is undesired for these satellites, because they fluctuate in their orbits, and therefore they must keep the communication link with the Earth station, whatever is the angle of view. And so by putting a cloak, which is made by these periodic metasurfaces conformal around the structural elements, we can hide them to the antennas, recovering exactly the original radiation pattern, as the structural elements were not present there. But not only that, we can also cloak antennas themselves, and in particular we can cloak receiving antennas in order to have low scattering sensors. As it is well known by reciprocity theorem, in order to absorb some power, any antenna must also scatter some power. And therefore it is not possible to have a zero scattering but still absorption. But there are fundamental bounds about that, and we have demonstrated in a series of papers that by placing a conformal cover around, for instance, a dipole antenna, but this is a more general concept and is valid for any kind of antenna, around the dipole or the antenna, the sensor, we are able to approach better and better the fundamental limitation, which means that we can get the minimum scattering for a given absorption level. So we have minimally invasive sensor for which are acquiring measures without without a significant perturbation of the electromagnetic environment. But we can cloak also transmitting antennas. For instance, let's consider this case where we have a Pico base station with a 4G and 3G cellular system antennas. They are just monopoles. And you see here that the UMTS antenna is much shorter than the LT1, but they are very, very close one to the other. So the UMTS antenna is completely obstructed by the presence of the LTE, and the radiation pattern is completely destroyed because the LTE antenna is working as a reflector for the UMTS one. The opposite is not true because the LTE antenna is much taller than the UMTS one, and so almost doesn't see it. So the perturbation is very small. So if we put now a cloak, a metasurface cloak around the LTE monopole, which is working at the frequencies of the UMTS antenna doesn't see anymore the LTE antenna. And this means that we can recover the radiation pattern and also the impedance matching of the UMTS antenna as it were alone in the platform. So this actually opens the door to new co-siting strategies of very crowded platforms, like, for instance, satellite payloads or ship trees or smart cars and so on, so forth. Basically, the two antennas are working as they were alone there. But then we started loading the metasurfaces with some electronic circuit. For instance, in this case, we have a cloaking metasurface around a dipole antenna, and we load the metasurface with this diode pair. No bias is needed here. If you do that, when the two diodes are not conducting, actually, the metasurface is just a cloak. But when the two diodes are conducting, then we have a short circuit between the strips of the metasurface, and therefore what you have is that the cloak is not working anymore. It is just a kind of solid cylindrical metallic shell around the antenna, which means that the antenna is working more or less in its regular way. So we can use this, for instance, in more advanced antenna systems, like for instance this one. Imagine you have a Yagi-Uda antenna where the driven element is a regular dipole and the reflector and director are passive dipoles where we have around this kind of metasurfaces. Then when we use this system in the reception mode, then the impinging power is so small that the two diodes are not conducting. So the reflector and the director are hidden to the electromagnetic radiation, and therefore this is an omnidirectional receiving antenna at the operation frequency. But then when the central antenna is transmitting power, now the power level is much higher, and the reflector and the director of the Yagi-Uda are not covered by a cloak anymore, and it's working as a regular Yagi-Uda antenna. So basically at the same frequency, we have this low power radiation pattern, which is an omnidirectional sensor, let's say, but a high power. At the high power, we have just a directive radiation pattern as the one expected from a Yagi-Uda antenna. But we can use this concept also, for instance, in a kind of array structure where we have the central element, which is not covered by the nonlinear metasurface, and the rest of the elements are. So in this way, for high power, we can, so the array in the transmitting mode is working as a regular array. In the receiving mode, we have this low power omnidirectional radiation pattern. But we can make the circuit loading the metasurface ever more complex, like for instance in this case. Imagine we would like to have the antenna cloaked for a short pulse width, whilst the antenna is again visible when we have, for instance, a continuous wave or a larger pulse. Now, the electronic circuit we use in this case is this diode bridge, where on the arm we put a series between an inductance and the resistance. If you see the current and voltage characteristics over here, and you use this diode bridge to load this cloaking metasurface over here, you have that you get an open circuit between the loading points over here when the impinging pulse has a pulse width which is shorter compared to the time constant of the circuit. So the metasurface is working as a clock and the antenna is completely hidden. But when instead we have a larger pulse width compared to the time constant or even a continuous wave, then we have a short circuit over here between P1 and P2, and then we have just a kind of cylindrical metallic shell, and we have that the antenna is operating as a regular antenna and is not hidden anymore. So basically this can be used to put an antenna in front of, for instance, a pulsed radar, so that the antenna is invisible to the pulsed radar and can still work for other pulse width, larger pulse width, or even continuous wave. But then another possibility enabled by the current control we have of metasurface is, for instance, the one of getting a time modulation of the properties or of the surface reactance of metasurfaces. For instance, here in this case, we have loaded the metasurface in order to get a proper surface, a proper time modulation of the surface admittance. And then we have a reflector baking the structure. It's just a regular flat metallic structure. And then what is going to happen here is that impinging with an electromagnetic field, the time modulation here, when the time modulation is on, we can use the virtual absorption concept, and we can heat a complex mode within this cavity, which is actually, we assume that the structure is lossless. So basically, we don't have absorption, but also we don't have any scattering from this kind of cavity. And therefore, this can be used to implement a free space battery with unbound energy accumulation. As soon as the time modulation is off, then all the energy within the cavity will be released back to the free space. And this is another very important functionality we can use to enable self-powering of antennas. Another concept we have put forward by using time modulated metasurfaces is the one of the Doppler cloak. The Doppler cloak is a cloak which hides the velocity and can be used for antennas which are mounted on, for instance, fast vehicles or very fast trains. There, even if the Doppler shift is very small, even at such high speed, then in communication systems which are based on multi-carriers, like for instance FDM, this fast speed would cause a Doppler shift, which eventually would cause a intersymbolic interference. And this is actually bad because in real life you have it and you have to compensate this at the higher level by using proper protocols and algorithms. But you can do it at the physical layer by using the idea of the Doppler cloak. We have demonstrated also as you can read in this paper. Basically, by a proper time modulation of the metasurface, we can have that the metasurface is working, and so the antenna, which is at the center of this metasurface, which is surrounding the antenna, basically is working as they were at rest, so not moving at all. And so basically we kill the Doppler shift, and in fact we have called it also Doppler cloak or velocity cloak. So we make the antenna radiating as it were at rest, even if it is mounted on a fast train. But now, having said that, let's see how we can use this third generation of metasurfaces in future communication system. I will propose here a couple of concepts. One is the smart antennas 2.0, which means a new generation of intelligent antennas. We have I'm leading a quite large project in Italy, which is called Mantles, about this, where also other universities and Professor Oliveri and Professor Monti are also involved in this, where basically the idea is the following. Let's consider the usual antenna we have seen in the previous example, and also the usual conformal metasurface around it, which is now not used as a cloak, but rather is it is controlled actually at the individual cell, at the unit cell level. Having done that, we can make this metasurface working not only as a cloak, but also as a polarizer, as an inhomogeneous metasurface getting a given radiation pattern for the antenna, and so on and so forth. So basically, the idea is to have a new generation of intelligent and cognitive antennas, which actually scan the electromagnetic environment and adjust their operation accordingly. Like, for instance, self-tuning of the operation frequency, having scanned for all the possible interferences, or adjusting the polarization properties according to the polarization properties of the metasurface, adjusting the radiation pattern, set the visibility or invisibility mode, and so on and so forth. So in this way, the intelligence is of these new antennas is not given by the higher level of the communication pile, but is given at the physical layer. And we are showing in this project that by increasing the complexity, going from passive, nonlinear, tunable, reconfigurable, programmable, time modulated, and cognitive metasurface, we can actually broaden or enable new functionalities, and thus broaden the field of application. The other possibility for the third generation of metasurface in future communication systems or wireless systems, let's say, is in the role I mentioned, the bad role played by the environment. So any obstacle like walls, doors, windows, external surface of any object must evolve from a mere obstacle to a smart electromagnetic relay node. And we are working on this together with Professor Maci, and with the idea of smart skin antennas and also smart skin walls, which are able to working as a relay node for millimeter waves. Then I share with you this other example, the line of sight issue I mentioned before about millimeter waves. Let's imagine we have here an access point, and here we have a fixed terminal. So in this millimeter wave scenario, you cannot use or rely on the multipath as you do in sub-6 communication, sub-6 gigahertz communications. And so the idea would be to use these smart surfaces over here, for instance, on the floor, integrated on the floor of these, which are actually getting the incoming signal and reconfiguring itself in order to re-establish the line of sight communication link between the access point and the fixed terminal. So with the ability we have now to control the properties at the individual level, the other functionalities of smart electromagnetic surfaces would be in electromagnetic forwarding and routing, which this time happens at the speed of light, and this actually dramatically improves the system performances. Of course, there will be need for a computation as well, but this is a local computation, a local computation at the metasurface module as well. It is not a kind of tons of processing or signaling behind the regular surfaces we have now nowadays. And this actually would extend also the concept that MetaWave, this company, has put forward for 5G, dealing with these smart, let's say, screens, which actually mechanically rotate in order to enable anomalous reflection. But still, if we are able to control the individual particle, we do not need anymore this mechanical rotation of the structure. So basically, smart electromagnetic surfaces equipped with a local control and the local low computation module, as said before, can enable a number of functionalities, such as sensing the environment, for instance, estimating the direction of arrival, positioning awareness, which is very important to know where in the environment our node is in its absolute position and in its relative position. And also is very important to get adaptive connectivity. For instance, restoration of the line of sight as mentioned, or overcoming localized coverage holes, and so on and so forth. I just closed this, so this part showing that this can be done not only by using reconfigurable metasurfaces, but can be used, but also by using reconfigurable metagratings. In metagratings, we actually enable further functionalities because so the concept of metagrating is that we have a regular diffraction grating, but the individual elements, so the unit cell, is designed by using the metamaterials rules, let's say, or properties. And therefore, by making it reconfigurable, you would enable further more dynamic control of the direction of both the reflected and the refracted beams. So some examples have just appeared in this paper by our group on the IEEE transactions on antennas and propagation. This brings me to the conclusions. I would say that metamaterials and metasurfaces are already making a revolution in the field of applied electromagnetics, but what is more important to me is that with the ability we have nowadays to control their properties in time and space, we are actually opening the door to play a very important role in the design of future wireless systems. And I have shown you how and why the third generation of metasurfaces can be a key enabling technology for future communication systems. I would say that today there are already several projects at both European and national levels in which people from communication society and the electromagnetic community are working together towards this end of enabling the 6G and this for taking all these challenges I've mentioned at the beginning of my presentation. Before concluding, I just acknowledge the work done by the whole group, which is sketched here. And that's all. Thank you very much for listening.
Okay, Professor Bilotti, thank you very much for the very interesting and very informative presentation. I mean, I personally learned a lot about the huge spectrum of applications that metamaterials can actually lead to in the future. I would like to ask to the audience if they have any question. They can talk, they can send messages. Are there any questions? Okay, I personally found the tunable, frequency tunable metamaterial applications quite interesting and as a huge potential to develop, future communication systems. In these frequency tunable metamaterials, whether antenna or filter or whatever they are, we still are limited with the performance of semiconductor materials, semiconductor circuit elements like varactors, switches, regarding whatever the technology you may use, barium, strontium, titanate, gallium arsenide, whatever. But at the end of the day, these frequency tunable components are going to bring some limitations because they have some kind of non-linearities, some distortions they are going to generate. How do you see the limitations that will be brought by the semiconductor components can be reduced, maybe still possibly, by using some special designs? Is it possible to reduce the degrading negative effects of the semiconductor materials by still using this kind of metamaterial approach?
Okay, thank you very much. This is a very, very interesting question. Actually, answer here is rather difficult because so these are current limitations, but are related to technology. What I want to say is that what is important here is to make a careful co-simulation of the electromagnetic part and the electronic circuit. Yeah. So basically, what we do is to combine the electronic solver and the electromagnetic solver, and in this way we are able at least to consider all the aspects you have mentioned, and this is the first step. So to properly consider this, because in some cases, if you read some papers around. So this is completely overlooked. So just people say that they can change the varactor considering the data sheet from a given value to another value. But so then we have the nonlinearities, as you mentioned, and all of these parasitic effects. And this at first must be considered. So once you have the simulation ready for considering all these aspects, then you can work on that to make this so less affecting the overall performances. In our cases, actually, we are using quite established, let's say, structures and techniques and even active elements. So we are working around the X band. So basically, we don't have so many issues. But for sure, when you will go towards real millimeter waves, then so you will have to find something which is different from semiconductor. So maybe NEMS, MEMS.
MEMS,
so
maybe.
Yeah. So it could be a good solution for that.
Yeah.
So I hope I have answered your.
I think there is a question in the messages. Are RF processing techniques needed for this type of electromagnetic surface? Abdul Ghaffur Ray is asking. Thank you for interesting presentation. Are RF processing techniques needed for this type of electromagnetic surface? He is asking.
I'm not sure to have quite understood this question. So you are talking about RF processing techniques.
Manufacturing, or what is it?
So it's fabrication, because if it is related to fabrication, we use regular PCB fabrication facilities to get this structure. And then we have some, let's say, pick and place machines for picking the electronic circuit and place it. It's SMD, regular SMD RF components that can be soldered in the place you like by using this pick and place. So it's quite standard. As to the conformal part, then we use flexible substrate, and so it's becoming a standard technique. It's not so strange, let's say.
Okay. Any other questions? Right. Okay, Professor Bilotti, thanks a lot. I think it's time to close the session. I think it's lunchtime anyway, so there's a lunch break now. So thank you again. Thanks a lot for the informative presentation. Have a nice day.
Thank you very much to you all, to the organizers, for having invited me. It was a pleasure. Thank you. Bye.
Thank you, Professor Bilotti.
Thank you, Othman.
Thank you. Bye. Bye, Othman. Bye.
It's wonderful moments with you. Okay, now let's have a small break, and then we will come back with the other presentation. Thank you all of us.
أهلا وسهلا. صباح شو أمورك؟ طلبت البارحة؟ والله ليش بطلب؟
morning, Professor Osman. How are you doing?
Good morning. How are you?
Fine.
How are you?
Good.
Nice to meet you.
Nice to meet you too.
Thank you very much for the invitation.
We are waiting for Professor Francisco Falconi to join us.
Okay.
So we need to wait some minutes. Okay. We have,
No problem. No problem.
Okay.
Thank you very much.
You're welcome. And also we are waiting for Brisbane Haddo.
Okay. Okay. No problem.
Good afternoon.
Good afternoon.
Good afternoon, Professor Francisco. How are you?
Odman.
¿Qué tal?
Salam alaikum.
Alaikum salam. How are you doing, my friend?
I'm good. How about you? How's everything going?
Yes, we are fine. Okay, so just COVID situation.
Okay.
Yeah.
Good. Can you hear me well?
Yeah, I can hear you. Yeah.
Okay. Good.
Everything is okay?
Yeah, I just had lectures now. I finished at 2. So, eating fast and yeah, presentation, then a meeting, then,
Oh, yeah, I know. You are always busy. Okay.
No, well,
Yeah.
as you.
Okay. So you, as Miguel told me that you are teaching in presence or remotely?
What? Excuse me?
Teaching is in presence or remotely?
No, in presence.
In
No.
presence. Okay.
Yeah. So, but you see, what happens is that university has opted to give everything in presence.
Okay.
But of course, there are students that are not here. So we have to give classes at the same time on location and by Zoom. So that's the way we do it.
Okay, so it's fine.
Oh, it's fun. But
yeah, it's a lot of work. Okay.
Oh yeah, it's a lot of work. Yeah.
Yeah, because the giving classes remotely is different than in presence. Okay, so we need to.
Oh yeah, for sure.
Dedicate a lot of time to your slides, your speech. Okay.
Oh yeah. Look, what about you? Are you giving classes locally or are you doing them remotely?
No, remotely. Okay, in Morocco, I think some universities choose with reduced number of students. Okay, to give some classes in presence, but in our university we choose to do it all remotely. Okay, so in order to avoid the risk, because last month
good idea.
I think we have lost 6 professors. Okay. Because of COVID.
Really?
Yeah.
Oh, that's sad, man.
So, yeah, it's a bad situation. So we need to be careful.
Yes, of course.
Be safe. Okay, that's the problem.
Man, so
yeah,
take care.
Yeah, we should do that, all of us. Okay, to be safe and take care.
Yeah, you're right.
Because this is a special time, complicated. Okay, so.
Oh yeah.
We need to deal with this.
You're absolutely right, my friend. Okay. So how did the presentations go in the morning? Everything good?
Yeah, it's perfect. We have 3 speakers. We have Professor Tibor, and later on we have Professor Miguel, and the last one, Professor Bilotti. Okay. And now we will start by you, and then we have Nasser Shahat from JIT's NASA missions, and the last one programmed for today is given by Professor Carlos.
Nice, very nice.
Yeah.
Yeah.
And tomorrow we have some presentation for students in the context of Yarman Carlin students context. So I need to send you all the papers, okay, in order to do the reviews and to be with us for tomorrow. Yeah. We will start at 9, but the competition is programmed at 10:30.
Okay.
Okay.
So I will do my best because there's a few meetings in the middle. So don't worry. I'll send you the info.
Okay. Thank you. I don't know. Okay. We are watching Professor Ben Haddou. Okay, the chairman of this session is so okay. So, Professor Osman, if you are not busy, you can chair the session of Professor because I think we are waiting for Professor Ben Haddou and didn't show for the moment. Osman? Okay. Otherwise, I have the Fran, we can start.
Okay.
After introducing to you. Okay, just give me 2 minutes. It's a honor, and I am humbled to introduce our speakers, Professor Francisco Falconi.
Professor Osman, I think Mike is there.
We are talking about Ben Haddou.
Good evening, Dr. Francisco.
Hello.
Hello.
Hello, Frank. How are you doing?
Oh.
Hello, Frank.
Yes. Hello.
Hello.
How are you?
It's fine. Thanks. It's a pleasure having you. So thank you so much for accepting the invitation and for the keynote talk you're delivering and sharing with us this afternoon.
My pleasure. So should I start? Yeah.
Okay, let's.
I think Professor Mike.
I don't know. You have moderator here.
Yeah.
So sorry, this is Mike. I don't know if you can hear me now.
Yes.
I'm not hearing anything anymore. Can you hear me?
Yes.
Oh, that's great. No, sorry, but this is really kind of tricky to get into Zoom across our company policies, I believe.
Hi, Mike. It's okay. Thank you.
So for me, it's only the test for tomorrow morning. So I'm glad that it works now. So it should be okay for tomorrow morning as well.
Okay, good.
Okay, so maybe we can start. Yeah.
Osman, I'm Mike. Osman.
In the meantime, I'm going to share my screen if you are okay with that. So I can start putting.
Okay, yeah. You can share your screen. Okay.
Okay, all right.
Okay, it's fine.
So whenever you tell me, I will start the presentation. Yeah.
Okay, just give me 1 second. Okay. So I'm humbled to introduce today our speaker, Francisco Falconi, from the University of Navarre, Spain. Professor Falconi, he's a well-known research in the field of wireless communication, metamaterials, and other applications. So from February 99 to 2000, he was a maker of commission engineering with Siemens Italtel, deploying microwave access systems. From 2000 to December 2008, he was a radio access engineer with Telefonica Mobilis, performing radio network planning and optimization tasks in mobile network deployment. As a co-founder of member in January 2009, he has been the director of the TAFCO Meta Wireless, a spin-off company from OPNA, until May 2009. He was an assistant lecturer with the Electrical and Electronic Engineering Department, OPNA, from February 2003 to May 2009. In June 2009, he became an associate professor with the Electrical Engineering Department, buying the department heat from January to 11 to July to 2018. So Professor Francisco Falconi published a lot of papers in well-known journals, has many awards. Okay, so he has a big CV. I cannot talk all about it today. So I let Professor Falconi to start his talk. So you have the floor, Falconi.
So thank you very much for your kind presentation, Otman. Well, first of all, thank you very much for the invitation. It's an honor for me to provide this presentation. Hopefully, you can see the slide. Yes?
Yes.
And the presentation correctly.
Yeah.
Okay, then. So welcome to this presentation, which is entitled Advances on W-band Integration and IoT Applications. And basically, I'm going to be discussing about some of the work that we're doing in relation with integration of body area networks and applications related with the integration of this type of systems in paradigms of smart cities and an Internet of Things. So in order to start, currently there is a trend in developing solutions related with the realm of smart cities and smart regions. And this is mainly given by the fact that it is very well studied that population is shifting towards large urban areas. And in order to make these areas sustainable and in order to enhance quality of living in these areas, it is compulsory to handle them in a more efficient way. So there has been a lot of interest in order to implement what is considered a system of systems in order to provide these services in a more efficient way. So basically, when we consider a city, we're talking about multiple type of systems that are working in order to make everything go smoothly. So we can have energy systems, and in relation with that, the control of the smart grid, smart metering, or the way in which we can handle multiple type of renewable energy sources, for example. Of course, energy efficiency is also going to be an issue. We can have the handling of water and hydric resources in order to optimize the way in which these hydric resources are employed. We can have intelligent transportation systems as well as autonomous and connected vehicles in order to improve urban route planning, multimodal transportation, and also in order to decrease transportation times and burden related with different types of contamination, such as pollution or acoustic contamination. Of course, waste management, which is also a pretty big issue. It's an everyday more relevant issue, actually. And here we're talking about compostage, and we're talking about the way in which recycling is handled, and the way in which waste classification is performed, et cetera, et cetera. Of course, we have other transverse systems, such as communication systems, which are going to play a key role in order to provide high levels of interactivity among this type of environment, and other elements, such as the way in which resource management is handled, and the way in which citizens rely and relate themselves with the administration in terms of and open government. So within this context comes also the concept of Internet of Things. And they're very, very well related, even though they develop, let's say, in parallel frameworks with different goals, but in the end, they're convergent to the same point. And actually, one of the most well-known definitions was given by Sunmaker about 10 years ago, in which it was stated that IoT is basically an implementation that will allow objects and people to be connected. And this connection is going to be very, very flexible, enabling connectivity at any time, place, with anything, and with anybody, using any type of system, path, network, or service available in order to give this communication capability. So basically, we're saying that anything can be connected, and we can use any mechanism we need in order to provide this connectivity. And this was thought out initially as a very interesting concept, but there was really no initial application, as the concept has been steadily implemented and thought out. There's quite a few application domains in which IoT can play a very relevant role, not only as providing an additional service, or let's say an added value proposition, but also becoming a fundamental element in order to be competitive. So among the different type of services that we're talking about, we have those related with healthcare, for example, which nowadays are very, very relevant in relation with pandemic control, for example. We have elements related with home and building automation. This was one of the key enablers of IoT, with all of the systems in order to control lighting and smart appliances, for example. All of the logistics related with retail and with transportation and delivery and asset management, for example. And of course, we can also employ it for multiple type of distributed systems. And of course, utilities also are here contemplated, like, for example, gas or energy or water distribution, where IoT can play a very interesting role in relation with providing telecontrol, telemonitoring of all of the devices and all of the installations that are in use. Now, besides having, let's say, a technical context, it also has a very relevant economical context as well. It's a very well-known and studied fact that internet connections are increasing steadily, and the trend is ever increasing. This goes in contrast, for example, for circuit switch connections, which a long time ago have already stabilized and are actually dropping in favor of packet switch connectivity, for example. In the case of packet switch connections and internet-based traffic, this traffic is steadily increasing. And it's also worth noting that device connectivity is increasing in a very, very steady way. So it's not only about the fact of connecting users, which can be, let's say, conventional internet connection as we know it, but also machine-to-machine, device-to-device, and in a general fashion, IoT-based connectivity. And this connectivity is not intended just in a transverse way. It's also intended for a wide array of different type of application domains. So we can find it in these initial statements, for example, in healthcare, for example, but we can see that they're already being implemented and they're increasing their use, for example, in sectors such as transportation or manufacturing, among others. So as we can see, there's also not only a technical interest, but of course, there's a social and economic interest in the adoption of IoT solutions. Now, within this context comes the specific case of wearable devices. And wearables are basically devices, not devices, sorry about that, which are worn by users with a goal basically of increasing interaction with the surrounding environment. And in order to do so, we are going to pay careful attention to aspects such as ergonomics. We want to have comfortable devices, low-weight devices. We're going to be considering aspects such as aesthetics. We want devices that have to look good. They have to be cool, actually. And not only that, they also have to provide us technical functionalities such as very precise energy control and communication capabilities. Now, interactivity is one of the main elements that is required in terms of wearables, and communication systems are the ones that really provide this enabling feature. There's multiple applications in which wearables can be looked for, and they have been developing from the initial ones related with sport activities and some health applications in relation with some specific monitoring by health professionals to a wide array of different type of applications in different sectors. For those of us who are a little bit, let's say, older these days, I can't forget about the wearables that were already existing in the 80s. And here I show you two of the ones that at least I knew as a kid myself. And I have to point this one out. I knew them. It didn't mean I had them. I didn't have them, and I wish I did. And we're talking, for example, about a very, very well-known calculator watch, or an even cooler Pac-Man watch, right? So these were really wearable devices. They were integrating electronics that were going on low consumption circuits. But the difference between these devices and the wearables that we know nowadays is the fact that none of these integrated communication capabilities, which is something that, of course, is inherent to the capabilities we need nowadays. Of course, the classification is very varied from the initial proposition based basically on different types of watches or bracelets. Nowadays, we have many, many different types of elements depending on the application and the ergonomics that are required. So we, of course, have mobile terminals. Actually, our mobile phones are wearable devices. They're usually considered as opportunistic sensor systems. We have bracelets. We, of course, have different types of textiles with integration of electronics and photonic devices. There's a different proposition of helmets that are used in sports as well as in rescue systems, for example. Glasses such as HoloLenses or Google Glasses, different type of key rings, and even some very interesting systems such as intra-body magnetic coupling-based communications, which can also be employed, for example, for security reasons. So actually, there's quite a big range of devices that are available out there nowadays. And as we were saying before, the context in relation with the wearables is very similar to the context in relation with IoT and internet connectivity. And actually, the estimation is that this market is going to be steadily increasing, and that the value that it's going to be providing is going to be within the next decade, within the realm of approximately $100 billion every single year. So as we can see, the market share is going to be within the million of devices in different type of elements such as hearables or watches or wristbands or other type of connection devices. So as we can see, there's also a very big interest, in the development of wearable systems. Now, if we talk about communication technologies, there's also been a very strong development in wireless communication systems that can be employed in order to provide different types of coverage capacity estimations as a function of the application. So here we can go from mobile systems currently on the widespread use LTE and, of course, incumbent 5G connections. In the case of wireless sensor networks and WLAN, these are very interesting for telemetry, telemonitoring applications. Nowadays, very, very interesting, all of the new applications developing in relation with low power wide area networks, such as LoRa, LoRaWAN, or Sigfox. And of course, we also have the devices that are more considered as wearables. And these are wireless body area networks in the realm of 802.15 standard and some proprietary standards. And here we have the systems such as Bluetooth or Bluetooth Low Energy, which form piconets and scatternets. We have near-field communications that have become very popular for identification and payment methods. RFID also comes in the category of W-band, even though the range can be bigger, in the range of several meters if it's UHF with high power readers, and intra-body communication systems. So we have different types of solutions that we can employ if necessary in order to communicate wearables. But what is it that we need to take into account in relation with the use of wearable devices? Well, there are some constraints and some challenges. We have to take into account that there's, of course, a limitation in relation with cost. We need the devices to be basically moderate or low cost. Users are not willing to pay a high amount for the devices that we're buying. We need to consider ergonomics. We need devices to have a small form factor and to be comfortable and not to be heavy and not to have a very big profile. Actually, low profile devices are better perceived. Of course, we need to consider energy management as well. We want the devices to be operating within a relatively big time frame. So therefore, we need to consider that energy resources might be scarce. And therefore, how can we handle this situation? Of course, communication capabilities. We really require flexible communication systems, and they have to comply with all of the rest of these conditions in terms of cost, ergonomics, and energy management. So, as you can see, wearables are very, very interesting, but they do provide some challenges. In my talk, I'll be basically discussing about the communication capabilities and the challenges that they are going to be giving us. Of course, ergonomics, energy management, and cost are going to be related in bigger or smaller ways in relation with these communication capabilities. Now, in relation with this, I have to remember everyone. Of course, you all know it, but you know that's why I study these things, and you're going to allow me just to talk a little bit about it. We are going to be using wireless links, and of course, we are going to be using radio waves, and radio waves are very interesting because they are going to have a zero time development. So this means that as soon as we turn on our transmitters and receivers, we're going to have communication link capabilities. That is fantastic in order to provide services. However, it's a very, let's say, hostile environment in terms of interaction of EM waves with the surrounding environment, with different elements that are going to be affecting. And also, we're going to have elements such as high dynamic variability, which is inherent with the fact that it's a mobile channel. We have also variable scattering conditions. And of course, it's detectable. So man-in-the-middle attacks are going to be, of course, very feasible. And we could jam also these channels with basically different types of interferences. So basically, these links are going to be very useful to provide mobility and ubiquity. However, we need to analyze them in order to understand if they're going to work or not. And basically, in order to do this, quality of service is going to be given by link balance analysis. And this is also very well known. And what we need to take into account is that there's different elements in relation with this link balance analysis in order to obtain receive power level, which is going to be compared against sensitivity and depending on the sensitivity value, which at the same time is dynamic, because it's going to be basically depending on bit rate that we require. And this, at the same time, is going to be given by modulation scheme, coding, as well as other factors that can also affect sensitivity, such as hardware constraints given by noise factors, for example. This is going to lead to variable conditions in which receive power levels are going to have to be greater or equal than these sensitivities. And this is why we have coverage capacity relations that are dynamic, because these sensitivity thresholds are going to be changing. Of course, channel dynamics are going to be the element that are going to be the most complex in order to compute and in order to take into account. And in the specific case of wearables, we also have to consider that sensitivity is also going to be affected by the specific factors in the implementation of these wearables. So here we're going to have antenna constraints given by human body impact, for example, or the small form factor, which leads to miniaturized antennas, or the fact that we're going to have to employ conformable antennas. And of course, this might affect the radiation efficiency. And we are also going to have to take into account items such as the energy constraints. So therefore, maybe we cannot transmit with all the power we need to transmit. We also have to take into account the required transmission rates, et cetera, et cetera. In any case, it's going to be compulsory to compute coverage capacity requirements, as with any radio system, by the way, in order to guarantee that these systems are going to be working. So in order to do this, radio propagation estimation is going to play a key role. And there's different ways in which we can do this. On the high end of accuracy, we can have full wave electromagnetic simulations, such as FDTD, FITD, method of moments, etc. They're going to basically solve Maxwell's equations on a volumetric grid. This is going to provide us very accurate results, but of course, it is very demanding in terms of computational cost. So on the lower end of the accuracy, we're going to have statistical empirical based models. These are usually going to be obtained by regressive methods, and they work relatively well, but they're going to be strongly site dependent. So if we change the conditions of the region where we are computing these estimations, these are not going to be working well. They're going to have to be recalibrated. Moreover, this type of empirical based methods are not going to consider in an adequate way small fading phenomena such as given by multipath propagation. Moreover, we're going to have to take into account other type of mechanisms such as multiple types of diffraction losses or diffuse scattering. And in the specific case of wearables, we also have to take into account other factors such as what are the types of human body models that we want to consider, if they're going to be complete human body models, simplified models, geometrical based models, if we're going to take into account human body dynamics and human body location of the transceivers, which also is going to play a key role in relation with losses. The different type of communication channels within the human body are also going to be given by these dynamics. For example, we can have interbody or intra-body communications. And of course, the incumbent applications that are coming in relation with this are also going to affect, for example, what is the location of the transceivers and what are the specific requirements that they have. So as with any network, the topology and the environment are also going to play a key role in this coverage capacity estimation. So there's a midpoint in order to obtain this calculation, which is to employ geometric optics-based techniques such as ray tracing and ray launching, which provide, let's say, an adequate ratio in terms of computational complexity and accuracy for relatively complex environments. So this is basically the methodology that we have been following. So for that, we have developed a full 3D ray launching algorithm, and it's based on solid angle of departure with tetrahedral resolution. We consider all of the electromagnetic phenomena given by simplification of Fresnel equations, and we can configure the different type of parameters that we're going to employ. It's very interesting to note that in order for this type of deterministic based approaches to work well, we need to take into account in a very precise way the topology and the geometry of the scenario under analysis, and to consider adequate material parameters. And this is something that we do in our simulation code, in which dispersive material properties are considered in terms of conductivity as well as in terms of dielectric constant. So in order to increase the computational efficiency of this type of algorithms, different type of, let's say, additional features have been added. For example, estimation based on the combination of relaunching with neural network interpolators in order to reduce computational cost. Also, convergence analysis was performed at the time in order to optimize the parameter configuration in order to, put the adequate parameters for the simulations to provide adequate convergence results without adding additional computational overhead. Mechanisms in order to reduce computational costs by reducing the computation of diffraction components, and this can be done by using a hybrid approach in which ray launching is combined with the electromagnetic diffusion equation, for example, applied in a bidimensional feature for now. Another approach is to employ deep learning techniques in order to provide initial learning patterns that are employed for conventional, let's say, indoor type scenarios in order to provide initial results and train these results in order to decrease computational cost. And different alternatives of this type of methodology have been implemented within our group in order to optimize in a further way the way in which this is developed. So this is one of the latest results in which basically the methodology was improved in order to consider exactly what is the amount of ray rebounds that are employed within the deep learning technique in order to fully optimize the way in which the calculation is performed. So what are the type of things that you can get once you do this type of calculation? Well, you can obtain, for example, transceiver current consumption as a function of transceiver density within a complex indoor scenario as a function of the location of the transceiver. So here you can see volumetric plots of the current consumption of a conventional Zigbee device as a function of where it is located within the department building of our university, where I'm located at right now. So depending on the way the network is configured, as you can see, these maps of current consumption change, and they can aid in determining what is the most convenient network configuration to reduce what is going to be basically the energy consumption. And this is going to be very interesting in order to implement systems that are going to be inherently limited in terms of energy consumption. And this, of course, is going to be the case of wearable systems, for example. The same can be applied in this case. This is for another specific laboratory within our university. And again, we can obtain power consumption distribution plots as a function of the potential location within the volumetric scenario of this laboratory. And as you can see, as a function of the location, current consumption increases in a very, very relevant way. So, of course, this is something to be taken into account in order to implement optimally the network. Not only that, with this type of tool, you can analyze in a very precise way interference impact. And this is an example which is applicable to IoT integration. This is actually an analysis performed for ultra-dense node configurations in which the overall goal is to achieve a density of 1 transceiver per square meter in an indoor scenario within the university. And we're not really interested here on the numbers, but as you can see qualitatively, if we change the amount of antennas that are implemented, this is the amount of transceivers actively operating, and we modify the height in which we co-locate these antenna systems. As you can see, the signal to noise ratio distributions, which are computed volumetrically but represented in 2D planes for the sake of simplicity, change in a very drastic way. Please consider that the overall surface that we are having here is within the order of approximately 200-250 square meters. So it's not a very big scenario. And as you can see, variability is pretty high. If we were to do this, excuse me, in a conventional way, probably would be using empirical based equations, then they would give us very uniform coverage patterns. And this is really far from the truth in this type of complex indoor scenarios. Of course, another example of things to take into account is interference. Here you have a work we did some time ago in relation with obtaining an equivalent model for the interference created by a microwave oven. The magnetron inside a microwave oven is a source of interference that leaks not only from the, let's say, the connections at the door seals, but also given by the fact that the screen in front of the front door is a subdiffractive screen, and therefore it doesn't provide a reflection coefficient that is equal to 1. It's a very high reflection coefficient, but once you model it, and actually you can model it using an equivalent surface impedance method that is very, very similar to what is done nowadays with frequency selective surfaces, then what happens is that basically you are going to obtain leakage from the oven. And on the top image, you can see here, this is an image employing CST and the equivalent impedance sheet model. You can see that here, this is the front door. And this front door, you can see that leakage is coming out. And this is obviously power that can be converted in the near field to a far field radiating source. And this is what we did applying Huygens methodology, a Huygens box method, in order to obtain equivalent antenna rays that can be coupled to the ray launching algorithm in order to, let's say, obtain the equivalent antennas that are radiating in space. So this is, let's say, instead of being a Wi-Fi hotspot, is my microwave oven, which is an interference source. And as you can see, it's a pretty relevant interference source. And actually here you can see some of the measurement results obtained in relation with packet error ratio, which depending on which is the channel that is employed in the case of Zigbee, can give us very, very low signal to noise ratios because the interference can be very, very high. So again, this is something that if we're talking about wearables and IoT, is we have to take into account, because maybe our wearables are living or coexisting with a great deal of appliances that can be potentially interference sources, and in practice they will be. As we were saying before, here we have some of the more detailed results in relation with the node density analysis, in this case for a small indoor scenario. As I was saying before, this is one of the labs that we have in our campus. And what we did is we started from this situation we have here, where we had basically one access point for WLAN, WBAN connectivity within each one of the rooms or the hallways. And we progressively increased the density to this value here, which is basically 1 node per square meter. And what we did is we computed all of the transmission sources here and the potential signal to noise ratio as a function of the duty cycles of these nodes. And here you can see some of the results that were obtained as a function of the frequency of operation, the location of the height plane that is considered, and the amount of transceivers that were operating. And in these images here correspond to different wearable users that were co-located inside. These could move around the scenario. And of course, as you can see, the distributions of power obtained, and therefore of the signal to noise ratios obtained, are highly dynamic. They're going to strongly depend on what is the configuration of this network. So we really have to pay a lot of attention in this detail, because we can have very large variability, which can really affect our coverage capacity estimations and in the end, the quality of service metrics that we're using in the scenario. So here you can see another example. Here we can see in more detail the effects in terms of wearables at different heights. Here, if we change the heights, for example, you can see that there's very strong variations. Even only on the same physical location, we vary 1.5 meters of height. You can see that it's a very relevant impact. Here you can see the same results obtained for linear radials, where we could co-locate the receiver device. And as you can see, well, we have let's say the common characteristic in relation with multipath propagation inside the environment. And of course, we're going to have the losses that are going to be given by the specific line of sight or non-line of sight conditions inside the scenario. Well, once you can obtain signal to noise ratios, you can map quality of service, and you can, for example, depending on the type of system you're using and the EB2N0 requirements given for that communication system, you can plot, for example, where you will be complying with the required signal to noise ratio within the specific volume of operation. So here you can have the different cases as a function of node densities. And in our case, just as an example, we stated that the signal to noise ratio had to be greater or than 5 dBs. So the green plots are the specific areas inside the volume as a function of node density where these circumstances complied. And as you can see, depending on the way in which you specify the thresholds related with node density, these areas can vary significantly. Moreover, we also perform measurements in relation with potential previous interference. And here you can see some spectrograms that were obtained for different frequencies and also for different locations. Here you can see very simple cases for the office environment and for the hallway. And you can see, for example, that here we can observe clearly a Wi-Fi bearer that is not observed inside the office. And even though the surface is relatively small, the interference conditions can be pretty different in the scenario. So again, these indoor dynamics are pretty complex, and we have to take them into account. Of course, you can perform this same type of evaluation in bigger scenarios. This is actually the auditorium of the University of Tecnológico de Monterrey in Mexico. And this is a very big scenario. So actually several thousands of people can be inside here because they have a very big auditorium, a very big library. And we performed estimations of interference impact and calculations of node density, considering the main hallway of the main foyer of the auditorium. So here you can see some of the results depending on what is the node density employed and also the configuration of the system. And again, if we vary the node density and we vary the frequency of operation and the location of the nodes, our conditions in terms of propagation are going to be clearly variable. Here you can see the same examples in terms of coverage plots as a function of node density. Here you can see, for example, the evolution at 2.4 gigahertz for 75 nodes, 28 and 19. And of course, you can see that the coverage plots vary. This is a very, let's say, straightforward conclusion that we can obtain. But it's worth noting that this variation, of course, is not done in a uniform way. It's going to be strongly dependent on the interaction of the nodes with the surrounding environment. And this can be clearly mapped in terms of the quality of service. Here you can see, for example, the simulated impact in terms of EVM for a very simple QPSK modulation scheme. So depending on the way in which node density is implemented, what is going to happen is that our signal to noise ratios are going to vary. And for example, here you can see the constellation for the case of high node density, and you can see what happens when you vary for this high node density for a specific node. This is node 5 that has a very good coverage value. You can see that the constellation is pretty well described. In the case, for example, of low node density, what we have is a very good value because there's basically no interference, and this specific node is located very close to the transmitter. But what happens in the specific case when we don't have good coverage values? You can see that in the case of a high node density here, what is going to happen is for a different node that is located in a position where we have lower coverage, our constellation is going to be working worse. And in the case of lower node density, where the transmitters are going to be even further away, of course, in this case, it's even worse than before because, yes, there's less interference, but there's much less signal as well. So again, the way in which node density varies is going to have a very relevant and non-trivial impact on the way that the systems are going to be operating. Another interesting element to take into account if we are talking specifically about W bands is the fact that we must take into account the impact of human body. And in order to do that, well, it is compulsory to consider some type of human body model. So in our case, we developed a simplified human body model that could be integrated within our 3D ray launching code. And this was done quite some time ago. And actually, the purpose of doing this model at the time was initially having confidence in having the capability of studying the way in which we can include human bodies in relation with a certain type of applications. Initially, these applications were healthcare-related applications based on telemonitoring, and it was interesting to take into account the impact of human body in relation with that. So we developed a scalable human body model that could be parametrized not only in terms of the dimensions. This is, you can configure parameters in order to vary the height or the weight of the subject, and therefore consider, for example, male subjects, female subjects, children, etc., and more weight or less weight. Not only that, it has different layers of different types of tissues and bones, and depending on the type of application that we want to run, we might consider a simplified model. This is going to be the usual case for communications, or we could consider a more complex model. And this is something that we developed specifically for items related with dosimetric analysis in relation with our colleagues at ISC in Madrid. So not only that, we also studied different types of propagation mechanisms that could be used in the future, basically for intra-body propagation, and basically with collaboration, in this case with colleagues at Universidad de Vigo and New Mexico State University. We worked on the development of precursor propagation inside of human body models. And we actually demonstrated that you could reduce the effective path loss that is going to be given in the case of an electromagnetic precursor, a Brillouin precursor, for example, by a factor of 1 divided R instead of 1 divided RK. So this is something that is very interesting and that is still there to be worked in the future in relation, for example, with different types of diagnostic-based systems or communication-based systems. Another one of the elements that is very interesting to understand in terms of propagation and consideration of human body models is ultra-wideband. Now, ultra-wideband has gained increased attention in recent years, basically because it's a very interesting system for basically high precision location and high precision tracking. Currently, standard 802.15.4a has a precision that is given in the standard at 10 centimeters and the state of the art in relation with the transceivers available in the market, basically decawave transceivers, gives values in the range of approximately 20 centimeters in relation of indoor location-based applications, which is a pretty good precision. And it is worth noting that the feature standard, which is 802.15.4z, is aiming at achieving resolution levels in theory in the range of 2 centimeters, which is a very, very high resolution, and that finds many different types of applications in logistics and patient handling, and different types of work-related aspects and industry-related aspects. So given this interest, we have performed different types of analysis in relation with the way in which ultra-wideband could be employed, for example, for location and tracking purposes of users. But of course, in order to do that, it is compulsory to consider the impact of the human body in this type of system. So this is what we have been working on for the last couple of years. And we have been working on, for example, the impact of human body losses and shadowing in relation with ultra-wideband channel characteristics, basically in the 4 gigahertz band that spans from 3.75 to 4.25 gigahertz, and more recently in the 6 gigahertz frequency band. So we have obtained different types of results in relation with initially the type of subject that can be employed in order to consider the impact in relation with ultra-wideband channel modeling. Later on, the location of the different type of ultra-wideband channel transceivers and the way that they are going to be impact elements such as different types of ranging algorithms. So we could compute the way in which we can increase later on accuracy, for example, mitigating that impact. And actually that has been one of the most recent results, the way in which considering how human body is going to impact the way in which ultra-wideband time of flight readings are going to be obtained. You can take into account pre-distortion effects, and therefore you can recalibrate your ranging algorithms in order to take into account the impact of the human body in order to decrease the errors. And this is basically what we have done. And here you can see some of the results by applying the mitigation algorithm. And as you can see, we can obtain a very interesting reduction in what are the errors committed in relation with the precision of ranging and positioning algorithms in indoor applications as compared with no mitigation and mitigation, and depending on the location of the ultra-wideband device, for example, in the arm or in the chest. Not only that, in order to do that, we have also been working on time frequency channel modeling. And in order to do that, of course, we need to try to adapt the simulation technique that we use in order to make use of our 3D relaunching code for a system that inherently is time domain based. So in order to do that, what we do is we sample the frequency spectrum of the ultra wideband channel, and we do subband simulation. And what we do is that we take our initial band and divide it in 3 subbands, and we perform calculations at the middle and edge frequencies of those subbands. And by doing so, we can perform an estimation on how accurate the simulation technique is going to be in order to perform precise RSSI estimations. And from those RSSI estimations, we can perform adequate time of flight estimations. And actually, this is what we have been doing, working on the different type of distributions of power delay profiles as a function of the frequencies that are employed, considering the ultra wideband channel as a total, and considering the impact on the simulation code in relation with, for example, cuboid mesh size and how it's going to affect the resolution of the ranging algorithms that are employed. And all of this is done basically in order to provide modeling mechanisms that can be employed to design in a better way these wearable systems where we could include ultra wideband technology. So just to talk briefly about some of the local developments that we have been doing in relation with this, one of them has been related with sports. So we have tried to couple different types of wireless sensor network technologies in relation with judo. So in order to do that, we have considered the environment as well as a specific developed judogi model in order to take into account the impact of the human body as well as the impact of the judogi dress. And here you can see some of the results. And initially, this was done on a set of only 2 unique users inside the venue. But of course, if we want to perform more precise considerations, then we have to take into account that if we go for competition or training, we're going to have multiple users. So we extended these results for the case of multiple user consideration. And here you can see some of the estimations obtained as a function of the location of the transceivers and considering different distributions of users inside the indoor scenario, which is a real gym that we have at our university. It's worth noting that the full details of this 3D scenario were considered, as well as the full volumetric volumes of the 30 persons that were implemented with a simplified shell model of the human body. We implemented also the design of the system in order to test it, and we started out at the time with initial web-based application in order to send the information. At the time, it still wasn't a cloud-based application. Of course, we have been tending to that more lately. And another application was in Surf. And at the time, we were interested in providing and analyzing connectivity options in relation with the potential of embedding sensors within surfboards and also in putting sensors within the surfer in order to provide body area network connectivity, and later on to provide connectivity from the surfboard, for example, to land or to buoys located in the sea. So in order to do that, first we implemented the human body model coupled to this simplified surfboard model, and we performed volumetric analysis of that. And later on, what we did, and this is the image on the lower left-hand side, this is actually co-locating the surfboard with different levels of sea surface roughness within the sea, the coverage estimation within this range. And here you can see the scale in meters. So this is approximately for about 1,000 square meters of range. So the next step is trying to provide scenarios of communication inside of transportation vehicles. And here are different types of communications that we have considered. This is one case of inter-wagon train communication based on Bluetooth scatter nets. And this was given by the fact that we wanted to directly connect telephones among users inside a train wagon. This is a real train wagon from the CAF company in Spain. So we performed the characterization of the system. In this case, the complete system, again, with web-based transactions, was also implemented to test the solution. We performed a similar analysis in this case, but for long-range railway passenger vehicles. And again, here we were interested in performing detailed analysis of the radio wave propagation conditions and the way in which we can characterize the wireless channel as a function of user location and the topological complexity of the wagons inside. You see, a train wagon has a very large amount of scatters, and therefore they're going to strongly impact the way in which our systems are going to have their coverage inside this type of scenario. And this is something we wanted to consider. Moreover, on this upper figure here, it can't be seen very well because the figures are a bit small, but here we're considering different densities of users inside the wagon and the way that this density is going to impact on the overall performance of the system. We did the same type of analysis, but now considering a metro station in Bilbao. And this is basically a simplified model of the metro station. This is actually in the metro station of Moyua in the center of Bilbao. And here it was interesting to pay attention to the density of users located at what would be the access to the metro wagons, as well as inside of the metro wagon models that we implemented in order to provide a context-aware service within the metro of Bilbao. We also implemented an interactive shopping environment, and of course, there were nodes that were embedded in the shopping cart, and as we can see on the lower image here, we considered the simulation scenario of an alley where we had users that were within the propagation path and therefore could impact on the way in which the system was working. And as you can see, depending on what is the type of metallic or glass element used, for example, these are like the two limiting cases in relation with propagation, because here we were combining wireless sensor networks with RFID tags in order to perform the identification of the merchandise. Well, this was going to provide different characterization on the wireless link channel. We also implemented the corresponding app in order to monitor, and that was pretty interesting and fun to do. Of course, in order to measure it, initially you have to do it in 4 a.m. in the morning so you don't bother clients, which is pretty fun as well. As I said earlier, we have been also working in the application in the health sector. So here was one of the initial developments, and this is a Holter, which is a device which is an automated electrocardiograph. And the idea is to implement one in a wireless way. This is now something very trendy. At the time, it was pretty novel. And to communicate directly with Bluetooth to our mobile device, which would be the gateway to our back-end systems with the medical specialist on their side. So here, among other things, it was compulsory to analyze radio wave in order to understand if connectivity requirements would be upheld in the case of any type of potential distribution on the way the sensors are located, the mobile phone is located, etc. An additional development was the development of social sensor networks, and this was done within the development of a joint project with our government and the Red Cross in order to provide different types of assessment of people that were living on their own but that had some type of neurological disease. In order to do that, there was a combination of biophysical medical sensors and social sensors. These social sensors are basically indicators to see if a user is inside a room, or if it's stepping on a specific tile, or if the user is in the bed or has opened the door, etc., etc. And of course, here we had to combine user interaction in order to provide quality of service. All of the system was implemented, as well as the corresponding backend as well. And actually here you can see some of the results obtained, and as you can see, of course, depending on what is the location in which we are working and what is the location of the transmitters, then of course our distributions are going to be different, okay, in relation with the operation of the wireless sensor networks. Here again with the Holter, sorry, there was a mix-up in the slides. Here you can see a little bit of the characterization as well, and you can see how it depends as a function of where it's located, if body shadowing is produced, the impact of the human body, etc., etc. One of the latest works has been a context-aware intensive care unit. Here, there's interest in deploying IoT within the intensive care unit, but one of the main issues is considering how interference is going to impact and if there's adequate coverage. So this is an initial trial developed some time ago, and we analyzed the way in which this would be working and the impact of the users inside of the scenario. So these initial trials here, you can see real spectrograms measured within the premises of the ICU. And of course, this is a very complex scenario where wireless channel modeling is compulsory in order to fully understand the way in which this is going to be work and it's going to be effective. Another one of the most recent results is the application of LoRa technology, LoRaWAN, in order to perform in the same complex of the Hospital of Navarra, but in a bigger area, for patient tracking and asset tracking. So here you can see some of the results. A full-fledged coverage analysis was performed considering the full complexity of all the buildings. Here you can see a little bit the layout that was performed, all of the measurement results. And we're still working here to provide a real system. This was only mock-up design in order to characterize the wireless channel. Now we're working little by little to get the system implemented and to test it with real patient tracking. And this is, I think, yes, almost the last slide. This is also one of the latest results, and this is basically in order to provide an interactive utility tunnel environment. You see on the subfloor of the city of Pamplona, there's utility tunnels that are employed. Here you can see some of the images on the left-hand side. And these tunnels, which take utilities such as lighting and communications and gas and water pipes, they need to be connected because, of course, there's going to be workers that are working here, and there's no coverage of mobile systems inside due to the way in which the tunnels are implemented. So we performed a detailed coverage analysis and actually deployed Zigbee as well as LoRa technology to understand and see if it was feasible to use them in order to provide low capacity but high quality coverage in relation with the potential signal transmission of emergency signals, for example, if there was an issue with a worker within the tunnels. And of course, we also considered the introduction of human body models inside of this type of utility tunnel, because as you can see, there's very strong non-line of sight conditions and very strong scattering that can be produced in this type of environment here. So I just wanted to tell you some of the applications and some of the challenges, basically centered in the case of wireless channel characterization and the impact that it's going to have in terms of the way in which our wearable devices are going to be working. So we really need these wireless systems in order to provide these context-aware implementations, and it's going to be challenging. We need to comply with coverage capacity. We're going to have a lot of device constraints and limitations in the way in which the network can be deployed. For example, LoRa works in a star topology, so this is something we need to handle. And of course, there's many solutions that come to our way as engineers and scientists, different types of headnet configurations. There's a very interesting and exciting development of conformal electronics and the integration of RF front ends. There's a big challenge in terms of smart energy management with all of the research in terms of energy harvesting, rechargeable batteries, supercapacitors, and how we can manage all of them together. And of course, in our case, precise wireless channel analysis, which we think that can be very useful in terms of providing adequate network and device implementation. Well, sorry there's some Spanish there, sorry about that, didn't notice it. Anyway, I really think it's a very exciting journey that opens ahead for all of us, so I really wanted to share it with you. Thank you so very much for your time and your consideration. It's 3:32, so I went 2 minutes out of time, I'm sorry for that. I'm very glad and open to any questions. I'm not sure if we have time for that, but just in case, I'm at your available for you for anything you may need.
Professor Benhaddo, you are here with us?
Hello, everybody. Good morning.
Good morning. How are you?
We're doing well. How are you doing? Sorry, I joined the meeting at 7:30, but it was, I think my system did not give me the ability to talk, so I was talking, but nobody heard me. And thank you for the very interesting presentation, Professor. It's really, as you said, a problem that has a lot of opportunities And the question I have is in terms of deploying base stations that will interact with users. How do they or what is the distribution of those base stations as reference to the number of users that will be run area, given that we're going to increase the number of users?
Thank you very much. That's a very interesting question. Actually, in this presentation, I talked nothing about base stations, right? Because let's say that they would go more in the realm of PLMN communications, which we also work. Okay, so to answer your question, you're completely right. That's something that is very relevant that needs to be considered, and that is basically again a coverage capacity estimation. So if we go, for example, on what is going on in wireless mobile networks, which is the evolution from 3G to 4G, which is maturing right now. I mean, 4G networks are mature right now. They're achieving maturity level. What happened there was cell densification in order to provide a smaller cell coverage, in order to provide higher capacity. And in order to do that, you densify cells. This is a very well-known strategy that you can use in order to say my cells are going to be quasi-static in terms of user mobility. Therefore, I can maintain higher levels of signal-to-noise ratio, and therefore my transmission rate can be higher. Now, if we go from 4G to 5G, which is basically the trend right now, things change a little bit there, because in this case, of course, we go for even higher speeds. The threshold is approximately at 10 gigabits per second per cell. That is not going to be achieved with every single frequency and every single system. That is not true at all. That's going to be happening only for some small cell distributions, not for large cell distributions, because coverage capacity constraints cannot be maintained, really. But the thing that we need to take into account there is that 5G is going to be capable of doing some things that we weren't doing before. For example, we're going to be capable, at least in theory, of using D2D communication. So we're going to have comparative schemes that are going to have very small links, and therefore coverage capacity can be very, very high, because transmission power is going to be very low and interference is going to be very small. So I mean, you are not going to have to put a lot of base stations. You're going to have Pico cells that are going to be giving you the service, and they will be connecting to base stations, right? And the other really cool thing is beamforming, right? And we have been, and I'm sure a lot of the people that are here work with beam steering, beamforming, MIMO systems, MIMO multi-user, MIMO 3D, and all this jazz, right? So finally, this is the good news for everybody. Finally, we're going to be able of using it somewhere, right? Because for the time being, it was like a lot of hype with MIMO and 4G. I'm sorry to say that MIMO and 4G has not played a very big role, right? Because actually implementing MIMO with users is very difficult. It's very difficult to have multiple streams with the user terminals. However, 5G is going to be more keen on that. And not only that, 802.11ax, which is Wi-Fi 6, is also very strong on beamforming. So I think that these two evolutions, the capability of large densifications given by D2D, which is also going to be related with wearables in this case, and the capability of handling better interference with beamforming capabilities is going to modify the landscape in terms of the base stations. There will be more, but they are going to be different. And we're going to have a lot of pico cells and microcell distributions, right? We'll see. I mean, we're going to have to let operators deploy it, right, to see how it goes on. But I think things are going to go that way. Yeah.
Thank you very much.
Thank you. Thank you.
Thank you. Any questions from the audience? Probably not another question related to education. I mean, we need to educate engineers and probably have use tools that are or make visualization and understanding of the concept easier, because we're getting to more and more interconnected system and complex system. What tools do you make available for students to pick up and and contribute?
Okay, that's a very good question. I agree with you totally. Yeah, I mean, when we studied electromagnetics, it was the blackboard, right? And you would go to the book and you would cry, and that's all. And it was a good experience. I mean, if I just clicked my camera here, you would see Balanis on the shelf, and you would see Posar on the shelf, and Collins and all that stuff, right? And Stratton and all of these classical electromagnetic books, which I enjoyed very much, but they were not trivial to work at all. So of course we need visualization tools. And in our case, for example, in the case of electromagnetics, we are using educational licenses of CST, for example. And in the specific case of what I've been showing here, this is ad hoc implemented code. We have done that code in MATLAB. And the thing is that it's really not for undergrads. I use it only with either my PhD students or with postdocs, because the code is, to be honest, we're friends here, right? The code is hell. I mean, it's not intended to be used in a user-friendly way. So it works relatively well, but it was not coded as a professional code. So right now, for example, in my case, what I'm doing with master students is we're using simplified MATLAB analytical-based models because, for example, you can use ultra-wideband. That's a specific case. We can obtain power delay profiles that can be obtained from ray launching, but then you can take that to MATLAB code to have the impulse response that can be done in a very simple way. So that's basically what the type of thing that we're doing, showing them the type of tools you can use, and then try to simplify them as much as possible so they go to the concept and don't go crazy with all of the code that's behind. I would love to have more professional tools, but they're expensive.
Yeah.
So,
especially for educational environments in Morocco, for instance, we would like to have some tools that can engage more students and increase the number of engineers who can contribute to this area, which is booming, and there is a need for it. Yeah.
I fully understand. My suggestion for you would go for educational CST. They can have comprehensive prices there. And in the case of wireless channel modeling, one of the tools I use, for example, is the Quadriga model from Fraunhofer. It's a free tool. You can use it if you want. And it's based in MATLAB. And that's a very interesting tool. I can give you the information if you want. It's free of charge completely.
That would be nice.
Sure.
Thank you.
You're very welcome.
Thank you, Dr. Atman, for picking up the tab and introducing Dr. Francisco Falconi. So I think any other question? I think this is an interesting discussion. All right, so with that, I think we'll bring this session to a closure. Thank you, everybody, and then we'll hand over the control to Dr. Atman.
Thank you. Thank you very much.
Thank you, Francisco, for this wonderful presentation. Thanks, Professor Benhaddo. You can stay with us. We have other exciting presentation. I give the floor to Professor Osman.
Thank you very much, Professor Otmani. The next presentation will be given by Dr. Nasser Shahat. Dr. Nasser Shahat, are you hearing me?
That's me, I'm here. Can you guys hear me?
Nice to meet you.
Nice meeting you.
Thank you very much. Good. Your talk is entitled Enabling New Types of NASA Mission Through Innovative Antennas, Earth Science and Deep Space CubeSats, Mars Helicopter, and European Lander. But first, here is a short reminder of your biography. Since 2013, you have been a microwave antenna engineer with NASA Jet Propulsion Laboratory, and you have been technical section staff. You are currently the payload system engineer lead on the SWAT mission. In 2017, you received the prestigious Blue Allen Award for Excellence awarded by NASA's Jet Propulsion Laboratory for demonstrated unique talent as a leader in rapid spacecraft antenna development and telecom system engineering. Finally, in 2018, you were awarded the Future Technology Leader Award by the Engineers Council and the NASA Early Career Achievement Medal by the United States government and National Aeronautic and Space Administration. This was a short reminder of your biography. Are you ready to present your talk now?
Absolutely.
Go ahead, please.
Okay. Okay, so thanks for having me. Thank you very much for the invitation. I'm very glad to share some of the latest innovation at the Jet Propulsion Laboratory with all of you. Morocco is actually a country that is very close to my heart. My parents are from Algeria, so I got the opportunity to be in Morocco many, many times. A lot of my best friends are from Morocco, so I was very excited to visit again. Unfortunately, we have to do that remotely. Okay, so let's get started. I'm going to make an overview of different missions and different antenna design that we developed for this mission. So I will start with CubeSat. JPL has been working on CubeSat mission for the last 6 years quite intensively to enable new types of missions such as Marco, which is the first interplanetary CubeSat, so going away past Earth's low Earth orbit. And you will see that this is actually a very interesting concept. So 5 years ago, the former director of the Jet Propulsion Laboratory challenged the laboratory to find a way to achieve bandpass communications during the entry, descent, and landing of InSight lander, and using a CubeSat. So at the time, we had absolutely no clue how to do this, mainly because the CubeSat is limited in terms of output RF power, and they are limited in size. So it's very difficult to deploy very, very large antennas to compensate for the low power that this CubeSat can provide. So it was very challenging because we had no storage volume allocated in the CubeSat. And as a result, we had to come up with a concept that falls atop of the CubeSat bus, deploys into an antenna aperture that is 3 times the size of the CubeSat. So the concept is very simple. InSight, as it lands, transmits all the telemetry to the CubeSat using UHF, which is typically the frequency we use for short range communication. And then the CubeSat in real time transmit back without any delay, transmit back to Earth the data that is as it is receiving. So when it's receiving at 8 kilobits per second, and it needs to transmit back at 8 kilobits per second as well. So those are the constraints that we had. So we developed this reflectory concept, which falls atop of the surface of the CubeSat, deploys with 3 hinge-driven panels, as you can see in the video on the left. The reflectory panels are held against the CubeSat bus using burn wire. So the burn wire, as the names give it away, we actually apply current on them, and it burns the wire and cut the wire. And then the panels deploy. As the 3 panels deploys, then there is the feed that you see right here, deploys as well because it was held in place because of the panel. So to achieve the 8 kilobits per second at 1 AU, which is about 149 million kilometers away from Earth, we needed about 28 dBi with circular polarization, obviously, because we're extremely limited in terms of RF power and DC power to drive the SSPA. So we had about, I think, from the concept to the delivery about 12 months. And so it was a pretty fast development compared to other planetary missions. And so we had to be very cautious with the approach that we took to make sure that the design was successful, because if we did not deliver on time, we will just not launch at all. So the few innovation that we came up with is the reflectory panel design, where, as you can see here on this layout, you can see that we have two Rogers board on each side for symmetry purpose. And in the center, we have a composite material that allows us to be very, very strong. And this combination of the two allows us to have flat panels that meet the surface accuracy requirement, but also maintains good thermal surface, maintain good surface flatness over thermal. So having the symmetry makes sure that the thermal gradients across the surface of the antenna remain as low as possible. And then the second innovation is the hinges that allows us to fold these antenna panels very close from each other, because if you have large gap between these panels, you're going to disturb the radiation pattern quite significantly. You will have gain drop, but also a very, very high side lobe. So all of that leads into an efficiency reduction. If your efficiency is too low, then you start growing the antenna size to compensate. And that makes the allocation to fold the antenna much larger. And also makes the antenna design much complex to deploy, making it much less likely to be successful. So all of those are trade-offs that you need to be very careful about when you actually come up with the design. And then we have the feed that deploys in a very, very simple way using loaded hinge. And you will see a little bit more information about that later. A reflectory design is actually pretty straightforward. To come up with these layouts, you can come up with a MATLAB code that does that very, very quickly. It's not very challenging. Maybe in 1-2 days you can come up with this. The main challenge is actually to design a feed that illuminates this rectangular aperture as efficiently as possible, so you can get the highest efficiency out of this antenna design. So as you can see on the bottom, the two radiation patterns are actually pretty nice. We have a very good accuracy between calculated and measured results. And the predicted gain came very, very close to what we predicted. So we had margin, as I said, the requirement was 28, and we achieved more than 29 dBi. Oh, and on the right, we actually show the optics, which is also very critical to get the best efficiency out of this design. However, you're constrained in terms of how you can move things around. Obviously, if you didn't have any of these constraints, you will probably get higher efficiency, but you have to deal with the constraint that you have, because that's the reality. So this is how the feed looks like. It's a 2x4 patch array that allows us to illuminate efficiently the aperture of the antenna. Each of these elements have a taper, a Taylor distribution. So as you can see, 0.5, 0.8, 0.8, and 0.5 to allow us to reduce the side lobe toward the bus itself. So the bus will be on the right side here, and you can see that the side lobe are much lower than 20 dB. So that allows us not to be affected by the presence of the bus, which is in very close vicinity of this feed. If you don't pay attention to that, when you put everything together, you will have a very bad surprise. Then, I always really like to show this design that was actually done by my colleague, Emmanuel de Corsas, because it's the perfect example to illustrate how basic knowledge of RF allows you to come up with a smart design. So this one is actually the UHF antenna. The UHF antenna needed to provide a gain of about 7 dBi. and it needed to fold against the surface of the bus, so no storage volume allocated inside of the bus. Of course, successfully, the deployment needed to be successful, so you need to make it as simple as possible, as usual. And we also needed to get circular authorization to receive the data from inside lander as it landed. So we actually decided to use a loop. As many of you know, a loop is supposed to provide linear polarization. So if you excite the loop at one of the corners, you will get linear polarization in this direction. Now, if you excite this loop on the other corner, on the right bottom corner of the loop, you will get polarization which is 90 degree orthogonal of the first one. So if you know what the definition of a circular polarization is, you would know that there is 3 requirements that you need to meet. The first one is that you need to excite 2 orthogonal polarization. So let's say V and H. The second one is that these 2 polarization needs to be excited with the same amplitude. And the last one is that these 2 polarization need to be 90 degrees out of phase. So I just show you how you can excite 2 polarization that are orthogonal out of a loop. And since they are orthogonal, they won't interfere from each other. So you can excite these 2 corners, and you will have a fairly good isolation between these 2 ports. So then, if you put an antenna on the CubeSat, you need to be aware that you will have reflection from the CubeSat. So you put it at the height that will allow you to increase the directivity by 3 dB. And so then the things that you need to do is to find a way to excite these 2 polarization with a 90 degree out of phase. So if you excite these 2 polarization with 0 degree and minus 90 degree, you will get right-handed circular polarization as we need. And that's what we did. And to do that, what we come up with was actually to use the loop itself as the ground plane for a microstrip line, which allows us to excite these 2 points here and there with 90 degree out of phase. By the way, there is a typo here. It's 0 and minus 90 to end the same amplitude. So that's how you can do that. So you have the balloon that allows you to do that. And we achieved the requirement by doing so with a very good cross XPD. So that's an excellent example of how you can apply basic RF knowledge to come up with an innovative design. And then for the mechanical deployment, it's very simple. As you can see, we have 2 springs that deploy this loop antenna, which is placed on a fiberglass substrate to give you strength and a good mechanical structure to deploy to avoid vibration or even breaking during launch because of vibration and shock. So you can see the picture of the antenna deployed and stored. So you can see that the storage volume that it takes is very limited and it's outside of the CubeSat. And those are the radiation pattern results that we obtained. As you can see, we used a CubeSat mockup. The radiation pattern at this frequency needs to be done in free space. So that's why we're outside. You cannot perform a measurement at 400 megahertz indoor. So that's the reason. And as you can see as well, we have error bars because these measurements are not as accurate as indoor measurement at microwave frequencies. So you need to be aware of that and be very, very aware of what the error you will get, because those numbers are what you provide to the system engineer, and you want to make sure that they apply the right margin on top of the number that you provide. And as you can see, we obtain very good accuracy, and the difference between the cross-polarization discrimination is actually pretty good for such a compact and simple design. So Marco was the first interplanetary CubeSat, successfully launched, successfully traveled to Mars, successfully provided band pipe communication as we wanted, and took a beautiful picture of Mars that you can see on the left, where you can actually see the feed on the bottom and the reflectory on the top. And obviously, not that it matters that much, but Mars on the background. We also verified the radiation pattern successfully in space, and the gain came out within plus minus 0.4 dB to what we actually measured on in the radiation pattern range for the reflectory antenna at X-band. And here I actually show the received data by the deep space network during EDL. So as you can see, we have Marco A and Marco B. We launched 2 for redundancy to make sure that the mission will be successful. And there is a difference between the 2 received data, and that's normal. It's because the DESN is using a shared aperture concept where you use only one beam and receive data from both CubeSat at 2 different frequencies. So each of these CubeSats were tuned at 2 different frequencies, slightly apart from each other. And the DSN is looking at these frequencies to receive the signal at the same time. And so as a result, one will be at the peak gain of the DSN and the other one will be slightly off. And that's the reason why you have about 1.5 dB of difference. So this achievement was historical. It was enabled by these 2 antenna innovations. And also, not only enable this mission, but it's opening up many future opportunities for using CubeSat for deep space science mission. Okay, so following that, obviously, whenever we develop new antennas, scientists are coming back to us and they are asking for more. We want to go farther in deep space, so telecom engineers are asking for larger aperture to achieve higher gain. So we also developed this antenna which provides an aperture of almost 1 meter by 80 centimeter and provide a gain of 47 dBi with an efficiency of 47%. So that's at K-band. So that's quite an improvement compared to Marco, and we actually developed this antenna, deployed it successfully on the ground, obviously, tested it in the range. We obtained about 47 dBi of gain, and as you can see, the accuracy between calculated and measurement is pretty decent for a K-band deployable structure. You have to understand that when you deploy a large structure like that, it's actually not that trivial to measure accurately on the ground because they are designed for 0 gravity. So you try to have offload structure, which you see all these wire is the offload structure with weight on the other side to represent this 0 gravity environment that space is supposed to provide. But so you will have misalignment as a result, and it's always very important that you verify the surface flatness after you deploy the antenna so that you can make sure that there is nothing that's not expected, and if there is something that is not expected, you can also insert that into your model to account for it. So then I'm going to talk about mesh reflectors, and I will start by talking about another groundbreaking CubeSat, which is RainCube. RainCube was the first Earth science active radar that was deployed in low Earth orbits. Like I said, the first active radar, meaning that this radar was actually transmitting and receiving. Most of the previous CubeSat in low Earth orbit were passive instruments, such as radiometer or spectrometer. So they are not transmitting any power. They are just looking at power reflected and emitted by Earth. And so here, the enabling technology was also the antenna, which is the one I show here, which is a deployable half-a-meter mesh reflector operating at Ka band at 35.75 gigahertz. It needed to provide an efficiency higher than 50%, with a gain of more than 42.5 dBi. We achieved 42.6 dBi and 56% efficiency. We had about 1.5 U of storage volume, which is 10 by 10 by 15 centimeter. And the deployment accuracy needs to be highly reliable, because at Ka band, the surface requirement, the RMS value is about 0.2 millimeter, which is extremely strict. We also never deployed in space a mesh reflector that operates at Ka band. So we used a mesh that has opening per inch of 40 OPI, and up to now, most of the space mission have never ventured higher than 30 OPI mesh. So as you can see here, the antenna is stowed on the left, and on the right, you can see that the antenna is started deploying. Few things that are key to this technology is the telescoping waveguide that is in the center. It's actually not telescoping, it's the feed that is telescoping along the surface of this waveguide. The waveguide is fixed and do not move. Then we have a feed horn, which is a multi-flare feed horn, which provides a very good beam circularity and a very good cross-polarization discrimination, so good XPD. And the key here is actually to come up with the optics that allows us to fold everything into the storage volume while minimizing the risk of deployment failure. So we actually used a Cassegrain design. The Cassegrain design was very convenient because the subreflector is under the focal distance. So it allows you to minimize the number of deployment of the feed. And then the focal distance over the diameter of the antenna needs to be picked such that these ribs fold nicely around the feed horn. And those are all the trade-offs. We worked very carefully at the beginning of this project to make sure that we picked the best RF and mechanical design. And that's really key. Most of the time, if you look at what has been done, mechanical engineer works on their side and RF engineer works on their side. They don't talk very much, and they end up with a design that's either not RF optimal or not mechanically optimal either. So in that case, we really pushed to make sure that the likelihood of success and the best RF performance within these constraints could be met. So I'm going to show you a video of the deployment. So as you can see, the canister, like I said, is about 10 by 10 by 15 centimeter. We have 4 screws around that allows us to push out the entire antenna out. The ribs start deploying. All of that is fairly well controlled because it's controlled by a motor until the mid-hinge start deploying. So you see up to now, everything is controlled. You can revert back with the controller. But once this mid-hinge deploy, that's game over. Everything needs to be perfect or you cannot revert back. And then finally, the last step is the subreflector that deploys, and it's just a spring that pushes it out. For the RF design, like I said, this is a Cassegrain design. One other key feature of the RF design was actually to compensate for the surface aberration that comes from the fact that you actually don't have a parabolic shape out of this deployable antenna. And the reason is very simple, is that between each ribs that you see here, they are limited in number because you don't want things to jam during the deployment. The surface of the mesh is completely flat. So as a result, you have a systemic surface aberration that's coming from that. So what you need to do is refocus the feed location, or the subreflector in that case, to re-optimize, and you can almost bring the loss close to zero with the number of ribs that we are using here, which is 40 of them. And those are actually measurements of the actual surface that you see here. We used a laser ferro arm that allows us to get the surface of the mesh without actually touching it at all. And after that, we extracted the parabola surface to illustrate what kind of difference we're actually seeing. And you can see that the difference are quite significant. And that's the reason why you need to compensate for the surface aberration that's coming from that. And this is a very, very nice video of the antenna deployed in space. The reason why we actually took these pictures, which is actually a succession of pictures put together, was to verify to the best that we could that the antenna deployed successful. So here you can see the tip of the horn at the bottom. You can see the three struts that holds the subreflector together, and you can see some of the ribs and the mesh. And in the background, you can see Earth. So we took the exact same picture on a lab, and as soon as we received this picture on the ground, we overlapped the two pictures to verify that everything that we see in this picture deployed where we expected it to deploy. And then we got some very, very neat science out of it. So the purpose, which I forgot to mention, of this CubeSat was to measure rain precipitation. Hence the frequency band that we picked, which is Ka band. And this vertical line that you see is actually the absorption line from the precipitation where a rain cube was able to pass. And what you see on the bottom, which is a 2D plot, is actually data that was obtained using another CubeSat with a radiometer. And the scientists overlapped this data, and they were actually very, very impressed with the level of accuracy that they obtained between these two CubeSats. And now they are considering to launch much larger small sat missions, where they will fly these two instruments that were qualified through this CubeSat mission in larger missions to get a better science in the future. One key of using small sat or CubeSat is that now you're able to send a constellation of them. And as a result, you will be able to obtain temporal resolution that you wouldn't be able to get with a large spacecraft. So obviously, large spacecraft will give you much better results, much better SNR. The quality of the result will be much, much better. But what a CubeSat can do is giving you information that these large, highly reliable and highly accurate spacecraft are also very, very expensive, will not be able to provide, which is the temporal resolution. And that's where scientists are really excited about using small sat and CubeSats. So like I said, whenever we develop antenna technologies, people are getting excited, but the scientists always want better. So they ask us to develop an antenna that could be up to 1 meter aperture, and that could also be scaled potentially in the future to 2 meters, 3 meters, 4 meters, if we use a larger small satellite. So in this case, they constrained us to use a 12U CubeSat and they provided only a 3U storage allocation, so it's 1/4 of the CubeSat bus to obtain a 1 meter diameter. And the antenna that I show here is actually an offset reflector, and the reflector itself was actually designed and developed by a small company called Tendeg. We work with them very, very closely to get the need for this mission. It also, the requirement was also to operate at K-band, achieve more than 50% efficiency, but we overachieved and obtained much more than that. So this antenna was developed for the radar mission, the same one for RainCube, but also we developed the same one for telecommunication. So for telecommunication, people were interested in having X and K band capabilities. So this is the one I'm going to focus on here. So we developed a feed that will that will fit inside of the storage volume and be compatible with this reflector. So you can see the X-band design on the left and the K-band design on the right. The K-band is very straightforward. That's a horn with a polarizer. And the X-band design is a dual frequency metal-only patch array, and I'm going to show more details about this later. You can see how we model this reflector in TICRA-GRASP, which is the tool that we use the most for a large reflector and also large spacecraft simulation. And as you can see here, the feed is located here, the CubeSat bus is here, the boom is represented here, and the reflector is here. And these results are highly reliable, and you will see that the results that we obtain are very, very good. So this is the X-band results, uplink and downlink. At uplink, we don't really care about the performance in terms of cross-pulse. You can see that we achieved about 13 dB of XPD, which is not great, but it doesn't really matter because we have so much margin at uplink. And at downlink, this is where the design needs to be refined, where you need to achieve the highest gain and also minimize the XPD. So as you can see, the accuracy between calculated and measured is pretty good. At X-band, it's not that difficult because the surface accuracy is not that stringent. We obtain efficiency that are very, very high. Again, because here, this is not a Cassegrain design, so you don't have any blockage that comes from the subreflector. You don't have blockage at all because you're offset fed. And the surface accuracy and also the surface mesh loss are very low. You can see in these two lines, surface mesh almost close to 0, and the surface RMS, it's also very, very low. It's lower than 0.1 dB. So those are the reasons. And then let's look at the K-band. The K-band results are also very, very accurate. And I do need to mention that the reason why they are so accurate is because we extract the surface of this reflector, inject it into the GRASP model, and that's how we actually assess the impact of the surface of the reflector. So again, the surface is not perfectly parabolic, but we pick the size of these triangles to minimize the loss at K-band. Okay, so like I said earlier, we are now looking at small sat that will combine the two technologies that I mentioned earlier. So the RainCube active radar and the radiometer, passive radiometer that we've flown on another CubeSat. And here we actually try to be very clever. What we tried to do was, let's use, since we have the room to do so, let's fly different feeds so that we can, so that we can take advantage of the spacecraft motion to achieve 3 dB overlap, and that by doing that, we can get much more coverage of Earth in a constrained time. And so we get much more science and much more data out of it. So the feed placement was optimized to do so. And so if you look at the beam that we see here, they are very far from each other. So in red is actually the 5 dB beam width, and in black is the 3 dB beam width. But now, if you account for the spacecraft motion and you have a straight line like that you move, you can actually get the 3 dB overlap like that. And that's what I meant by being clever. And then you don't even need to worry about mutual coupling between these elements, because you only start worrying when you have a 3 dB overlap on the 2D pattern like this. But in this case, you can see that they're very far from each other, so the coupling between these elements is going to be pretty low. We achieve very high efficiency again. This design is at K band, same frequency, 35.75, since we're trying to just fly the exact same Raincube instrument with a much larger antenna. So this one is going to be 2.1 meter. 2.1 meter. And as you can see, we have the radiometer on the other side. So like I said, every time we do something, the next mission is trying to be clever and to be more innovative to make sure that we get better science out of the mission. Okay, now I'm going to talk about metasurface antennas. We have been working on different metasurface antennas in the past, I think, 3 years or so. We were lucky to be funded by ESTO through an ACT program, and what we proposed was to design W-band multi-beam antennas that are completely flat and that are compatible with micromachining technologies. So we've been developing a lot of instruments that are now relying on CMOS technologies, trying to make them lower power and much smaller, so that we can fly these on different platforms such as CubeSat or even small robots. And so we need to be very clever with what can be done and how to make this instrument much smaller. So here we decided to focus at W-band, which is 94 gigahertz, and the scientists were interested in having a beam pointing at 0 degree and 2 other beams pointing at -45 and +45 degrees. So the beam in the center will be pointing toward Earth, so nadir pointed, and the 2 others will be able to get data from 2 different directions that will give us information about wind, Doppler information about the wind. So we will be able to know in which direction the wind is going and at what speed the wind is going as well. So we work with scientists to usually write this proposal to understand what the requirements are for such antennas. So it's also very important to understand the science behind it, because otherwise you will not get funded in the first place if you don't have a very good science case, because that's really what drives every single NASA mission. So in this case, the design is interesting. We're using quasi-optical pillbox design. As you can see here, you have a source on the bottom layer. We actually have 3 horns here. You excite these parabolic elements here. So you have a parabola across the surface. And then you have a slot that couples this power to the top layer. And on the top layer, you still have a parabolic shape here. The wave is reflected back in this direction, and then you design this metasurface to modulate this signal in a way that you get the pattern that you want. And the pattern that you want can look like whatever you want. So it can be a very directive antenna, it can be an isoflux antenna, anything you want, and you can even have multi-beam out of it. So here, we actually used leverage on the pillbox design to excite this parabolic shape from 3 different locations. And by doing so, you can get different beam directions. So you can pick the offset on each of these feeds so that you can get the beam direction that we want. So on the paper, it's feasible. In practice, it's much more complex, and the fabrication of such an antenna is very complex. It took us a lot of time, a lot of resources to actually achieve that. And as you can see here on the left, you actually have the first prototype that we tested. So you have the 3 connectors to excite this SIW horn. And here you can see how this metasurface looks like. So they're like sub-wavelength slots elements, sub-wavelengths, meaning that they are not resonant slot as we're usually used to. And that's the reason why these slots can be so close from each other. And then the separation between these repetition allows you to get the beam direction across this direction as you wish. And those are the measurement results. So you can see when you excite the feed in the center, you're getting a beam at, I think, was about 14 degrees, which is what we wanted to get. And the H-plane direction, we are at 0 degrees. And then if you excite feed number 2, you are now pointing in the same direction in the E-plane, but in the H-plane, you are close to 45 degrees, which is what we wanted to achieve. And if you go to feed 3, you're going to get minus 45 degrees. So we published this result. Feel free to take a look at it. And we are now working on another design that's much higher efficiency and that will combine Schottky diodes on this top element that will be biased with so that we can change the state of each of these elements to steer the beam in the direction of the metasurface itself. So then we can steer the beam in this direction without any issues by just controlling the state of these diodes. It's still in progress. The second design that we work on, we are actually collaborating with University of Rennes, and David Gonzalez was working with us at JPL as a postdoc, and then he moved back as a CNRS researcher at University of Rennes, where I actually did my PhD. We are very, very excited about this work because here, what we tried to achieve was to get rid of all of the weakness of these metasurface antennas. So metasurface antennas up to now were printed on a substrate, and as a result, they were pretty low efficiency, and they were not the best designed for flights, and that really constrains you on where you can go. So, for example, if you go to Europa, the radiation levels are so high that you cannot use substrates. So it's completely prohibited, otherwise your antenna will just degrade over time and they will not survive the environment. And same with thermal. If thermal changes are stringent, you will have delamination issues if you're using substrate and things like that, which take a lot of time to qualify. And so, and finally, metasurface on substrate are actually very, very low bandwidth. And so we actually challenged David to find a way to make these antennas completely metal. And that's what we managed to do with this design. Let's go to the measured results. So this design is completely made of metal, entirely made of metal. And not only it's entirely metal-metal, it's using 3D printed technologies. So that allows us to build a lot of them very quickly and in a very, very cheap way. So if you want to fly those on CubeSat, that's perfect because they are going to be extremely low cost. So here you can see the achieved performance. So we got about 50% efficiency at the center frequency at K-band. The gain was actually pretty good. We got about 32 dB of gain, and the accuracy between measurement and calculated result is excellent. And now I want to show you a video of the 3D printing. So the way they fabricated this antenna was by doing different sections like this, and you can actually see the difference between each of them. Because when they actually run this test, they were trying to optimize the best process to get the best surface finish on these tiny elements. And let's take a look at it. So I want you to have an idea of the speed. That's in real time, that's not accelerated. So you can see that it would take probably less than 5 minutes per antenna to fabricate. So it's quite impressive. So then, following all of this progress on metasurface, we are now working on another one, which is similar to the first one I've shown, but entirely made of metal. Again, to improve the efficiency and to be more resilient to the environment. And in this case, we wanted to get 2 beams with 3 dB overlap, real 3 dB overlap, and get a good isolation between these two feed elements. You can see the feed horn and the bottom. Even though they are extremely close from each other, we still achieved isolation at the center frequency that is better than 17 dB of isolation. So we designed this antenna, we obtained all the performance that we wanted, and now we need to figure out a way to fabricate these in a very reliable way that will survive all the stringent environmental requirements that we have. And another thing that we would like to point out here is that, as I said, we're working on CMOS. Our lead for the CMOS on-chip radar is Adrien Tang, Dr. Adrien Tang at JPL. Very, very clever engineer. He comes up with a lot of very good ideas. In this case, he came up with a way to actually even improve in real time the isolation between the two elements. So any power that might go from the transmit antenna to the receive antenna, so one is transmit, the other one is receive, you have a systemic error that's due to the S parameter that you have here. And as soon as he turns on his radar, he has a program that allows you to cancel that contribution in real time, improving the isolation from 20 dB to almost 50 dB. And I'm not showing these results here, but we will share that very soon in publication. As soon as we have the antenna and we put everything together, and you will see that this is a very clever technique that will probably open up to a new type of radar that we might fly in the future. Okay, now I would like to discuss about Mars helicopter. So the Mars helicopter is on its way to Mars with the next rover, Mars 2020, which should land, I think, in less than a month now. So I invite you to follow the progress and watch the landing, because the landing is always a very, very critical event that is being followed all around the world. Everyone is crossing fingers that everything goes well. This time, this rover will carry an helicopter at the bottom of the rover that will deploy on the surface of Mars, and we will have 30 days allocated to us to perform all the flight maneuvers that we need to demonstrate to show that it's actually possible to fly on the surface of Mars. So my contribution to this project was the telecommunication subsystem, where I developed the antennas for the helicopter, but also for the rover. I also did all the link budgets to make sure that the link will close successfully within all the constraints that we have. And I'll show a little bit details about that. So we use the monopole antenna, so it's linearly polarized, and we place that on the surface of this solar panel. The surface of the solar panel is made of carbon fiber, and the carbon fiber is actually a good reflective surface at UHF. So we're taking that into account to improve the performance of the monopole. But still, as you can see, the ground plane is still fairly small compared to the monopole. So you have to be aware of these constraints and how they will impact the performance of your antenna. Not only, we also have blades to fly, obviously, right? And these blades are made of carbon fiber filled with foam so that we can have the lightweight blades. And people did not expect that, but carbon fiber is a very good reflective surface at UHF. I think in this case, we're operating at 914 megahertz. So we were extremely constrained in terms of mass because the entire helicopter needed to weigh less than 2 kilograms, and they allocated less than a gram for the antenna and the cables and the radio. So it's very, very constraining. And we still need to survive the stringent vibration and shock levels. And we had to come up with a design that was fairly easy to make and cheap as well, which is constraint that we usually don't have for flight missions. But here was technology demonstration, extremely constrained. So we had to meet all of these requirements. And that's the antenna you see here. And that's the flight model that you see here, where we actually tested the antenna. We verified the S11. We did not verify the radiation pattern because we were pretty confident that such a design was simple enough that if you have good S11, you will have good radiation pattern performance as well. So we did test the DEM, but not tested the DFM. Okay, so the radiation pattern that I'm showing here is actually very important, and I want you to pay attention to that. The blue line shows the vertical polarization, and the red line shows the cross polarization, which is H, horizontal polarization. Now, on the right is when we start including the, first, the reason why you don't have a very, very low cross polarization to start with is due to the asymmetry of this ground plane. If you have an infinite ground plane, then you will have a much better cross polarization. So that's the first constraint. The second constraint is that now you have blades. And as you put blades and you rotate them, you will see that the cross polarization is affected as well. So this is what you see here. In real time, the blades are turning, and we have to account for this impact on the radiation pattern performance. Then we have constraints on the rover as well. And the rover at the time, they were not sure whether the helicopter would be included into the mission or not. So they told us, well, you guys get this spot and don't bother us because we cannot accommodate anything for you guys. We're too far along the mission. So just make it work with this constraint. So we had no ground plane. So you can see here, this is the surface of the ground plane. Not very convenient when you need vertical polarization using a monopole, right? So, and not only, we were in a location where we would be affected by multipass and shadowing because of all the elements on the rover. So we put together a graph model to assess the impact on the performance, and you can see here the radiation pattern where the copole is in blue and the cross pole is in red, but sometimes they overlap. Sometimes the cross pole is even higher because of this multipass and shadowing effect that I was talking about. So So you have to be aware of that, and you have to account for all of that when you are assessing the link. So the map that I show here is actually the link coverage. And so in dark green, I show the receive power that is higher than minus 99 dBm that allows us to reach 250 kilobit per second. And in light green, I show 20 kilobit per second. And the circle in the center is 250 meter diameter, and the one on the outside is 1 kilometer. So this tells you where you can communicate. So in the center is where you're going to be in average. The one on the right is the worst case. So that's basically when the helicopter copole and crosspole overlap. So let's say the blade rotate and they end up in a place and in an orientation with respect to the rover that puts you in the worst place where the cross polarization is going to be the worst. So that's where you are. But when we do link budget for space mission, we never design for worst case. Otherwise, you would just explode the budget. So you have to be aware of statistics. And so that's what I'm showing here. On the left is the best case, center is average case, and the right is the worst case. So if you are in a direction, if you place the rover in a convenient direction, you will always be able to communicate with it. If you end up here, for example, where it's white, you will not be able to communicate. So all of that are things that you need to be aware when you are assessing the capabilities of your system. And then when we fly, there is no problem anymore. So when you fly, you have very, very good coverage. And the reason is very simple, that the propagation loss is much better because now you don't have multipass with being so close from the ground. So we went into the field and we did a field test. We had the mock-up for the helicopter, a mock-up for the rover. For scale, you can actually see us there. To give you scale, we actually took this picture, but then the helicopter was located at, I think, about 200 meters. And again, here you can actually see what we did, what we actually rotated the rover, so we can also have an idea of whether the predicted radiation pattern on the rover was fairly accurate. And so we rotated this rover in a very, very sunny day, very, very hot day in California. I can tell you that was a very, very tough day for us. Engineers are not used to manual work, so that gave us an opportunity to work out a little bit. And here you can see, again, show the worst case, average case, and best case. And we never end up being worse than the worst case, which is exactly what we want. So the results were very positive. So the predicted communication link, so the received signal at the receiver was as predicted. So that was very, very positive. Do I have more time or should I end very soon?
Okay, as you like. We enjoy your presentation.
Okay, so I'll just finish then. So then I would like to talk about the Europa lander. The Europa lander is a mission concept that is very, very, very innovative and very, very challenging as well. Probably one of the most complex NASA missions we have had in terms of planetary exploration from an engineering point of view. And that's only my point of view, obviously. So the reason why we want to go to Europa, which is the icy moon of Jupiter, is because scientists think that this is the place where the likelihood of finding life is the highest. And so as a result, they would like to land on the surface of Europa, and they would like to perform an in situ measurement to demonstrate that. So to do so, they put together a team of very, very smart engineers at JPL to come up with a concept to demonstrate that this mission is feasible. However, when they proposed the first concept, the review board came back and told them, no, this concept is not acceptable. The cost is way too expensive. If you guys are not able to bring back the cost by at least half, this mission is never going to happen. So the engineers said, well, the only way we could reduce the cost by half is not to have an orbiter with telecommunication capabilities send with the lander. That's the only way. And to do that, we will need to enable direct link to Earth, which they thought was impossible, and put that to bed right away. And that's the reason why they did not account for that. The reason why they thought it was impossible is because the efficiency numbers that you need to achieve is higher than anything that we have achieved before. It's more than 80% efficiency for a flat antenna, because you cannot deploy an antenna on a cryogenic environment. So the temperature are too low. And you're also very constrained because you cannot use any substrate on your Europa surface, because the radiation level are just stringent. So they will not survive. So at the time, I was not involved with this mission, and I overheard the conversation in the hallways right in front of my office. And the telecommunication lead say that, oh, we're cooked. If we can find a way to do direct to Earth communication, they're just going to cancel this mission concept. And the group supervisor at the time replied, well, that's not possible. The antenna that you guys are using is the best you can achieve with this constraint that we have. And I heard that question, I heard that statement, and I said, hey, I think I can do it. And they first laughed, but then they told me, well, we don't really have any solution. So if you think you can do it, why don't you go ahead and come back with a concept? And so this is the concept that I propose. This antenna is entirely made of metal. It provides dual frequency operation with circular polarization, and it's made of metal. And it can survive the high radiation levels because it's completely DC grounded. So there is nothing flooded. The entire, if you put a multimeter to check the connectivity, everything is connected to each other. So it's completely DC grounded, which allows that when you're bombarded with electrons, everything is going to bleed into the ground. But nobody believed me when I proposed that. Not only because the RF performance were much better than anything we have ever flown before, but also because I claimed I could survive the environment of Europa, which is cryogenic temperature, and also very high radiation levels. So we first fabricated this subarray, which is an 8x8 element. We demonstrated the RF performance and proved that we could get aperture efficiency more than 80%. So let me clarify when I talk about efficiency that the efficiency is defined as the highest gain directivity that you can calculate from the area that we have. So that's the gain that you measure over that ideal directivity that you can get from the surface area. And we got more than 80% efficiency. Now, just to put things in context, all the antennas that we've flown before, the baseline that they were using for this mission was providing 70% at uplink and 18% at downlink efficiency. For MSL, which is the latest rover that we have on operating on Mars, provided about 50% efficiency at uplink and 40% efficiency at downlink frequency. MER, which is Spirit and Opportunity rover, showed 25% efficiency and 50% efficiency. And I claimed that I could get more than 80% efficiency at both uplink and downlink. That's why everyone laughed at me and didn't think it was possible. So those are the design that have been flown before. This one is the concept that was used on the Europa that they were using as a baseline, thinking that this was the best you could do with the environmental constraint that we have on Europa. So not only this antenna is smaller, it's more efficient. So it relaxes the pointing requirement because your beam width is much broader, but also it can handle much higher power than any of the other antennas. So then they told me, well, okay, you did these small antennas, but we don't really need the small antenna. We need a very large one. So what makes us believe that you will still maintain the performance for a large antenna? So we built a 4 subarrays, a 2 by 2 array of subarrays, which I showed before, which are excited with waveguides, which allows us to maintain the efficiency. And we got about 80% efficiency at uplink and downlink, but not only, we got very, very good accuracy between measurement and calculation. Why is that? Because it's entirely metal. So the surface finish is the best you can get. And that's the reason why you can get such good accuracy at X-band. This shows you how things fold on the surface of the lander, and that shows you why the antenna needs to be folded, because on top of that, you have the landing gears that will go on top of this. So you don't have any more volume to store the antenna. So even when we demonstrated this large array, then they wanted the real one. So we said, okay, we'll do the real one, which is about 80 centimeter by 80 centimeter. So it's 32 by 32 patch elements. And as you can see, the accuracy is as good as what we got before. So we showed that this antenna could meet all the requirements. We qualified it to achieve technology readiness level of 6, which is what's required to fly the technology. And we did IESD testing, which is electrostatic discharge, to prove that we could survive the environments, the high radiation. So we put it in this chamber that bombards it with electrons, and we have a probe that's connected to the inputs that tell us how many discharge we are seeing and what are the magnitude of this discharge. So if you have discharges that happen nonstop, then your receiver will be impacted and you won't be able to communicate. And you can even destroy the receiver if the amplitude are high. Not only we didn't see anything with high magnitude, but the people told us, well, we saw only few of them and they are so low that we don't really know if they're real or if they are noise. And that's the first time ever that we see that testing a hardware. So that tells you that this antenna is extremely resilient, and it's always possible to do such things when you understand how the physics behind operates. And we discussed a lot with the IESD expert to know what the mitigation in the design should be implemented. And this is a picture of what the lander will look like. We actually have the real antenna here, and we also have the real landing gear that they are testing to show that they can successfully land on a very random surface. And so we're very excited. There is a lot of technology development that are going on at JPL to make sure that this mission will be successful and ready to go once we are given the green light to go by NASA. Currently, it's still a mission concept, so we're developing all the technology to enable this mission. But we are at a very, very, very good state to say that we're very confident that we're ready to proceed with a mission like that. Okay, and just to finish and conclude, I provided a few references that I invite people to read if they're interested in the topic. And I have a book that's coming up very soon, early 2021. Actually, I need to update this date, published by Wiley. So feel free to take a look at it. We also got this month this publication on the Antenna and Propagation magazine on the Morse helicopter, so you can have more insight on how we designed these antennas and how we did all the link budget calculation and the field test. So feel free to look at all of that if you're interested. And thank you for having me here. I'm very excited to share all of this knowledge and innovation with all of you guys.
Thank you, Nasser, for this wonderful presentation. I think waiting for Mohammed Saidi, Professor Saidi.
Hi, can you hear me?
Yes, we can hear you.
Hi, Nasser. Thank you so much. Thank you so much for your amazing, impressive talk.
Thank you for inviting me.
You remembered that you remember that we were planning to invite you the last time we met in was it in Abu Dhabi or in UAE a couple of 3 years ago, and unfortunately it could not happen in person. Probably very soon we will be able to host you here in Morocco and to have
would be my pleasure
in person talk. Yeah. So the talk is open for question. I have seen a question from the audience here. It's in the chat box. Christine is asking. Well, thank you, Dr. Hart, for yeah. Can you read the question? Probably asking. Yeah.
I don't think I can read the section, so I'll ask you to read them to me.
Oh, okay. Okay. So the question is, she would like to know the possibility of using leaky wave antennas as potential candidates for space applications.
Yeah. So leaky waves and metasurface antenna are very similar. They have a lot in common. So as a matter of fact, the first one that I showed with the slot is considered as a leaky wave antenna. So it's definitely possible. It's just that one of the drawbacks of the leaky wave is that they are not very broadband, and the beam direction is changing across the frequency band. And that's not a good thing for most radar application. So we need a very good beam pointing stability over the frequency band of operation. So unless you find a very specific concept that would take advantage of that feature, then that's not a very good option. Next question.
Okay, thank you for any other question?
Okay, I think what kind of simulation tools that you use to simulate the reflector array?
We use different tools depending on what we do. Like I said, we use a lot of TICRA grasp tools. We also use CST, HFSS. We use our own code, but most of the time we don't need to because this software are very, very complete. What else? Yeah, that's about it. Those are all the different tools that we typically use. And the decision of which one to use depends on obviously what problem we're trying to address. So for reflectors, I always use TICRA. For feed horns, for reflectors, I usually use TICRA shunt. And then I switch back to CST to finalize the model. For very complex antennas like the Europa antenna, I use CST and HFSS. I always correlate the result with two tools to make sure that nothing was wrong. That's something I always advise people to do. And yeah.
Okay. Any other question from the audience? In such case, I will ask a question, Nasser, if you mind, if you don't mind. So, I will ask a question regarding possible cooperation opportunities with the universities here in the region, with the GPL and with NASA, especially in antennas, microwaves engineering.
So we can discuss offline. I mean, we can discuss whether it's possible or not and what the venue are to do that. We collaborate with universities in the US. It's much more difficult to collaborate with universities abroad, but I can explore whether that's possible or not.
Okay, thank you.
I don't
Any
think.
other question? Okay, so thank you so much, Nasser, for the amazing, wonderful talk. And I really hope to see you in person here in Morocco very, very soon. Can send you, as the invitation is still open. And okay, so now we have actually next session. It will be chaired by my colleague. I don't know if you have any other word to say, Nasser.
No, that's all. Thank you very much for having me. It was my pleasure to be here. So thank you very much. I hope you guys got something out of this presentation.
Okay, yeah. Thanks, Nasser, for this presentation.
Thank you. Okay, thank you.
Thank you.
Okay, so probably we move now to the next talk. So I see that Christophe is already here. So, but I think who is?
So we need to give the floor to Wahid. Professor?
Yes, Wahid Nayari is. Are you here? Wahid Nayari, are you here? Professor Wahid Nayari, are you here? I see him. Is actually here, probably. Yeah.
I think he just left.
No, he's here. I see him in the list here.
Yeah, but no. Okay, you can introduce Professor Saidi.
You can go ahead with the presentation of Christophe. I can see the Wahid in the list of participants.
He was with us, but I think he left. So you can introduce Professor Carlos. Hi, Carlos.
Hi, good evening. Hello, everyone.
Fine.
We're fine, thank you. Thank you. Thank you, Christophe, for accepting the invitation and for the also your contribution to MMS'20.
Thank you for the invitation. I hope it's not too late. Everyone should be tired.
No, I don't think so.
No,
no, not really.
No. Okay. So we had a lot of exciting presentation.
Okay, and there are still a couple of people around.
Yeah.
So okay.
And also we have some people on YouTube and Facebook.
Okay. Okay. So shall I start?
Yes, sure. Go ahead, please.
Oh, okay. Well, okay. So sorry not to be physically present in Morocco. It's always a pleasure, huh? And I'm giving this talk from my office in Leuven, at KU Leuven in Belgium. And I'm going to talk about magnetless non-reciprocal metasurfaces. Let me get to the laser pointer if I can. Sorry. Yeah. No, this is the pen, and this is the laser pointer. So I'm going to talk about magnetless non-reciprocal metasurfaces. And that's a very hot topic at the intersection of three hot topics. As you know, metasurfaces is certainly a revolutionary field in electromagnetics engineering with the new possibilities of transforming electromagnetic waves. Non-reciprocity is not something new, but there have been a lot of recent innovations in this area. And magnetless non-reciprocity, which means non-reciprocity without using magnet and ferromagnetic materials, for reason we'll see later, is something particularly new. So the combination of these three ideas is something very, very interesting and hot. And I will mostly talk about the microwave regime today, but I will say a word in the end about the extension to the optical regime. So that's supposed to be something very general. Okay. So let me start. So first I will define what is non-reciprocity. Even though it looks simple, it's not always trivial. And then I will give some milestones and talk about the mainstream technology for non-reciprocity. Then I will present a concept that is used mostly by physicists, but that is necessary for advanced non-reciprocal design and research. It's the concept of time reversal symmetry breaking. I'll show you why I think this is important and useful. And from this point, we'll go to non-reciprocity without magnet and without magnetic materials as well, for reasons I will have explained before. Then we'll go to metasurfaces. Obviously, a lot has been said about metasurfaces in this conference, and metasurfaces are a fantastic platform for non-reciprocal devices. I'll show that. And once we have established this, we have the metasurfaces, we have the non-reciprocity, the magnetless non-reciprocity. We'll go through a number of applications for all of that, okay? And wrap up. So a few words about non-reciprocity from a general perspective. You see here a review, an overview, a critical overview perspective paper that I wrote in the Physical Review Applied. If you want to know more, much more about this, you can look at this, this paper that is quite comprehensive. So, you know, let's start slowly. Non-reciprocity is a concept that is familiar to our daily lives, you know, coming from the Latin reciproque, meaning to the front as to the back. And, you know, I give you a present, you give me a present. That's something that is reciprocal. And if you don't give me a present, it's non-reciprocal. So that's something that is very obvious. But this is also present in all the branches of physics, and not only electromagnetics and photonics, but of course also acoustics, thermodynamics, electrodynamics, quantum mechanics, and relativity. So it's present in all the fields of physics. So that's something extremely important and general. And the archetype of a non-reciprocal a system is the boring isolator. I need to start with this, obviously, where simply the power goes in one direction and it's prohibited in the opposite direction. Typically in the opposite direction, it's dissipated, you know, into heat. That's what a typical isolator is. And typically, this is characterized in terms of transfer functions, here scattering parameters that are different in the different directions. That doesn't need to be about the amplitude. It can also be a non-reciprocal phase shifters, of course, where it's the phase that is not the same in the two directions. So non-reciprocity is generally defined as for a system as a situation where we have different transmission field ratios like S1, S12, when the source and the detector are exchanged. And naturally, there are many more components, phase shifters, non-reciprocal radomes, and many others, both in the microwave regime and in the optical regime. And there has been a time lag of about 30 years between the two developments, because of course the microwave sources were invented about 30 years before the laser sources. So in terms of history, you know, people typically refer to Michael Faraday for the beginning of the history of non-reciprocity. But Faraday was mostly interested by noting that applying a magnetic field to some materials could rotate the polarization of the wave going through. He didn't explicitly mention the non-reciprocity of the phenomenon that I'm going to describe later. And it's really only Stokes and Helmholtz that specifically noted that if you were exchanging the source by a detector and the detector by the source, then the wave would experience different adventures, which would lead to the asymmetric scattering matrix. And a bit later, Kirchhoff reformulated the works of Stokes and Helmholtz, and he noted in passing the equality between the absorptivity and the emissivity of antibodies corresponding to temperature, which was the basis for the black body radiation theory of Max Planck and the beginning of quantum mechanics. So very deep roots. Huh? And in the meanwhile, Rayleigh noticed, and I will also discuss that you can get non-reciprocity through some nonlinearity. And the next theoretical step was done by Onsager, a Norwegian scientist who got the Nobel Prize for this. And he put non-reciprocity on a universal basis that is actually involving thermodynamics and stochastic physics that we don't have the time to talk about. So it seems that everything was done. However, recently we hear a lot about non-reciprocity in the context of metamaterials. And this talk is to show you why this is making sense, I believe. So over the past 70 years, non-reciprocity, non-reciprocal systems have been essentially dominated by ferrite technology. And ferrite technology uses ferrimagnetic compounds such as YIG, for instance, yttrium, iron, garnet, and many other oxides, and also permanent magnets that are required to magnetize those materials, okay? And this has been for 70 years. However, there are fundamental drawbacks with this technology. The first of them is that the magnets that are required to bias the ferrites, they are heavy, bulky, and they're opaque to electromagnetic waves, you know. Now, also the crystal structure of those ferrites, you see here the YIG crystal structure, is incompatible with that of 3-5s, so semiconductors or 4s. And so this technology is not compatible with integrated circuit for mass production. That's a huge problem. There are other problems also. Once you have a material, you have a single ferromagnetic resonance that is limiting to some extent. You also have the static response, the hysteresis that is fixed, entirely determined by the molecular structure of the medium. But also you have some even dangers of injuries with the magnets. You can demagnetize the environment. Those materials tend to be brittle and corrosive. Their extraction is highly polluting. And these rare earths, they are very unevenly distributed on the earth. They are mostly in China, in fact, and that's not an easy thing. So there are a lot of drawbacks, and therefore for us, finding a solution to this has been almost of a mystical quest. How could we find magnetless non-reciprocity to get rid of all these drawbacks? Okay, so to understand how to find a route for magnetless non-reciprocity, we had to ask some fundamental questions. And this leads us to the concept of time reversal symmetry breaking that I'm going to present right now. So let's get back to our brave isolator. Here it's a Faraday isolator. And the way typical microwave engineers look at this problem is they look at it in the space domain. You know, if this is Z, at Z1 you have the source, at Z2 you have the load, and then you make sure that the transfer functions are non-reciprocal. Now, time reversal symmetry is a thought experiment and a mathematical transformation that is very powerful, and that requires to change the perspective. Now we are going to look at the system in the time domain. We're looking at the evolution of electromagnetic wave in the time domain. So see what happens in the time t equals to 0. We have the wave here. We have a vertical electric field in this rectangular waveguide. Then the wave propagates through the system. It first rotates through this torsade and then back due to Faraday rotation. And after a time t, it ends up at the output, still in the vertical polarization, as you can see here. Now, what we do here is we reverse time. If we reverse time, you know, in the velocity, which is space divided by time, space doesn't change, time changes. It means we reverse the velocity. So it means we reinject the wave from that side, okay? And so that corresponds to changing the sign of t. We go here, and now we relaunch that wave with vertical polarization. And if the system were reciprocal, we would return to the original state. That's called time reversal symmetry. But because this system is non-reciprocal, you see the field rotates in one direction, then it keeps rotating, and it becomes parallel to a resistive sheet where it gets dissipated. So the output field here is 0. So we don't return to the original state. And so the system is not time reversal symmetry, because when I change the direction of time, you know, I don't go back to the origin of time, but I get to another point. So that's a bit weird for engineers, but it's extremely powerful, as you shall see. Now, in physics and in electromagnetics, all the quantities are either symmetric or anti-symmetric when you change the sign of time like this. For instance, the electric field is symmetric, because if you take a parallel plate capacitor in a static regime, if you change time, you know, the charges don't move. Okay, so the direction of the electric field is not changed. But the magnetic field is asymmetric or odd, because if you change time, as we saw, you change the direction of the velocity, and then you change the direction of the current, and from the change of the direction of current, you change the direction of the magnetic field. So if you change the sign of time, you change B. So what is the consequence in Maxwell equations? You see here that if you replace t by minus t, you change the sign here, but we have seen that B also changes. So minus over minus, there is no change on the right-hand side. And on the left-hand side, if you change the sign of time, as we saw here, we don't change the sign of E. So we preserve the parity. So the Maxwell equations are not changed. And one says that Maxwell equations are symmetric under time reversal. So let's look at an example to better understand what that means. So in general, the laws of physics, they are symmetric under time reversal. Let's use again our time diagram here, positive time, negative time. And let's look at 3 examples, okay? The first one is the one of a chiral medium that probably has been discussed here. So it's a medium composed of small spring resonators. And then when the wave goes in one direction, the current winds in the spring, and that leads to a rotation of the polarization as seen here. And so we are here, we have a little rotation. When we reverse time, it means when the wave is reinjected in the opposite direction in this thought experiment, then the currents that wounded, now they unwind, okay? And as a result, the polarization gets back to its original state. So this system is time reversal symmetric, okay? And therefore it is reciprocal. Now let's take a ferrite, or it could be a plasma, a sheet of graphene, for instance. So in a ferrite, typically we need now a magnetic field. So we apply a magnetic field through a magnet. And through Faraday rotation, we also have a rotation of the polarization as we go through. Now, if we apply the parity rules that we saw in the previous slide, remember B is asymmetric. So when we change the time, we should also change the direction of B. And if we do that, the wave sees the same landscape from the left and from the right. And therefore, this angle is going to wind back just as in the chiral situation. So again, we have gone this way, that way, and back to the origin. So this system is fully symmetric. It's fully reciprocal, sorry, okay? But what happens in real life is when you build an isolator, you assemble the ferrite material and the magnet, you close the box and you sell it. So the direction of the magnet is not changed. The magnet always looks in the same direction. And as a result, you fail to respect the odd parity of the magnetic field, and you break time reversal symmetry, okay? So that's the reason why now the angle rotate by phi and then keeps rotating, you accumulate the angle, which is a Faraday rotation. Okay, so in this case, you have an asymmetric permeability tensor and so on. Now, that sounds a complicated thing to do when you look at a simple isolator, but I will show you an example where the situation is not so trivial, okay? And there will be more and more sophisticated, also millimeter wave special non-reciprocal systems. So this is a special system. You have an array of lasers here, and followed by a lens with a screen and an aperture in the focal spot of the lens. So you see here, the rays by the different lasers go through the aperture and essentially get received by an array of detectors on the other side. Now let's assume we put the sources on the opposite side, on the right. If we send the wave here, now what happens? Obviously only the central beam goes through. So what do you say, everyone in the room, is that a non-reciprocal system? Some people have erroneously said that, yes, it is a non-reciprocal system, but it is fully reciprocal, in fact. It is asymmetric. And if you use the time reversal symmetry concept, you can easily see that. Remember, time reversal symmetry is changing the time, therefore it's changing the velocity, okay? So what does it mean? It means we need to take each of the rays and change the direction of the rays. This is not what we do here, because here we send the rays horizontal and we should send them in this direction to make a test on non-reciprocity. So such a system is perfectly reciprocal. It is only asymmetric, and you would never be able to do something like a special isolator with a system like that. So that's not what we are looking for, okay? What we are looking for is actually non-reciprocity, and non-reciprocity that gets rid of the magnets and the ferromagnetic materials. You see here a special issue that we guest edited with a couple of colleagues, where you have a number of ideas that I'm going to summarize here. So if we cannot use magnets, we have to ask the questions, what can we use? How can we do that? Sorry, I had an issue here. Okay, what is the fundamental condition to achieve non-reciprocity? Well, first of all, if you look back as an inspiration to the Faraday non-reciprocity, you see that we needed a magnet, right? We used a magnet from the input to the output, and the magnet is fixed whether the wave comes from the left or it comes from the right. So in fact, the system is not only time reversal asymmetric, but it's also asymmetric in space, because we have the South Pole here and the North Pole there, and not the other way around, okay? So a simple way to see it, you know, if you start non-reciprocity, if you have wind blowing in your back and wind blowing in your chest, of course, you don't run at the same velocity. So this is here a simple example of a space-time asymmetry. The wind blows to the right and therefore affects your experience. So there are actually two fundamental ways to achieve non-reciprocity. The first one is to use an external force, just like the wind I was talking about. And this is actually related to another topic I won't talk too much about, but the space-time metamaterial system. I'll just say a word about this. And you see, it's really a motion, for instance, a piezoelectric motion here, that is the external force, and that allows, like the wind, to get non-reciprocity. The second one is, instead of using a dynamic external force, like the wind or piezoelectricity, we use a fixed force. That was the case with the magnetic materials, but we want to get magnetless, so I put this in brackets. But that's also possible with an electric bias, and that's our transistor-based non-reciprocal system that we like very much, and that I will describe a bit later. So this is the first category. We have an external force that breaks time reversal symmetry. The other possibility that I will explain shortly is to use nonlinearity. Okay, you'll see you can also have, even without the application of an external field, a similar effect where the wave goes more to one direction than it goes into the other direction. So let's take a look at how this works. I don't think many microwave engineers know that. So I'll show you, and I will criticize that approach, and I'll show you why I don't like it. So I just remind you what I said, that this was already realized by Lord Rayleigh, you know, who was obviously a very smart man. And the general operation principle, even though there have been plenty of structures published in the literature, but the general principle can be understood with the help of this structure. So what do we have? We have here a pair of two media. The first one, the gray one, is linear, and the second one, the brown, is nonlinear. And it's nonlinear with a nonlinear term, so an intensity-dependent term that is strongly lossy. Okay, so the way that works is, first we have to assume, you know, that we have a considerable amount of reflection, even very high, like 99% reflection. So you inject a wave at a given power, and then only 1% goes through. And when the wave reaches the nonlinear medium, it is so weak that it doesn't significantly excite nonlinearity. So this is almost invisible. And therefore, the wave here can completely go through. We still have 20 dB loss, but at least, you know, we still have some way that goes through. But when the excitation is from the other side, now the magnitude is so strong that it triggers, it biases, it self-biases the nonlinear medium. And therefore, we have a lot of loss and loss exponential dissipation. And then we have further loss due to the reflection that we already had before. So in this case, we get only minus 40 dB. So this is a non-reciprocal device, of course, because there is a difference in the transmission of 20 dB. Okay, you see here, that's things published in Nature, you know, interesting physicists. That's an implementation with two diffused photonic waveguides and rings here, coupled ring resonators with whispering gallery modes. You see here, this is a reciprocal system or linear, so it's hard to see, but in fact, we have the same transfer function. In this case, you see the input, and here you see some dots that indicate that you still have some power, but if you excite from the other side, you see nothing. So in fact, what happens is that this ring is nonlinear and lossy, okay? So the energy that goes here strongly decreases here before it gets to the other one. In contrast, the weak energy that arrives here doesn't trigger the second. Now, this is not a realistic thing for an engineer. You know, it's important to understand, because if we have nonlinear system, we need to understand why this leads to non-reciprocity as noted by Rayleigh. But that's not the right way to do non-reciprocal devices. First of all, of course, you always depend on the intensity of the input signal. Then nonlinearity generates harmonic and intermodulation products, usually not desired. The performance, as you see, are terrible because you need to have initially some strong reflection to get this effect. But probably the worst of all is that this doesn't work really an isolator, because if the two waves are sent from the two sides at the same time, what happens is the stronger, in this case, this one, is automatically going to bias the nonlinear medium, so that loss is very present. So the system in the other side is also being dissipated by that loss, and the system is 100% reciprocal in such condition. So you see, it's vastly useless for things like, and there are other types of issue and problematic. So that's very interesting to understand, but I don't think it's good for devices. Okay, I need to take a look at the time also. Now, the second one is the time modulation route. So remember, it's a dynamic modulation. In fact, that goes back to the time of the parametric amplifiers, you know, and all these devices, the 60s. You see here, you get a non-reciprocal phase shifter. It's not using any magnet, so it's magnetless. What it uses, it's a transistor, it's a mixers, two lower sideband mixers, and here you have a pump. So here you have a pump that is sending its signal with a phase omega p, and then it goes through a phase shifter, so there is an omega p prime. So if you come from the left, you know, you get omega p minus the input, and then omega p prime minus omega p. So you have omega p prime minus omega p for the phase. In the opposite direction, you have the opposite phase shift. I forgot to say that, of course, like in parametric system, the frequency here is twice that. So twice the frequency minus the frequency is the frequency. So there is only one temporal frequency in the system. And we also take the differences of the phase in the different orders so that we have a non-reciprocal phase shifters. And we know from our courses in microwave engineering that if you have such a non-reciprocal phase shifter, you can build any non-reciprocal system such as circulators. So this is a sort of a lumped element, you know, but there have been also distributed elements. And those were first studied by actually another deceased colleague, was a great friend of mine, Arthur Odiner. And in the 60s with Cassidy, he was interested in space-time modulated structure in liquid antennas, for instance. So you see here, in addition to the wave, you send a wave that is biasing an array of varactors, okay? As a result, the wave that goes on top of it sees a permittivity that varies in space and time, and it's actually progressing. So when you calculate the periodic, the dispersion diagram of such a periodic structure, then you get a skew diagrams, you know, so that's also called a space-time crystal, but I won't talk too much about it. And of course, it's non-reciprocal because the modulation is like the wind, you know, if you have the wind on your back or your chest, you have a different response. So that can have good non-reciprocal performances, but also it creates harmonics intermodulation products. Among the interesting things that you can do if this is in space, imagine you have a simple mirror or ground plane, the wave comes in here, it gets reflected there. But now when you have this perturbation that moves in this direction, this creates what is called a phase gradient, okay? As a result, the reflected wave is deviated to another direction, but at another frequency, unfortunately, you know, and then you can keep going. So you can manipulate electromagnetic waves in space. But we also need a dynamic source that is not so good as a static source. And that source can be pretty expensive. So for these reasons, the magnetless solution that I prefer, that we have been working on for 10 years, is the transistor-based metaferrite, okay? So that our first publication was in 2011. That was a big moment for us. And what we said, you know, is, okay, let's try to imitate nature. How does a ferrite work? Well, the way it works is when the ferrite is biased and then a wave is impinging on the structure, then it kicks the electrons that precess about the magnetic field of the structure. Okay, and as a result, you have unidirectional currents. So we said if with a metamaterial particle, we can imitate that, then that should work, you know. So we took here a pair of rings. I'll show you some more details, but essentially a pair of rings where the current in each flow in one direction only. And then that creates this magnetic moment that exactly corresponds to the equation of magnetism. And of course, we are then going to have, if we repeat that unit cell, we are going to have the same response as a ferrite. So I call this a metaferrite structure, you know, and the parameters like the ferromagnetic resonance is not controlled by of course, by the molecular crystalline structure, but by those resonators, and we can maybe do a number of things. So you see here, what we use is a current or a voltage to break time reversal symmetry. It's the static source, so it consumes much less. It's much easier to inject. The cost is lower. And as you shall see in the second part of the presentation, that allows you to do real non-reciprocal electromagnetic metamaterials for special control. Okay, so just to show you how this museum type of thing worked, you know, you have a wave that is impinging on the structure, and then you have this double ring. It has a circumference of lambda, and initially consider a time where the field is maximum, hitting the structural maximum. So this field is accelerating electrons, you know, of course, so the charges positive move here, negative move there, you know, and that's where you get your corresponding dipole response or dipole model of this structure. Now, a quarter of a period later, the field is zero. So there is no more field that is impinging on a structure. So now the electron charges can move where they want. So if there were no transistor loading here, they could move to the right, and to the left, you know, and then we have the polarization that remains linearly polarized as the superposition of two anti-cyclically polarized or rotating currents. But a transistor is unilateral because the bias of the transistor leads to an energy slope, you know, an energy cliff. And so the electrons can easily flow down, but they cannot get back up the cliff. So the charges can only move in one direction. And as a result, the current here will flow in this direction. And the magnetic field that is here radial, in fact, between the top and the bottom strip, as you can see here, the full wave simulation is rotating. And this is exactly the same thing as what happens with the magnetic moment at the atomic level in a crystal, okay? So, so we did an experiment. We're very excited. It was at that time my postdoc Toshiro Kodera. And according to what I showed before, we did this measurement, by the way, in the reflection mode. That was simpler for us because then we could put a ground plane and the biasing electronic on the other side. You see, this is the front with these metaparticles, and this is the back biasing, okay? So, you know, what happens is the wave comes in this way, rotates in one direction, dictated by the time reversal symmetry breaking of the transistor. And then if you time reverse the system or resend the wave, okay, you will keep rotating in the same direction. So in the end, the polarization is horizontal and here it was vertical. So that's clearly non-reciprocal. In fact, if you put a piece of ferrite on a mirror and you measure the rotation angle, you get that curve in the solid line. And the curve that we get with our structure is exactly the same. So that proved that we're able to create the first, actually metaferrite, the first magnetless non-reciprocal system metamaterial. And for us, this was an achievement. That's for me one of the nicest applications of metamaterials where they can really do things that no other technology can do. And I think that this will come into the industry very soon. So in the meanwhile, you know, we're happy. So we were playing around with some devices, also not only special systems. This is an isolator. You know, you have opposite cyclic polarization on the two sides. And so we either go in the same direction or in the opposite direction with these rings loaded by transistors. So this is a circulator. You see here, we have just 3 rings and that works beautifully. No magnetic materials, no magnet that can be fully integrated into CMOS. This is actually a diplexer. So the wave comes in there, goes to the satellite. And on the way back, that's a liquid wave antenna. On the way back, it comes here. It cannot go backward because of non-reciprocity, so it gets to the other port. So this plays both the role of a circulator, of an antenna at the same time. And also nicely, if you have a conventional system, to change the direction of rotation, you need to flip the magnet mechanically. But you can use an anti-parallel transistor system, and just switching from one transistor to the other one, you can flip the rotation the direction rotation, Faraday rotation, and so on, which is quite attractive. Okay, so now, but what we're looking for is not such simple components, but something more sophisticated for tomorrow's technology. We are looking for a material, a real material. You know, materials, of course, can be cut in small pieces while preserving their properties. They are good for mass production using technology. And we can also benefit from the advances of metamaterials over the past 15 years, okay? In particular, we can have responses, you know, susceptibility like permittivity, permeability, and stuff like that, that vary both in space and time and depend on omega and t. So there are lots of new possibilities. Some of them are described in this paper about space-time metamaterials. And you see what this is. Here, if you have a wave that comes in and the system starts to move in space and time, then you generate new frequencies represented by the new colors and you change the direction. So you change the Ks and you change the omegas, you change the space-time spectrum. But my topic here is really the transistor-based system, because the frequency is not changed, the source is a simple DC source. So I want to talk about that. And the meta-surface paradigm does this extremely beautifully. By the way, also we have a book coming up next year with my former postdoc, who's now at EPFL. This will be published in I think in March 2021. The first book on electromagnetic metasurfaces, theory and applications, and it can already be ordered if you wish to have it. For the sake of time, I think I will dramatically cut short this part to leave a chance for discussion in the end. So I will just remind the very basic concepts. You know, metasurfaces are a revolution, as I said before, because they allow to control electromagnetic waves in ways that were unthinkable just 5 years ago. Just 5 years ago. You see here this kind of cartoon animation where different things are done, reflection, reflectionless transmission, a surface wave, and orbital angular momentum, blah, blah, blah. We can do incredible things for the first time. Now, what is important for the following part of the presentation, where I'm interested in non-reciprocal metasurfaces, is just the key concept of the design here. So I'll just give you a brief flavor essentially in one slide and skip the next ones. So the key is how to design, how to synthesize that structure to realize such complicated and exciting transformations is to use enhanced boundary conditions. They're written a bit like this, but the left-hand side here, they are the same as n cross h2 minus h1, you know, that's what we have in textbooks. And usually in the right-hand side here, we have JS. But here we assume there is no impressed sources on the metasurface, but in contrast, we have the scattering particles that you see here. And these scattering particles can be modeled by surface polarizations, electric and magnetic, written here. So you don't need to look at the details, but just those are a generalization of the boundary conditions for the metasurface. But then if we make some simplification, I want to ignore these terms just for the sake of the argument. You know, the polarization, the electric response can be due to an electric excitation. That's kind of the permittivity, but it can also be due through coupling to a magnetic excitation. And this is a chiral type or bianisotropic term. So in general, you see here we have tensors, and this is 3 by 3 times 4. So actually that's 36 parameters in general. So for the first time in the history, we can control 36 parameters. When people tried to do that with chiral bianisotropic metamaterials that were 3D, that was not possible practically. Now we can really do it. And I think this is described in this book essentially, okay? So now just to tell you what are the quantities and how do we solve the problem, you see these triangles here, what do they represent? They just represent the difference of the fields on one side, on the other side. So T is the transmitted side, it's the bottom, and the other side is the incident and the reflected. So, and then we just take the difference. And of course, if we know the field, this is the specification, we just plug these fields in there. Av that we have here is the average. So it's the geometrical average, the field on the transmitted side and the fields on the incident side. So this is all known. We plug this in this equation, and the only unknowns are the susceptibilities. Okay, so the first phase of the synthesis of a metasurface consists of finding this function space and time that can be 36 parameters. And once we have that, we'll go to a second phase that I don't have time to describe today, where we'll find the exact shapes of the particles. Okay, so that's an extremely powerful technique. And of course, we will leverage here the plentiful of novel opportunities that are allowed by these degrees of freedom. Okay, if you still want an example, because of course this was not enough, I'll just show you one example. So let's take a very simple metasurface. You assume that they don't have polarizations perpendicular, so for simplicity, I'll take this away. And then the formulation simplifies a little bit to this. And then you see my problem is I have, in this case, 4x4 unknowns, okay? So the way to solve the problem is I need to set some quantities to 0. It means my problem is undetermined, okay? So I can try something. So let's say I'll put all the off-diagonal susceptibilities to 0. Then you see here, these 4 equations, they decouple into 4 distinct equations. So, and one actually is when the electric field is along X, and the other one is when the electric field is along Y. So you see what you can do here is you can control the electromagnetic field independently from each other for the 2 polarization directions. So it's by refringence, and what you can do, you can have, for instance, the X polarization that goes in one direction, and I don't have this here, but you could have, sorry, the Y polarization that would go in another direction, just to give you a sense. And also to give you a sense without any of the details, you see, if you exploit now more than one of these parameters, what we did before, you know, was say, okay, I want the incident wave here to be reflected this way and transmitted that way, okay? But if I keep more degrees of freedom, I can have several triplets of incident and transmitted waves. It's quite crazy. So you can simultaneously or separately have different types of transformations. Okay, so now I cut it short because I really want to go to the non-reciprocity and skip all of this. This is metasurface science and technology. You can look at the book if you want, or I can answer questions about this. Okay, so, but the point I want to make about the metasurfaces is we have a new mathematical tool that's called actually generalized sheet transition conditions, from which we can synthesize the structure for some exciting transformation. We find the susceptibility, then we can full wave simulate that, and then we transform these susceptibilities into actual shapes, and then we have plentiful of novel applications. Okay, so now let's get back to our interest, which is the non-reciprocal metasurfaces. Okay. I don't know if I'm doing with time. Do I have time to go through some applications?
Yes, okay.
Okay.
Take your time.
I will go through, and these applications I will describe only from a high-level perspective, because I'm going to use that knowledge on metasurfaces, but we didn't have time to look at the details. So I'll just highlight the very key points, okay? So to start slowly, let me describe something very, very simple, but nevertheless useful. That's a non-gyrotropic special isolator. So special, it means the waves are traveling in the air and not just in a circuit, as more and more often useful in millimeter wave and higher frequency technologies. They just want to have the wave going in one way and being cut in the opposite way. So an extremely simple concept to do that is to have an input phase that is a simple array of patches, then to have an isolated ground plane in the center, to pass a wave through a transistor to the other side, that will be the transmitting surface. So it's trivial, you know. So the wave comes, this is for one cell, for wave simulation, the wave comes and it goes through the transistor, possibly with amplification. And in the opposite direction, the wave is prohibited in the transistor and it's being dissipated in some resistive elements, okay? So that's very simple. And you see here that this is the wave going in one direction from here to here. And that one is the wave that is prohibited. Even it works for a large angular sector. So if you have, for instance, an antenna that needs to be protected from external interferences from a fall, for instance, you just put a a polarizer of that type, a radome, it also does not alter the polarization because it doesn't rotate the field, you know, and that will do the job. Okay, this is for theorists. Now, a second example is Faraday rotation. I showed you in 2011, we had a great eureka moment when we demonstrated Faraday rotation in the reflection. Now we go for something a little bit more difficult, transmission. So the wave has to go through. So we must make sure that the wave is not completely scattered by the transistor chip and so on. Okay, so here we have a structure that is something like some kind of distorted CPW structure. You see here there is the trace. Here there is one ground plane, and we remove the ground plane on the other side. The other ground plane ensures TEM transmission for wave guidance, but here we want scattering, so we don't care about guidance. Okay, so it's okay to remove one plane. So essentially the wave will go through this area and will go through the slot. And let's see a full wave simulation with the time reversal. It's quite interesting, I think. So you see, initially we send a wave, you know, from the back, and this wave is polarized horizontally, you know, horizontal like this. So this is the situation. It goes through, and then you see it rotates through the metasurface 135 degrees like this. Okay. So now, if we reverse time, and if we had a chiral structure, this polarization would get back to its original states. That's what would happen. So time reversal symmetry. But of course, what we have is a bias. And this bias is the electrical bias that is provided by the electrical battery to the transistor, you know, with the cliff, the energy potential cliff. Okay. So as a result, when the wave is launched back, you know, from this point, you see, it emerges now, it emerges here, okay, and not back to the original state. So there is a net rotation here of 90 degrees. And of course, this can be used to do the classical Faraday isolators. You know, it works like this: send a wave polarized perpendicular. Then usually it's used with ferrites. Here with transistors, you rotate by 45 degrees. The field is perpendicular to the electric strips of the polarizer. It goes through and then rotate back. And on the way back, now what happens is the rotation is still in the same direction that, you know, dictated by the transistors, and now it gets reflected and we get this way our isolator. So this was our very first proof of concept and I think that's the first magnetless Faraday rotator isolator. And this is far from being perfect. Okay. Now I don't have time for details, but what I can tell you is this was designed just from engineering knowledge, you know, but the metasurface knowledge allows us to crank this performance a lot. What actually happens that is not seen here is this system has a lot of reflection. And here, one key idea, I don't know if you can see me, you know, in metasurfaces, to avoid reflection, to match the metasurface, typically you put particles that have a vertical electric dipole and maybe a horizontal magnetic dipole. And when you look at the far field of these two dipoles, in one direction, they reinforce, that will be the transmission direction, and in the opposite, they cancel out. So that's the direction of incidence where you do the matching. So you see, you need an electric and a magnetic dipole that form a cross in the plane of the metasurface. Now here, what we do is we only have a magnetic dipole that is rotating. Okay, so we don't have this Huygens source. And what we need to do is we also need to make the structure electric. Okay, this is super complicated, but the message is, you see, here what we have is not a distributed medium like a ferrite in conventional technology, but just a metasurface that is deeply sub-wavelengths. So to be able to match it, we need some extra effort. And the extra effort is to have not only a magnetic, but also an electric response. And then we can have exactly the same response with a very high performance. Now, what do we have here? You see here, the angle is straight, you know, but what you can do is you can have the different particles here that are each different from each other. And by our theory in the book, you know, we can calculate these susceptibilities. And actually here, phi1 and phi2, they are the phase shift in one direction and the other direction. So that means that when the wave goes from the left, you will see a phase gradient, you know, like an antenna array. And when it comes to the right, it will see another one that will be designed by the metasurface principle. And then you could do things like this, you know. not only you have non-reciprocity, but you have generalized refraction together with this. So you can do a number of crazy things. This is an example. Here we have the radome, you know, a non-reciprocal radome, for instance. So maybe you have your radiator here, you know, and when the radiator emits, you know, the wave goes here and there. Okay, so it sends to the left, but on the receive mode you are sensitive here, so it receives from the right. Okay, so that's a non-reciprocal radome, very good for base stations. If you have a mountain here in between, you know, the wave goes through with the full effective aperture of the antenna. It's quite cool. And then you have here, if you look at the details, this is the metasurface here. Of course, that's the air. That's the air. This is also creating some kind of spatial isolator, some kind of exotic devices that still need to be implemented in the technology and in the industry. You know, then you can do other things. And again, I skip the details, but you see, you can have, for instance, a system that when you are polarized horizontally is non-reciprocal because there is the transistor in this loop. That's a magnetic moment with a transistor. But if the wave is in that direction, it's transparent or it's shifted by another phase. Or we can have a system that is really non-reciprocal in the two direction and induce Faraday rotation. All of these things are, so far at the level of concept, we are extensively building all of these structures to demonstrate them, and there will be an array of papers, a lot of papers coming up now that we have a good way to build this. Here is another interesting concept. This is what I call a non-reciprocal specular isolator. Okay, so what is it supposed to be? You know, it's almost like a simple ground plane, a mirror. The wave coming in is being reflected under the same angle, you know, but when the wave comes from the other side under time reversal symmetry, or we send it back, now the wave would be absorbed. We can imagine lots of applications for that, you know. So how do we do that? So, well, you see here, the thing is, we don't want to change the angle of reflection. That must be the same as the angle of incidence. So that means all the cells must be the same, okay, in this direction. Okay, so to break the symmetry in this x direction, what we can do now is something that has been very little used, and this is pretty advanced meta-surface science. We can now use vertical magnetizations, because you see, if you have vertical magnetization that radiates the same way on the two sides, when you take the derivative along x, that is odd. Okay, so in the end of the day, you won't see the same landscape if you come from the left or if you come from the right, you know. And if you solve the problem and you calculate this reflection coefficient, you know, it's horrible, but the only thing you need to see is this is a function of kx. So positive kx is going to the right, negative kx is going to the left. And you see here that this is not even in kx. So different kx change this term so that the overall term completely changes. So you can have transmission in one and reflection in another one, okay? Okay, maybe to finish, just another concept, I think it's the last, you know, you can play around and you can do some cavity sink, okay? That excites a lot of physicists. When the energy comes in, you know, if you fold the metasurface into a cavity like this, of course, the wave coming in cannot escape. So the energy is drawing forever inside. You can use this to load your telephone if you wish, and it's trapped forever. And this can be also used for some kind of camouflaging, of course, because the wave coming in never scatters forward, so or backward, and then that's a way to hide in a sense. Okay, I think without any details, the only thing I want to tell you is if you study metasurface science, you can do things like this. And what is the thing that we have here? You know, it's even more crazy. What we want to accomplish here is we want to have a different scattering when we go from the left. You see here reflection here, transmission there, and another reflection and transmission when we go from the right. Okay, and that's what we want all the time. But now we want that these transformations, both for the red wave and for the green wave, be independent of the angle of incidence. So this is something that everyone is after. So we want that if we change the incidence angle here, we still get the same reflection and the same transmission in both sides. Okay, so now that really sounds crazy. But if you make the calculations, And if you look at the transmission reflection to the right in red and to the left in green, you see that the angle of incidence is only involved in some terms here, okay? And these terms, they are the terms of susceptibility EE, MM, all the time, EE, MM. This is what I call the homo anisotropic terms, because it's electric to electric and magnetic to magnetic. And the other terms, I call them hetero anisotropic for obvious reasons, because now we have an electric response to a magnetic excitation. So that means if we can design a metasurface where we eliminate by proper shapes, we eliminate these homo terms and we have a pure hetero anisotropic metasurface, then the transmission, the transformations that we perform will be completely independent on the angle. Okay, super powerful. In practice, of course, there will be some limitations, but I think that's a really new concept. Oh, just some examples here. This is an active metasurface, and so you see it amplifies by 10 dB in that case. So here it amplifies by 10 dB when the wave is normally incident in the metasurface, but also here shown if the wave is incident under some angle, you know, it keeps going as if there were no metasurface with exactly the same amplification. So this is an, if you wish, angle-independent amplifier. In the opposite direction, this is an attenuator, also for different angles, as I didn't show. And same thing, you can have an angle-independent phase shifter. I don't know if you feel, you perceive, you know, that the power of this, that's really interesting and groundbreaking new. Okay, so fortunately, we are getting to an end. Okay. So I described non-reciprocal systems, started with the basic ferrite, showed you that we can also, if we want to get rid of the magnet because the magnet is not good, we can get this through non-reciprocity to space-time modulation, but those have some drawbacks. And therefore, I propose to go by a static bias that is electric, compatible with some semiconductor technologies. And this is the metaferrite, the transistor-based metaferrites, you know, that exactly have the same characteristics as ferrites, but without the drawbacks, lead to some devices. And really, the excitement is we are at the intersection of three concepts that are very, as I said, hot. So non-reciprocity is also leading to diversity, because if the system gets non-reciprocal, S21 is different from S12, so you have one more degree of freedom. And then when you have systems with many ports, you know, you have plenty of new degrees of freedom, and you can use that not only for non-reciprocity, but also for diversity. And then, you know, getting this non-reciprocity without magnet, it has been a 70-year issue. It's not fully solved, it requires industrial developments, but the concept is there. And then the metasurface that can do the crazy things I discussed. So putting all these things together probably is leading to some things that are there to stay. And now the ultimate slide, you know, some people say, yes, but there is no transistor in optics. That is fundamentally true. You cannot purchase an optical transistor. What would be an optical transistor? It's not an electronic transistor that would be modulated by light. This is still a transistor with electrons. An optical transistor is a transistor with photons. Okay, it means you can control a grid. We can modulate photons with photons. Okay, and if this were available, then you can transport all this technology that I presented to the visible. So I discussed with David Miller, he's professor at Caltech. No, not Caltech. Sorry, Stanford. And he wrote this paper 10 years ago, and you know, since then, there have been a lot of photonic transistors. I talked to him. You still don't have an optical transistor that you can purchase, but you see that a lot of people are interested in that. And using some quantum systems, some hopes appear. Okay, so that essentially concludes my talk. I think we can do unprecedented things, non-reciprocal things with non-reciprocal magnetless metasurfaces. Now in the microwave regime and in terahertz, and soon probably also in the optics. Okay, so with this I conclude, and I thank you for your attention. I hope there is still someone. It's hard to tell.
Okay, we are with you. Don't worry.
You're still there?
Yeah.
Okay.
So we are waiting for Professor Neyri. Professor Nair, you are with us?
Hello, yes, I'm here.
Okay, so
Hello.
you have the floor.
Hello. Thank you for your very interesting talk. At the beginning, I was there, but I don't know why the organizer couldn't find me in the meeting. Thank you very much. That was a very interesting talk. Can you hear me?
Yes, absolutely. Sorry, yes.
Okay, so we have room for question, I think, yes? Any question from audiences?
Okay, I think I have one, but it is a technical question. Is about
Sure.
diodes that you use in your design. What about the power that can support?
About what? About the diodes?
Yeah.
They are not diodes. Be careful. This is a very common mistake. They are transistors. They are transistors. Okay. So let's spend 1 second on that. It's absolutely important to understand that. You see, if you take a diode and you know the diode can be used as a switch. You forward bias it, the current passes. You reverse it, it cuts it. But this is a switch in the two directions. This is an open circuit or a short circuit in the two directions. If you use it as a as a detector, you bias around the biasing point, but you transmit also in the two directions with nonlinearity. So a diode, in contrast to what people think, some misconception, is a reciprocal device. It will never work here. In contrast, a transistor is really a unidirectional component, because when you bias it, you create a semiconductor wall. And then the charges, as shown here, they can flow down the slope, but they cannot flow up. Okay, so the systems will not work with a diode. No.
Okay.
You need a transistor. Otherwise, there are very similar components as diodes in optics that will be much easier. So you need a system where you manipulate the junction such that you create an energy difference with a slope going in one direction and not in the other one. It's like skiing, okay? But in a diode, you can only do cross-country skiing. It's flat. You need a transistor for alpine skiing, although you don't do much of it in Morocco. But yeah.
Okay.
Any other question? In that case, I have a couple of questions. The first question is, as you presented there, you presented some non-reciprocal devices, for example, like isolator. But for real-world application, where we need a very low loss, for example, how far we are? I mean, what bottleneck do you see to reach a real-world non-magnet isolator?
Okay, so first a general comment, because I usually talk to various audiences, and this is a typical question in engineering audiences. Okay, I still want to make this comment. To be fair, you cannot compare a technology that is completely new with one that is very well established. So it's like comparing the first transistors of Shortley in 1947.
Sure.
Okay, but that is clear for you. Okay, now, so we didn't have. I cannot answer this question specifically with numbers. Why? Because we have not realized this in CMOS technology. I wish this would be the case very soon. So to really have all the numbers, you would need to really fabricate that. Not all we have here are prototypes, but we know how transistors work, after 60 years of history, 70 years. So we can have certainly high quality transistors. There will be a little bit of consumption, but we can have, at least in terms of the metasurface, transmission through essentially at 0 dB, minimal dissipation. And then the question could be, if you have a special isolator, how much isolation can you get? I mean, you can complexify the device and to get as much as you want, I would say, because in contrast to what happens with ferrites, now you design. So you can pile up several layers. It's like making a longer ferrite, but you can do also other crazy things. Like if you take a ferrite resonance isolator, the conventional one has only one band. Why? Because there is only one ferromagnetic resonance from the crystal. But in a system like this, you can have two rings of different sizes. So now you can have a dual band system. So the first, your question really, to really answer this question in a satisfactory fashion, you need to make a startup company, you know, and to develop the technology, go CMOS, systematically compare. There is also the issue of power handling. Ferrites have a very huge power handling because they have a large volume. Obviously, if you want to be very thin, you don't have much more volume. But you could use LDMOS, nitrate-based, gallium nitride-based transistors, and so on and so forth. So it's a case by case. And maybe this would not be a replacement. I don't think this happens, but probably this is providing a complement to a conventional ferrite-based technology.
And the other question, oh,
yeah,
sorry.
Yeah, go ahead.
Go on.
Yeah, well, and a problem that I encountered because I wanted to implement this with companies in the past, but the companies who do ferrites don't only do ferrites, they don't have the technology for semiconductors, you know? And the companies who do semiconductors, you know, you go to TriQuint and so on and so forth, they essentially do semiconductors with huge groups. So changing that in the industry requires a paradigm shift, you know? But I think this is coming little by little. We just need to leave it some time. That's all too new to be really evaluated. But if you ask me, okay, I would definitely start a company tomorrow. I prefer to do research, but if I have people, I would support them without any hesitation.
Okay. My other question is about nonlinear non-reciprocity that you described in slide 14, I think.
Yes.
Slide 14. Yeah. In case of nonlinearity, how to define a reciprocal system? For example, you excited port 1 with some level of power, and in port 2 you have some another level of power. So to test the non-reciprocity of the system, should you excite port 2 with the same level of power of port 1, or the power reach to port 2?
Yes, of course. That completely depends on the power. You know, that's what I mentioned here, the intensity dependence, which is a fundamental drawback of linear systems. But the worst one, you know, is in optics, people work much more. I reread this book by my friend Bob Boyd, Nonlinear Optics. This is kind of the Bible. What is even worse is when you're nonlinear, you cannot really define a transfer function, strictly speaking, because what they do in the PNAX, for instance, Keysight, they have, if you have one physical port, they have different, and one polarization, they have different ports with different frequencies, you know? And so what they do in optics, they calculate the transfer function from frequency omega naught to omega naught. They can also calculate the transfer function for the second harmonic generation from omega naught to twice omega naught, and so on and so forth, okay? But you see, I don't know if you got this point, and I think people have even published without really telling the entire truth. They published this and saying it's an isolator, and it's not really, because in a real isolator, you don't know when you have a wave getting back to your face to destroy, you know, your source. And when you have the two waves from the two sides, it doesn't work, okay? So to me, it's more an academic curiosity or a way to understand maybe ionospheric phenomena. It's very important if you work in space to understand why you have non-reciprocity, you know. But if you want to commercialize a device, you'll never do that. I will not bet 1 cent on that technology.
Okay, thank you. Thank you.
Thank you very much.
Any other question from audience? So thank you much. Thank you so much for your interesting talks, and
thank you to everyone.
Thank you, Professor Carlos, for this.
Professor Osman.
For this wonderful presentation. Okay, I hope to see you next time. Okay,
physically here. Yes.
Okay.
Thank you so much.
Thank you so much.
Have a great evening, everyone. Bye.
You too.
You too.
Thank you, Christophe, and keep in touch. Take care. Thank you so much for the presentation.
Okay, so thanks for joining us today for the second day at MMS conference. Tomorrow we have another talk by Mike Cook-Camp from Rod Schwartz, and also we have a session for students presentation in the context of Yarman Cardin student contest. So please connect and join us to join this conference. And also we will hand this conference by closing ceremony in which we will announce the winners for this contest and to announce also the 2021 conference, I think, will be with us. So thank you.